All right. Some of you are wondering what we're going to do with the next 17 minutes. Yesterday, we were able to do a time warp, but today, I want to do my poetry slam. So I have a 15-minute poetry. Yes, it's going to be beautiful. There'll be some interpretive dance. You guys are required to love it. We actually added into the rules that you have to love my slam poetry and interpretive dance. So, none of this, right, this beautiful room, the food, the transportation, none of this is possible without some amazing folks that host us for the last, really 3 years. It's our third year here at UCF. And UCF is just amazing. They don't just provide the facilities, but they provide personnel that really help us make this a great NAC. So I'd like to invite Pete Georgiopoulos and the Honorable Bev C. up to the stage. So these are the folks that are the leadership in UCF and the hosts that have really made all of this possible. Dean Georgiopoulos and I have spent many a late night on Zoom calls talking about the NAC. So special thanks to UCF and to UCF hosts and to Michael Georgiopoulos and Bev C. for all that you guys have done. Let's give them a huge round of applause. And then the other and central powerhouse of the NAC, I'd like to invite the North America Championship Director, Tony. Please come to the stage. So, Tony was a professor at South Dakota School of Mines, and if you look up in the dictionary, retirement, you will see not Tony in the, for those of you that are putting together a retirement plan, Tony and Bev are both terrible examples of how to execute, or maybe they're great examples of how to execute retirement because they really are making a difference with all the stuff that they do. All right, John, should I start my poetry or do something else?
What do you think? I think we desperately need a time warp.
Wait, you didn't even want to think about it?
That I think we can handle. Okay, so I guess get ready. Less than a minute to go to the start of the contest, and so the folks up here are going to release the balloons, and the contest will start in 45 seconds. All right, help us count down to the start of NAC. 10, 9, 8, 7, 6, 5, 4, 3, 2, 1. The contest is underway.
Good morning and welcome to the 2023 ICPC North America Championship. I'm your host, Second Thread, and we are here in the beautiful and warm Orlando, host of the University of Central Florida, the host university here. We should have a wonderful problem set for you guys and hopefully a great stream as well. You can see all of the teams here. They've just gotten their problem sets and they are furiously opening them and looking through to hopefully find the easiest problem in the problem set. If you're not familiar with how ICPC scoring works, the general gist of it is you're given a set of quite a few problems. We'll see exactly how many in just a second, and the contestants can look through their sets and see exactly how many problems are in the set this year. but usually it's somewhere between like 10 and 15. And the goal of the contest is to write a computer program to solve as many of those problems as you can within a 5-hour window. You got to write a program, and it has to solve not only the cases. Oh, here come the problem sets. Very exciting. Nobody else has information on this. Coaches don't. They're not public yet. Top secret. All right. Yeah, the goal of the problem set is to write code that correctly solves both the sample input and hidden input that only the judges know about to as many of these problems as you can. The more problems you're able to correctly solve, the better you'll place on the scoreboard. And as you can see, we've got all the teams here. And the faster you're able to do that, the better you'll place among the teams that solve exactly that many problems. So obviously, in order to maximize that, they will try and solve the easier problems quicker. As we can see here, it looks like we have M problems. And let's see, is that right? It is true. The last one is Who Watches the Watchman. So it looks like it should be a great set. Obviously, there's quite a variance in skill here. We've got different teams. Some teams have a combined competitive programming experience of about 2 years, and some have been doing this since high school. So there are some teams that definitely know what they're doing, some teams that were able to make it past the regionals into the North American Championships, but aren't necessarily all the way there yet. And we're at the moment, we're just waiting to see the first solve among all of the different teams who are here. Whoever gets the first solve will receive a first solve balloon, and that's a heavily coveted prize. It's a golden balloon, and we'll see it delivered here, hopefully in just a few moments. And I believe there's also some prize money that's given to the first solve for each problem, which we call dark greens because on certain scoreboards they appear a darker shade of green. And dark green is, of course, the darkest of them. Good morning, everybody in chat. I see Constantine and some other people as well. Yeah, we'll have the ticker available for the vast majority of this contest and some other stuff as well. We are 3 minutes into contest. We don't have any solves or even submits yet. You'll see them appear on the left here when we do get some submits, and they should show the verdict as it's pending or once we get it correct as well. Once we have these, we can take a look at whatever problem's being submitted to and see if it's correct. We'll watch the first solve balloon get delivered to that team. During the stream today, we should have quite a few guests. We have the host of the host university. We have a coach from that team, UCF. We also have the dean, Michael Georgiopoulos. And we have quite a few competitive programmers, which you might be familiar with. Hopefully, at the end of this, we'll have Andrew He. He is working on the problem sets as we speak. You can see him here. He's opening everything up. You can see his terminal. Looks like he's reading one of the problems. A little tough for me to tell at the moment. And I wonder if he's aware that the contest has started. It's possible no one has told him. He's on Spodge right now. Do you want to go let him know? Nope. All right, he'll figure it out. He needs the handicap anyway. All right, we're almost 5 minutes in. Still no submits. Oh, is it locked for him still? Is that how it works? He doesn't get a... Yeah, welcome. We got Nick here, a judge.
Hello. It's been a while since we've been on a live stream together, actually.
Yeah. The last one was Pacific Northwest Regional.
Yes. So there is a mirror contest that is provided to the public. If you go to the NAC website, nac.icpc.global, you will look for a little live tab, and if you go there, there will be instructions for how to join the mirror contest. I believe that we intentionally start the mirror late, although I am not part of the systems group that is organizing the mirror. I just know that they intentionally wanted to stagger the starts to make sure that the real contest goes smoothly. There aren't any, first minute hiccups. People can't, log into the judging system, who knows what. So they're going to get the contestants all sorted out and ready. That'll take like 5 to 10 minutes, and then they'll probably spin up the mirror, and then people can probably go on the mirror. So that might be why Andrew is just doing other stuff at the moment.
We do have some comments asking who will be on the stream. Yeah, so we do have quite a few competitive programmers you might recognize. We got Andrew, we've got Nick, of course. We also do have Tourist. He'll be here in a bit, so stay tuned for that. Should be pretty exciting. All right, we are now 6 minutes in. Did you have a guess on how long because you've helped with all of these problems. Did you have a guess for how long you expected it to be before the first problem was solved?
I think I would have guessed that it would have been 5 to 10 minutes into the contest. I don't think there was, we had our first submission actually.
Oh, we got a wrong answer from BYU on problem F. BYU is an interesting school. They have, among their 3 competitors, you're only allowed 3 people on a team, they have completed 6 majors and 5 minors in total. That's an average of 2 majors per person, and I guess a little over 1.5 minors per person. That's because one of their teammates has 4 different majors. Looks like they got a wrong answer. Problem F. How about we take a look at it?
Problem F is Foursquare. Foursquare is indeed one of the easier problems in the contest, and it is one of my candidates for first to solve, actually. I wasn't sure if it would be the first one to be solved, but it's definitely on the easier end. Do you want to go ahead and read the problem?
Yeah, can I read it to the judges?
Go for it.
Or not the judges. The judges already know it. The
Yeah.
coaches watching this live. All right, inspired by a Piet. Oh boy, is that how you say it? Piet?
I
guy's
don't
name?
know. I don't know.
Piet Mondrian painting. You want to make a 4-pane window out of 4 colored rectangles of glass, kind of like the Windows, the old Windows 7 or whatever icon, where it's red primary colors. You're given the sizes of 4 panes of glass. Can you arrange them into a square? You may rotate the panes. The panes should never cover the entire square. Sorry, the panes should cover the entire square without overlap. Oh boy. So there are obviously quite a few ways of doing this. We can talk about what they are here, but like it sounds a little annoying.
We have a second submission from Carnegie Mellon University. They submitted to problem I. However, it looks like their solution was too slow. They got a time limit exceeded verdict. You want to explain what that verdict means?
Yeah, so for each of these problems, not only do you have to write code that's correct, as in it produces the correct output, you also need to do it so that it produces the output in a small enough time window. So for problem F, for instance, this is the first problem that got solved. There's a 4-second time window, which means you have 4 seconds, your code is 4 seconds to run for any possible input in order to get the correct answer. For problem I, it might be a different time limit. But if you don't have an efficient solution, or maybe you do have an efficient solution but you don't implement it well enough, you can get a time limit exceeded verdict. And it looks like this has quite a big input. X can be up to 10 to the 18th. That's like a billion.
Yeah, so problem I is a number theory problem. And in that problem, the input is just a single integer. It can go up to 10 to the 18. The time limit is set to 1 second, but I believe for this problem, all of the solutions that we wrote run in comfortably under 1 second. So we know that, or we have proved that our solutions are fast enough. So this time limit exceeded verdict is legitimate. Oh, but it looks like they just resubmitted and they are the first to solve.
Oh my goodness, first to solve from CMU. Hopefully we'll see the first to solve balloon get delivered here. Should be pretty cool. It's usually a gold balloon. And of course there's a certain amount of glory for getting it as well. We have a bunch of volunteers in a room to the right of the camera here. They've been inflating balloons for quite a while, I'm sure. But obviously there's a lot of secrecy because contestants know which problems map to which balloons. And since the problems are given in a random order, you don't know which problems are easier, which ones are harder. If you tell the contestants, like, we have a lot of this balloon, you can spoil which ones are easier, and you certainly don't want to do that.
Yeah, it looks like problem I has been identified as a problem worth solving. Princeton University has just come in with a solve. They got it correct in 1 try. So do you want to talk a little bit about how wrong submissions affect the ranking of the teams?
Yeah, so as I mentioned earlier, one of your priorities is just getting the most problems correct. After that, you want to get the problems correct as quickly as possible. But in addition to getting them right quickly, you want to get them right with fewer wrong answers. every time you get a wrong answer, that gives you 20 penalty points. So it's as if you solved the problem 20 minutes later than you actually did. And although CMU was the first to solve this problem, Princeton solved it a little bit after, but without any wrong answers. So they may have tested their code more, and that gives them a correct answer on it, and it puts them into first place despite having been the second one to solve it.
Right. So for problem I, we expect that teams will solve this problem relatively quickly. However, there are some edge cases, and the time complexity is something to be careful about. For those who are sort of familiar with programming competitions, we mentioned that the input here is this integer 10 to the 18, a billion. That's a very, very big integer. You can't even count from 1 to 10 to the 18 with a computer in a reasonable amount of time. So these teams will have a challenge figuring out how to solve this problem by skipping a bunch of numbers or doing a bunch of math ahead of time to figure out how to optimize their solution.
It looks like we got 2 more wrong answers on A here, one from University of Virginia, one from McGill University. It looks like neither of them are correct, so it could be A is just more difficult than people think, or it could be there are some tricky edge cases.
Yeah, problem A is an interesting problem. Problem A is also one of the problems that we expect to be on the easier end. We expect to see a lot of wrong submissions and perhaps time limit exceeded. But we'll see. We'll see if teams are able to find their bugs. There are also some edge cases in problem A as well. We see a couple of submissions to problem F incoming from Texas A&M and from Brigham Young University. Their solutions are also incorrect.
Yeah, so BYU, in addition to having a whole bunch of majors between their 3 teammates, 6 majors and 5 minors, they also have a coach which got married 1 week after last year's North American Championship. Unfortunately, the coach wasn't able to join him this year, but it's still a fun story. And we have other marriage stories coming up soon for some other teams too.
Yeah, a lot of interesting events are timed around the NAC for whatever reason. Actually, one thing I found out this morning when I was logging onto Facebook is, Facebook tells you, like, these are all the people's birthdays today. And so one of our judges, Lewin, his birthday is today.
What a small world. Lewin's a huge problem writer too, especially for this sort of region, things Van B helps with.
Yeah, Lewin has been a massive help for NAC or for North American ICPC over the years. He's been helping, I think, as long as I have been, and it's been going on 10 years. And it's great working with him every year. I'm sad he wasn't able to make it out to Florida this year, but wish him a happy birthday. He wrote some good problems for this problem set, so we'll see how the teams tackle his problems.
We have some comments about Richard Pang here. He is present at North American Championships. He helped coach a lot of the teams in the North American Programming Camp, which is certainly a fun pre-contest event. Lots of teams got some coaching on some geometry problems and some other topics as well. And hopefully that'll help some of them solve some of the problems in this set. I saw that M looks like it is some sort of computational geometry problem.
Indeed. So ICPC is pretty well known for having geometry
problems. Sorry to interrupt. We got another AC from San Diego, putting them in second place. Congratulations to University of San Diego.
Yeah. We were talking about computational geometry. So geometry problems are pretty infamous in programming competitions. One of the reasons why is geometry problems are fraught with edge cases. You have points, you're drawing lines for these points and so on. You have to be very careful if you're using floating point numbers. You can have precision errors, and precision errors are very punishing, especially in geometry problems. So problem M is pretty clearly a geometry problem. We'll see how teams tackle it.
And you can see right here the gold first to solve balloon getting delivered to the contest floor. Looks like it's being lowered to the correct height. And ceremoniously, we have lots of people watching. I always wondered if that was a little distracting. I was never the first to solve a problem in one of the contests this big.
I can actually talk a little bit about this.
Sorry, we'll let you talk in just a minute. We got a dark green on K as well, and a dark green on problem F. So that means 3 problems have been solved up to this point.
Yes, problems F, I, and K. These are all problems that are on the easier end. And we, like A, F, I, and K, definitely on the easier half. So we're going to quickly see teams racing to solve all 4 of them as quickly as possible.
University of Toronto with their dark green on K. They, on their way to North American Championships, obviously they flew here. Toronto's quite a distance away and 3 hours different. They accidentally sat next to the University of Waterloo, didn't recognize them, were just next to each other on the plane, and apparently once they were at NAC realized that they happened to be co-competitors.
Wow, imagine that. They also compete in the same regional. They compete in the East Central North America regional, so it's a little... I would wonder if like they would recognize
yeah.
them.
Okay, so it's not a 3-hour time difference. It is. They're just in Canada. All right.
They're all in Canada. There are more submissions coming in. The University of Waterloo has come in to solve problem I. University of Michigan at Ann Arbor has also come in to solve problem I.
And we have a submission from the host university, UCF Beehive, on problem I. It's still being judged.
It's looking like
It's an
correct.
AC. Well done, UCF. Congratulations. That puts them into 6th place, which if they can hold for the rest of these 5 hours will be a bronze medal.
We'll see if they can keep it up.
Yeah, it's always tricky because if you look at your place over time, it'll just naturally decay as other teams solve problems. So being able to hold that place is pretty tricky.
Indeed. Yeah, one thing that will become apparent is teams will be watching the scoreboard, and if you look at the scoreboard right now, I think you'll see like a little column of green solves on problem I, and then you have like the one team that solved problem F, Texas A&M, and then you have Toronto that solved problem K. So the teams that solve problem I are probably going to have people looking at F and K. All the other teams are probably going to be looking at problem I. We know Carnegie Mellon tried problem A, so we'll see if they continue submitting to A or if they maybe switch it up and tackle one of these other problems that's been solved.
NYU has 2 instant wrong answers, both on problem I, which is a bit ironic because their team's name stands for read the fine print. So I guess they weren't reading it quite carefully enough. But hopefully they'll figure out what's going on. It looks like they found at least one bug with that second instant submit, and that's usually only something you see if you submit with debug output or something silly like that.
Yeah, I'm actually, as one of the judges, I can see their verdicts on all of the test cases, and apparently their second submission actually passed more cases than their first. So
they did fix something, yeah, interesting.
They did fix something, but there were definitely still issues there. We have more submissions coming in. Lehigh University is the first to make a submission to problem C, but it looks like that submission is incorrect. Problem C is actually... sorry, I got a little distracted by submission logs. Do you have anything to share about Lehigh?
I do actually. So Lehigh, we might be able to take a look at their contestants right here. Lehigh is seated right next to Lafayette University. And Lehigh and Lafayette, they are, if there are any Americans here, they're huge college football rivals. They're one of the biggest rivals. I think they're the most played rivalry in all of college football. They're seated right next to each other. And both teams reported to me that their goal for this contest is to beat the other. They're right next to each other, and every time a balloon will get delivered, the other team will be able to see right next to them, like 6 feet away. So there's certainly a lot of pressure there, and the fact that they got a wrong answer might be... it was a wrong answer, right?
Yes, it was sadly wrong.
That might be a little bit of a relief to the other team.
Football rivalries carrying over into programming contests. I never thought I'd see the day.
Yeah, it's a very disjoint set of people, but if you're that into it, it's certainly something that's possible.
For sure.
The wrong answer from the dark green team here is looking a little rough because that penalty, it looks rough now, but the fact that they had a little bit of extra time to start working on their second problem might turn into an advantage later on.
Yeah, so we mentioned Richard Pang. He's the Carnegie Mellon University coach. He was talking about how he wants to encourage his team to get to 1AC a problem, 1AC meaning to solve a problem without any wrong submissions. He's actually keeping track of how many 1ACs his team gets because
Is his team Georgia Tech?
He's Carnegie Mellon.
Oh, Carnegie Mellon. All right, all right.
Yeah, because one thing that does happen is if you keep accumulating these wrong submissions, even if you solve the problems quickly, your penalty will be higher because wrong submissions, they add those 20 minutes and they very quickly add up.
So I don't know if this is Richard Peng, you'll have to tell me or not, but one of the Carnegie Mellon coaches knows how to both juggle and ride a unicycle simultaneously.
If you told me Richard could juggle and ride a unicycle, I would be very confused.
It doesn't seem like a Richard thing. He's a very serious person. That's a very clowny move. But certainly they are not clowning around today. Looks like we got another AC also on problem I from UT Austin. We had the statistics for all the problems shown earlier, and you could see it was a really interesting thing to look at, especially for earlier in the contest, because you could see how A looked like just such a trap. There are 4 different teams who have all solved it. They've all gotten it wrong, whereas most of the teams who've submitted to I have gotten it right. But it looks like you got to be really, I is the square one, right?
Yeah, I is the square one.
It looks like you got to be really careful not to miss any of the
Or
cases.
sorry, F is the square one, I is the number theory one.
Ah, the number theory, all right.
Yeah, so...
Should we take a look at what problem I is?
Yeah, feel free to read it out loud.
All right, let's see. So we have some positive integer n. And n is not necessarily huge, but there's another input, which is x, which is huge. And we'll talk about what x is in just a minute. So let f of n be the number of positive integers, the number of positive integer divisors of n. For example, if n is 8, then f of n equals 4, since the divisors of 8 are 1, 2, 4, and 8. Now consider some positive integer x. What is the smallest value of n where n to the power of f of n equals x? Okay, that is a rather complicated thing to see.
You should
Let's
definitely write it
draw
out. If you write it out, it'll be clearer. It's a lot of math.
Yeah, okay, so we have n to the power of f of n equals x.
And to be clear,
X
f
is
of
what
n,
we're looking for.
or x is the integer that you are given. So you are given x.
Yeah, you're given x.
You want to compute the
you wanna
smallest
find, oh, sorry, yeah, you want to find n.
You want to compute the smallest n such that n to the power f of n, where f of n is number of divisors, is equal to x.
Yeah, so let's write this. This is n divisors,
Sure.
like number of n divisors. This is equal to x.
Right. So yeah.
So x can be, this can be massive.
Up to 10 to the 18.
Yeah, so it's a billion, very, very large. And we want to find this. So it looks like this is always possible to do. For instance, if x is a really big prime, you can just do that number. Oh, I guess it would be that number squared, huh?
Yeah, in fact, it is not always possible. We have a sample input where we show that it is not always possible. So it's actually not.
Yeah, so is this number? No, it's not prime.
This number is not prime. This is 2 to the 16.
Okay, interesting.
So the first step is, or I guess one of the steps you need to figure out is it even possible? And so actually, if x is prime, it's never possible.
Because every number is going to have at least 2 divisors.
Yeah, there is an edge case. There's actually an edge case in this problem when x is equal to 1. But aside from that, aside from x equals 1, all integers greater than 1 have at least 2 divisors. So therefore, when x is equal to 1, you have like this is like an edge case that is hard coded in I think all the judge solutions. When x is equal to 1, the answer is n equals 1. Otherwise, you know that x cannot be prime. X has to be like a power of some integer.
Yeah, so x is, I guess, some integer to the number of divisors. And then I suppose it's not too hard to check all of the possible number of divisors.
Correct. So the solution path here is, so let's not focus too much on how to compute the number of divisors so far. Like, let's assume that we knew what the power was. Let's just call the power k. So now we're just trying to solve the equation n to the k is equal to x. So to solve n to the k is equal to x,
Where x is known.
Yeah, where x is known, you take the kth root on both sides. So n to the k equals x is equivalent to saying the nth root of x is equal to n. So now you just have to compute the kth root. The kth root of x. You just have to compute the kth root of x. You know that x has to be an integer. You know that n has to be an integer. So k cannot be that big. In fact, k can be at most. So we can show that when when x is up to 10 to the 18, k can be at most 60. So you can just
2 to the 60
Right.
is.
Yeah. We estimate, we know that like 2 to the 30 is a little bit more than a billion. So 2 to the 60 is going to be a little bit more than a billion. So you just brute force all the values from k equals 2 to k equals 60, and you have to compute this kth root. Computing the kth root, doable, and then you just have to verify for an integer n that the number of divisors is k.
Let's take a quick pause here. University of Waterloo has gotten the dark green on problem A. This is the first solve of all teams on problem A. And we're getting some more solves on problem K here.
Yeah, so Carnegie Mellon and Princeton University have both solved K while we were discussing a little bit about problem I. Waterloo was the first to solve problem A. You will note, if you look at the submissions, both Carnegie Mellon and Princeton both have one incorrect submission on one of the problems they have solved. Waterloo so far has no incorrect submissions, and that is why Waterloo is in first place at the moment.
No incorrects and a dark green. That's always something your coach will be proud of.
Yep, indeed. So yeah, problem A is definitely on the easier side of the problem set. There are edge cases, but Waterloo was able to catch all of them and actually solve the problem. It looks like UCLA has just solved problem G.
Waterloo would like you all to know that they have more geese per square kilometer, not per square mile, per square kilometer, than University of Washington. In case that was unclear, they have won the rivalry.
I have just looked at, I was peeking at Waterloo's solution to problem A, and they have the super short, like 3-line-ish solution. So problem A can be solved in like 3 lines if you know what you're doing.
Well, let's talk about what the problem is, why don't we?
Yeah.
Because I'm sure people are certainly interested in that. Problem A. Oh, long statement. Statement's definitely longer than 3 lines. Allergen testing. So you have a 1 minute or 1 second time limit. 1 minute. Ooh, 1 second time limit. You're in a chemistry class and you're working with some compounds, exactly one of which you're allergic to. You have a fixed number of days to figure out which compound it is, which one you're allergic to, that is. You set up a number of sites on your arm for testing. Each day, you want to do the following exactly once. So the first thing you do is apply each compound to some possibly empty subset of sites on your arm. And you can apply more than one compound to the same site. And then after that, you'll wait and see which sites demonstrate an allergic reaction. So if you're allergic to any of the ones on that site, then you'll demonstrate the reaction for that site. Yeah, that's what I just said. And then if a site demonstrates an allergic reaction, it cannot be used on future days. So I guess it's permanently allergic.
Yeah.
And you want to know the minimum number of sites you'll need on your arm to guarantee that you can determine exactly which compound you're allergic to within the given number of days. Of note, both the number of days and the number of compounds can be very, very large. Although I don't think the number of sites you'll need will necessarily be too large.
Mm-hmm. Yeah, so in the problem, the number of compounds and the number of days can both be up to 10 to the 18. But you can actually show, sort of similarly to problem I actually, that the answer, or that like, so here the number of sites you'll need is at most 60 for vaguely similar reasons actually to problem I.
Same thing of 2 to the power of 60 is bigger than 10 to the 18.
Yeah.
Which is of course what we're looking for.
Yeah, I want to backtrack a little bit to highlight some of the changes to the scoreboard. So UCLA has the dark green on problem G.
Oh, congratulations.
Yeah, do you have any fun facts about UCLA to share?
I do. Let's see. UCLA. Oh, maybe I don't. Have they not submitted theirs? I do have one about Purdue, though. Purdue just got an AC as well.
Purdue actually solved 2 problems in the same minute. They solved problem I and problem K, both at the 27 minute
Holy
mark.
cow. So they have flown up into 5th place, passing UCF, our host university, and quite a few others.
Mm-hmm.
Purdue has 3 members on their team, as most do. One of them is Caroni, who is probably quite well known within the Code Forces community. This is his 4th NAC, he claims. Although, I think this is only the 3rd one ever, right?
It is actually, this is the 4th NAC. NAC started in 2020.
At Georgia Tech?
At Georgia Tech. So he competed in 2020 in person. I met him there. He competed in the online NAC 2 years ago in 2021.
Ah, the online one.
Yeah.
That's what I'm forgetting.
Then there's last year was at UCF on site, and then this year. So this is his fourth one.
And I bet I would place money on the fact that he will be the last person in history to ever have competed in every NAC.
Yeah.
It's a tough thing to do, and he's qualified already in 2 of the past ones. But because of some COVID shenanigans, he's able to compete and qualify in the 3rd. We also have 2 other members of Purdue, one of which is an anime drawer, and the other one is a drummer. So quite a diverse set of skills there.
That is indeed a very diverse set of skills.
We also have quite a few more ACs, I guess, on problems I and A. MIT finally on the board with problem A.
Yeah, MIT is a perennial favorite at NAC, so it's actually a little bit. I'm actually a little bit surprised that their first AC has come in at minute 30.
Yeah, if you had made me guess, I definitely would have expected MIT to be performing better than they are now. It looks like Harvard's also gotten a wrong answer with no ACs yet on problem A. Another somewhat favorite at NAC.
Yeah.
Possibly underperforming this year.
Well, I will remark that a lot of the easy problems do have edge cases, sort of just by virtue of the fact that a lot of the small cases require special handling that doesn't quite fall under the purview of the general analysis.
And as the comments have said, Colin is back at the University of Maryland. This is Galen Colin, or Colin Galen, as his official name is. He has a YouTube channel. It's wonderful. You should all go subscribe. And he's now in 5th place, helping the University of Maryland. He's a 2nd year this year. He's got 2 teammates as well. And yeah, they're now doing quite well in bronze medal territory.
Yeah, I have a little bit of a soft spot for the University of Maryland. So I attended high school in Maryland. I competed so the University of Maryland ran a high school programming contest, which I competed in back in the day. That contest.
Really? I had no idea.
Yeah, they have a contest. So the local high schools compete in it. The 2 big shots are Montgomery Blair and Thomas Jefferson High School for Science and Technology. One of my proudest achievements is when I was in 11th grade, I competed against these 2 schools and actually was able to beat one of them. That is something that no one expected, because they always take like ranks 1 and 2. So everyone was very shocked when that happened.
So although MIT may have been a little slow to the start, they've just gotten a dark green on problem C. First solve on problem C, and that may have been what they started out working on. Maybe their start was a little bad because they picked the wrong problems, but it looks like if they're able to get a problem nobody else has worked on, that does give them some sort of advantage, which hopefully will last for longer into the contest as other teams start to go for C.
Indeed. So looking at the scoreboard right now, it looks like there are solves to 6 unique problems. Problems A, C, F, G, I, and K. And we're only at the 35-minute mark. So within 35 minutes, we've had 6 unique problems be solved.
We also have a third wrong answer, unfortunately, from BYU on problem F. They're working hard, but they haven't been able to get it yet.
Yeah, I'm looking at sort of like their logs for this problem. It looks like they are getting slightly more and more test cases as they make submissions, but they haven't yet gotten all the test cases. So it makes me think that they're trying to. This was the 4-square problem. It seems like they're trying to identify all the ways to break a square into 4 different rectangles, and there are quite a lot. So it's very easy to miss one if you take that approach.
We also have a second version of this, which is obviously not everyone who sees the problem. Oh, man. CMU, all right. CMU just got the 3rd problem. Problem G has already been solved, but it's still impressive. That puts them into 1st place. Congratulations to CMU with their juggling coach.
Yeah, I'm going to need a demonstration. I'm going to need to ask the CMU folks.
I'd like to see a video of this.
Oh, yes. We need a video. I'm sure we need to get a video of this, because people in the ICPC, they have all sorts of talents. Like, it's like programming contest is already a pretty niche activity, and so as a result, the people who do it, they have lots of other niche activities that they're like really good at.
So we have all of these contestants competing, but also simultaneously we have Andrew He competing over here. He has started the mirror recently. It looks like now he's working on problem K. Do we know how many problems he's gotten right? Would we be able to check that? Looks like he doesn't have any yet. So he's starting on problem K, which I think has a solve, right?
Problem K has several solves. Problem K is currently, I think, the second most solves. I'm trying to see if I can get a view on the statistics here. I'm sure it exists somewhere. Oh, here we go. Statistics and analysis. Let me see. Okay. So on problem K, there are 7 teams. So 7 teams have solved problem K at the moment, compared to problem I has 16. Problem A has 4 solves. Problems F and G have 2, and then problem C has 1. So those are the stats right at the moment. So Andrew working on problem K, that makes sense. K is a little bit of a math implementation simulation sort of problem, so he should knock that out real quick.
It looks like he's a little frustrated, or maybe he started typing something and it was incorrect. Now he's pacing around trying to figure out what's going on. It should be noted Andrew is in a secret undisclosed location, and he is far away from the contestants. He's not allowed to see this stream, and he's competing as part of a series of contests against University of Japan, or I guess Japan, not University of Japan, just Japan. Different contestants from Japan.
Yeah, so there is a contest series that is run by a group of individuals based out of China. This series of events is called the Universal Cup. And so Universal Cup has been running all of the like Chinese regional contests and a lot of the sort of top tier ICPC contests from around the world. So this coming weekend, they will be using the NAC problems as one of their stages. We have a lot of people here on site who do Universal Cup, and we don't want to tell them like, you know, you have to wait. Like they would have to really like disappear for the entire day and not interact with anyone if they don't want to be spoiled. So we've given everyone in Universal Cup permission to use their mirror participation as sort of their official one, and then we'll merge in the results for them.
Looks like we have some more first ACs here. We got Northwestern with their first correct submission, moving them up into 19th place. They are all integrated science majors. No computer science majors on Northwestern's team. But I guess integrated science is close enough. Certainly, it's useful to be able to program in lots of different domains. So having that skill is very useful. All right, we'll go back to Andrew here. It looks like did he get K correct? A. He got A correct? Oh, wow.
So
okay.
So Andrew was competing with his teammates. One of his teammates is not here.
Kevin's son, yeah.
Kevin's son, K-Sun48 for those looking for handles. Kevin is not here in Florida, so Andrew and Kevin are together on a call somewhere. And so Kevin probably did problem A while Andrew has been reading problem K, you know. They can't solve the problem with their starting letter in their first name.
Let's go back to the contest floor. We got quite a few new submissions. Again, one from Madison. They just got a wrong answer earlier, but they're trying to get problem I. And this time they get it with an AC. So congratulations to Wisconsin-Madison.
Yeah, we should be seeing the scoreboard sort of fill up now. I think it's been identified which problems are the easiest. So problems I and K, teams are likely to be tackling first. And then we're going to probably see them branch out a little bit. So we see a lot of wrong attempts on problem A. So teams will start to pick up that there are probably some edge cases, and indeed there are. So they're going to need to be careful on problem A. Similarly on problem F, like a lot of teams some teams have tried it. Very few teams have solved it correctly on the first try, and I know, so at this event actually, so the North American Championship also runs a programming camp in parallel. And so they have these special trainers, some of which are like former competitors, current coaches, other alumni. They talk about these various strategies. And so one of their sessions was on reading the scoreboard. So you look at the scoreboard carefully and you see, oh, these teams, they're not solving it on their first try. They're solving it on their second or third, or teams just aren't even getting it. So in that case, you know, they have to be careful. They're going to teams that are later on looking, they're going to say, okay, this problem looks like it has edge cases. They're going to try to be more careful. So maybe we'll see more teams get it right on their first try. Or maybe not, because, there were a lot of edge cases.
It's possible that if someone gets something wrong, or a bunch of people get something wrong, that they're just doing something stupid and you'll do it right. But it's always worth taking an extra second to consider, is there any way this could be wrong if everybody else is getting it right, or getting it wrong?
I just want to call out, Purdue is the second university to get the 3 problems solved. They just solved problem C.
Unfortunately, we got a wrong answer from De Anza University. They are the only community college here. They are a 2-year college, which is especially interesting because one of the things you need in order to get good at competitive programming is to participate in it over a series of a couple years. And they really only have like 6 months of training before their students move on to a different university. So the fact that they were able to make it here and have a team is really impressive and something that not any team can just do. We had another submit from U Central Florida on problem A, a wrong answer. Earlier they had runtime errored. It's possible that they were just trying to fix their runtime error, or maybe they're trying to gather information about the test cases or just the nature of the mathematics there. We're not quite sure, but yeah, hopefully they're learning something from these wrong answers and runtime errors, because they are causing penalty, and if problem A is going to matter, the penalty is going to add up over time.
Yeah, it looks like this team has, so they submitted a program in Python, and it looks...
UCF?
Yeah, UCF, and it looks like they're trying...
Wait, in Python?
Yeah, they submitted problem A in Python. Actually...
That's odd.
Well,
I mean, I guess for big integers.
So problem A, actually, the easiest way to solve it is to use Python. There's a risk of integer overflow, so I expect teams to be trying to do it in Python. I think specifically for this problem, though, like what they're doing is they do an exponentiation, and so the first thing they do is they'll compute like 2 to the power of d, and d can go up to 10 to the 18. So they're trying to compute the integer 2 to the power of 10 to the 18. That's a massive number. Python's not going to like that. So that's why we got a runtime error.
There is a very nice exponentiation in Python. You can just do ***. You'll have integer safety. But as of recently, Python started handling exponentiation differently.
It wasn't exponentiation. So Python, they have a thing where if you have a string, if you read in a string of length 1,000,000 and you try to pass it into int, it will just crash and be like, nope, I don't want to do this.
There's a very contentious change to the Python language, which lots of people, especially on Codeforces, had opinions on. Doesn't necessarily make sense, but I guess if it fixes production bugs and saves people a bunch of money in the real world, it might turn out to be worth it.
Yeah, it's always interesting when languages introduce changes, and these changes might have like very severe ramifications for people in the programming contest community. Fortunately for this problem, like our simple 3-line Python solution, it works. It doesn't have any issues. It's provably fast and correct. So we know that there's no risk. It happens that the formula that the UCF team is using is incorrect. You never have to compute 2 to the billion.
We just got Georgia Tech's first AC on problem I. Their fun fact is in training, I believe, they take a 1-hour break before starting any contest. And I think that's a really reasonable thing to do, especially if you look at like this contest or any world finals. These teams have been sitting in a contest area without their phones, without access to their coaches, just alone, I guess, with the other teams. But when you're in a situation like that, your nerves really start to build up, and it can get really stressful. And if you lose all your adrenaline before the contest starts, you're going to get worn out at the 2-3 hour mark in the contest, and there's going to be 2 hours left. The other teams are going to be catching up to you, and you're just going to be out of energy. So that's really not something you can afford. So practicing that break and getting used to those nerves is a good thing.
Yeah, time management is a really big part of these programming competitions, knowing where you are in the contest and what you should be doing. At different points of the contest, you'll be doing different things. Is it time to talk about the N+1 strategy, or is that something you want to talk about a little bit later?
That's a good idea. Well,
there are a lot of solves.
Let's talk about it later.
Yeah, there are a lot of solves, but we can talk about it in a little bit.
It looks like, I guess, maybe there's just a very nice curve this year. A very convenient curve where there are a lot of easy problems teams can go after. or if it is a rough curve, we certainly haven't hit the wall yet.
Yeah, so it is interesting to note. So we have solved 6 problems in it was
And
6 problems.
Deonzo with their first submit. Well done. Sorry, go ahead.
Nice. So yeah, we saw that there were 6 problems have been solved. And I think the only other problem that has been attempted is problem D by Northwestern. I'm looking at the statistics here. Yeah, it looks like problem D is the only other problem that's been attempted that hasn't been solved yet. So teams are likely to be focusing on these first 6. And so what we're probably going to see is I suspect we won't see a team solve a problem outside of these 6 for a little bit.
There's a lot of stuff to work on, so maybe it's just it's like an early 90-minute mark. We also have the first AC from Rice. They have 2 proud anime lovers on their team and 1 embarrassed anime lover on their team. So 2.5 anime lovers from Rice. It's always good to see them, and it's good to see them on the scoreboard as well.
Yeah, I wonder if they'll ever have a competitive programming anime. I know there were some jokes about that. I know someone was making like anime likenesses of competitive programming celebrities. I'm sure there's like there's an anime version of Gennady somewhere, and I'm sure that other.
I think there's one of me too.
Yeah,
in that post. Yeah.
Yeah, I'm waiting for someone to just make an anime about programming contests. I don't know if I could watch that. I feel like it would just be. It'd be a little bit too painful to watch virtual contestants getting wrong answers in the contest.
Despite this being a massive number of college students, there's probably a bigger overlap between anime fans and football fans in this group, which is interesting at the very least. We also have the very first AC from Emory University. One of the members of that team, Rudy, held the most upvoted comment of all time on Code Forces. It has been beaten by Monogon since then, but it used to be the most upvoted time. It was on a post where Mike was releasing stickers, and he suggested the sticker, "Is it rated?" about Code Forces contests. That's always kind of fun. They also have 3 different majors. They have 1 pre-med, 1 math, and 1 biology major. Biology, chemistry, I think. And one of them has written a thesis on ICPC practice methods. So quite an interesting team over there, Emory University. Hopefully their practice will pay off, and they'll be able to get some more problems later on in the contest.
All right. I want to quickly call out Brigham Young University. They are the 3rd team to solve 3 problems, having just solved problem I.
They were having a rough start earlier today, but it looks like they have gotten some traction, and they're finally catching up with their ACs.
Yeah, it was good for them to solve problem F. One thing that you see happen a lot in ICPC scoreboards is you'll see a team, they have a wrong submission on a problem, and then they have another wrong submission, and the next thing you know, they have like 30 wrong submissions, and you're wondering, you feel bad for the poor person at the keyboard who like can't figure out how to fix their final bugs to get that problem solved.
Especially in something this stressful. Taken just out of 2nd place, I guess now they're in 3rd place. University of San Diego has gotten the dark green on problem L. San Diego has a world champion at Go on their team. In addition to being one of the 3rd best teams in North America at the moment, he has a world champion in Go. This is the fast method. He was born in China, and he played the Chinese rules of Go. Then now he's in the United States, and in the U.S. we play, my understanding is the Japanese counting version of Go, so it's a different way of scoring, but it's similar strategy. Usually it only matters in about 1% of the games. And yeah, he's doing very well today. Their team is also named after a local building in San Diego. Of course, they're San Diego University, so that's very good to see. They're dropping quick though. Now they're in 4th place.
Yeah, I mean, teams are going to be very quickly solving 3. MIT just solved problem I. University of Maryland solved problem F. I'm actually a little bit surprised that problem L is the 7th problem solved. In my predictions for difficulty, I thought this problem would be one of the last ones to get solved. It's a hard one, and I think that a lot of teams are, the way that they're going to solve it is they're going to write, they're going to do one of these techniques where they write a slow program, and they're going to look for patterns in like the problem, and then they're going to try to guess the pattern. But whoever solved it here, they clearly didn't do that. They just derived the formulas just without needing to look at small cases by hand.
We can see all the different balloons here being given out to different teams. There is a quite a similarity in balloon color between all of the different problems that have solved. They all tend to be like a bluish green, which is maybe a bit unfortunate by the random balloon selector, but sometimes it is like that, and maybe we'll get some interesting like pinks, reds, yellows later on with the harder problems.
Yeah. I always wondered how they selected the balloon colors. I tried asking in the operations room, and they were like, apparently, like, they don't have equal numbers of all of them. So whichever ones they just have the more colors of, like, they ask, because if you only have like 10 of like one balloon, you don't want to have the easiest problem being that balloon. You want like one of the harder problems to be that one, so you don't run out of balloons.
You also definitely don't want the easiest problem to be black. You want the black balloon to be something special. So, in my opinion, otherwise it's just kind of, it lowers the rareness of it.
All right, I'm looking here at the scoreboard. Stanford University coming in with a solution to problem A. It puts them at 6th place, right at the medal threshold.
And Harvard is really turning things around. It looks like they've just gotten their 3rd AC. They had a very rough start, but yeah, up into 8th place themselves.
Yeah, so as mentioned before, like the easy problems have mostly been identified. So I would say that A, C, F, G, I, and K are definitely sort of the easy half in a manner of speaking, and then the other 7 problems are on the harder half. So we'll see how things shape up. UCSD being the only team to have solved the problem outside of that set, we'll see if they're at an advantage because they've solved problem L so quickly, or we'll see if they can maintain their position.
We see Andrew He here. He's competing alongside these teams. He has a teammate, Kevin Sun, who's working with him, and it looks like Andrew's working on problem G. I don't recall having seen any submits to problem G.
There were two. I think there were two ACs on problem G. So
okay.
UCLA has the dark green at the 26-minute mark. Carnegie Mellon at the 34-minute mark. Actually, Toronto just solved problem G.
Okay.
So yeah. Problem G is a data structures problem, and for those who don't know, Andrew is a data structures master, so I think I would expect him to get this problem really quickly.
It looks like he's still thinking about the best way of implementing it, pacing around, but
yeah.
he should be able to come up with the idea pretty quickly.
Yeah, problem G is interesting. Like I was looking at some of the judge solutions after the fact, and some of them were like, oh, data structures, I'm going to throw a segment tree at it. You don't need a segment tree to do it, but it's funny to see it in the solutions.
We don't yet know exactly how many teams will advance to World Finals from this set. It's usually safe to assume that at least the medaling teams will advance, but there may be more who advance, there may not be. I think it depends largely on the scoreboard distribution. The problem is like if 7 teams solve the problem, and they might just add one more slot for that team that makes the problem threshold. But of course, that's up to the contest organizers, which we'll hear from later on. We got Texas A&M solving a problem here. Congratulations to them. They have one of their members. Let's see if I can pronounce his name. I think it's Dhruv P. He types over 100 words per minute, which is kind of impressive, right? I'm sure there are lots of other competitive programmers who do. He does that with 2 fingers.
That's insane. I cannot. I actually have a friend from my undergrad years who also does he calls it the hunt and peck, and he goes with 2 fingers. It is insane watching him type. Like I don't know how he does it. Like my fingers would be so worn out doing that.
Sometimes you gotta follow the rules, but I guess if it works for you, you can just do whatever you feel like if you're that fast.
Yeah, we're seeing a lot of teams fill out at 3 problems. There are now 11 teams. I want to highlight Texas A&M. They are in 5th place. They solved problem K at the 52-minute mark.
And it looks like we just got an AC from Colorado School of Mines. Fun fact about them, their name is Kentucky Fan Club. Kentucky's team name is also CSM, Colorado School of Mines Fan Club. So they were different teams. They met each other over a training camp, I believe, or maybe at the last World Finals. They became friends, and then they decided to name their team names after the other university. Quite fun. They also have one of their teammates who is graduating with a petroleum engineering degree. as and he'll start working as a petroleum engineer shortly after this. I guess if the Colorado School of Mines is interested in mining, maybe that's something related to that. Certainly a field where, if you're successful, I bet you can make a lot of money.
Indeed, indeed. It's really nice to see the camaraderie. Like, when I first saw it, I was like, this is a typo? Like, did these teams intentionally, like, plant this? Like, I've never, like, there's this whole meme around, like, fan clubs. I'm very guilty of this. I frequently compete in team contests as Kusaga fan club, and I know that there are other peoples who make fan clubs around all sorts of competitive programming figures. So it's really great to see, these two teams are
Kusaga is, of course, a legendary grandmaster from South Korea, right?
Yes, Kusaga's from South Korea. He's inspired me to spend thousands of hours solving problems. Big shout out to him. If it wasn't for him, I probably would have retired from problem solving a long time ago. But
I believe he's actually coached or at least somewhat helped at previous North American programming champs, right? Camps.
He assisted in the 2021 programming camp. He helped find some problems for us. I don't know if he was actively a trainer, but I know he helped source problems for that instance of the camp.
We've got another submit from Lafayette here. Would we be able to see a comparison between Lafayette and Lehigh?
Let me see. I think I can do that. So Lafayette right now is currently ranked 17. They have solved 2 problems, and they have 107 penalty minutes. Meanwhile, Lehigh University is not yet on the board. They have made 1 submission to problem C, but that is it. So currently Lafayette is in the lead by 2 problems, but it's a 5-hour contest. There's a lot of time there. Things can change very quickly. We saw Purdue, they solved 2 problems in the same minute. So there's plenty of time for Lehigh to come up and solve problems. So, don't count them out yet.
Yeah, there's certainly another 4 hours of contest left. So anything can happen in this amount of time. We saw even teams with some rough starts have been able to quickly climb to 3 problems.
Yeah.
The most common being I, K, and A so far.
Yeah, for sure. No team has made it to 4 problems yet, which I am a little bit surprised by. I would have expected at the hour. Actually, we have 2 minutes until the hour, but I would have guessed. I actually predicted that the top team would have 5 problems solved by the first hour. So I understand it's a high stress situation. Teams want to take it slow and steady, but in the past, like, we had MIT breezing through the problem set, so I was always like, you know what, I'm sure some team will get to 5 really quickly, but we'll see if any teams get to 4. It looks like CMU.
We also got the first AC from University of Pennsylvania. They have an interesting team warm-up activity. They all 3 of the teammates will have a half scoop of workout, like powerlifting, pre-workout supplements before contests. This is something they've done in regionals, and it's something that they told me as of yesterday they were planning on doing for this contest today.
Oh my.
And in addition to University of Pennsylvania's first AC, University of South California, I think, SoCal? USC. They also got their first AC, and they are an unusually old university for college students. Their average team age is nearly 23 years old, which is how old I am. So they're only 1 month shy of that on average, which is, I guess, relatively old for undergraduates, I think, right?
Well, okay, so in ICPC, there are rules on the age. So I don't remember exactly what the age requirement is. I want to say it's like 25 or 26. We're having someone look it up for us right now. There is an additional, there are like a lot of restrictions. So one is like, you have to be an undergrad. You can't have done more than like 5 full years of post-secondary education. You must be like a full-time or a part-time student. You can't be like on leave and then do ICPC or something like that. So, most of these teams, a lot of these teams, they're gonna like, the younger teams will be like all freshmen or maybe freshmen and sophomores, but like the most experienced teams that you could ever have would be like 3 first-year grad students, for example.
We have the official rules from one of our helpers here. Uh, it appears if you first began post-secondary studies after 2018, then you're eligible. If you didn't do that, but you were born in 1999 or later, then you're eligible, which would make you, what,
24.
24? So, yeah, they're coming up close to... And if not, if you have competed, or if you have completed more than the equivalent of 8 semesters of full-time STEM study as of August 1st, if you've completed more than that, then you're ineligible. Otherwise, you are eligible, I believe.
So I guess, if you don't go to college until you're like 50, like you could be the oldest person doing ICPC, but that's definitely something.
Can we take a look at the scoreboard for all the teams here? We just got information about Andrew He. So yeah, it looks like the winning team on site has 3 problems.
Problems.
Carnegie Mellon. They've got a wrong answer on A, or 2 wrong answers on A, but maybe they can figure that out soon. But as of right now, they have 3 problems. If we take a look at Andrew here, his team, which is him and Kevin's son, they've got 4 at the moment, with an AC on A 6 minutes in, an AC on F, an AC on I, and an AC on K. They've gotten all of those right with just 1 submit, and they have a wrong answer on C as well.
Okay.
So
yeah.
they'd be winning if they were competing against the contestants. Obviously, they have far more experience than any of the contestants here. They've been competing longer than probably many of the teams' experience combined, but they are still quite good.
For sure. If USA 1 was losing, USA 1 is the team name for Andrew and Kevin. If they were not beating the official teams right now, I would be shocked. Like they are fast and they are good.
But they do have a handicap, which is they didn't get the problems until a solid 10-15 minutes after the teams did. So they've only had 75% of the times the team had. And yeah, we've got Andrew working on problem G here. I guess one interesting thing that I would like to know from him, which you might just know coincidentally, are they limiting themselves to using 1 computer at a time?
So this has always been like up for debate. Like how do these teams do ICPC contests where you're not in the same place? And so it's generally agreed. So a lot of these things are like on the honor code, but you can usually tell when a team is cheating and they're using multiple keyboards in parallel because their submission times will look very strange. But the convention that Andrew and Kevin are adopting, so they're on a voice call right now. Like they're going to be on a voice call. They're communicating with each other, and so they will ask for the keyboard. So what will happen is there will be someone who is like on keyboard. So right now, like Andrew was on the keyboard. So Kevin is not on the keyboard. So Andrew's going to type his problem, and then he's going to submit it or whatever, and then he's going to tell Kevin, okay, you have the board now. And so now Kevin will be allowed to start writing code and solving problems.
San Diego has just broken the 4-problem barrier with an AC on problem G. So congratulations to them. Well done.
Yeah, UCSD is going to be at a big advantage. They solve problem L really quickly, and I still maintain that problem L is one of the harder problems. I think it's probably in the top quarter in terms of difficulty. So they might be at a really big advantage having solved problem L so early.
Nick helped prepare quite a few solution videos. So we're going to take a look at the solution video to problem I here. This is currently the most solved problem in the set.
Hi, my name is Nick, and I'm here to present the solution to problem I, power of divisors. Define tau of x to be the number of positive integer divisors of x. Given an integer n, compute the smallest positive integer x such that x to the power tau of x is equal to n, or report that no such integer exists. N can be very large, going up to 10 to the 18. Note that in order for tau of x to be valid, n must be a perfect tau of x power. Therefore, we can brute force over all possible values of tau of x. Tau of x can therefore be at most 60, so all we need to do then is check if the implied value of x has exactly tau of x divisors. So for some candidate value of tau of x, we can compute the matching value of x by binary searching for it, being careful to avoid overflow, and then finally, to compute tau of x, we can simply use naive trial division. There is one edge case when n equals 1, because in this case, tau of x is equal to 1, and this is the only integer where tau of x is not greater than or equal to 2.
All right, thank you for that. We are back to watching the teams. U San Diego has claimed their lead here with 4 problems. It looks like they're doing quite well, but it's a little tricky because now they have revealed to everyone problem L is solvable, so some other teams might jump on a problem L.
Yeah, problem L is still hard though. So I think teams will look at it, and I think if the teams are paying attention to the camp, they might look at this problem. They might think, oh, this person has probably seen something very similar. I have no idea how to approach it. And hopefully, if they've been paying attention, they'll just ignore it. One of the important things to note is that just because a team solves a problem doesn't mean the problem is easy. It just means that team knows how to solve that problem. Everyone knows UCSD is a very strong team. So hopefully, if teams are like, I hope that teams are like aware of that, and so they'll think like, oh, you know, I don't want to spend more time on problem L.
Go ahead. I didn't mean to interrupt there.
Okay, yeah, no worries. So it has been established at this point that other problems are definitely more accessible than problem L. So for example, problem A has 7 teams that have solved it. Problem C has 2 solves. F has 9 solves. G has 5. So, you know, problem L is definitely solvable, and the top teams might look at problem L, but I would expect more teams to get around to that once they've solved more problems.
Do you mind if we pause for a minute and talk perhaps about problem K? Because it looks like that's getting quite a few solved, and we haven't even looked at it yet.
Sure, go for it.
Ooh, all right. Looks like, real quick, we have Galen Collin popping into first place with another ACNG. That gives us 2 problems, or two teams breaking the 4-problem barrier, which, for the record, I believe is currently on par with USA 1. All right, let's pause there. We'll leave them for a minute. We're going to talk about problem K here. This is space alignment. You're collaborating with a few other programmers on a coding project. To your horror, you discover that some of the people have been using tabs to indent code, while other people have been using spaces to indent code within the same file. Apparently, these people didn't notice there was anything amiss when they did so. You wish to replace the tabs with spaces so that the file has consistent indenting. Consistent indenting means that for every line at the nesting depth k is greater than 0, the first non-white space character in the line should be preceded by exactly k times I spaces, where I is greater than 0. Is it possible to replace tabs with a fixed number of spaces to have consistent indenting? So yeah, looks like you're given some lines of code, up to 100 lines of code, and what does the input look like? You're given some tabs and some spaces and some text.
Yes.
I guess just open and closing curly braces to make
Right.
things
So what's happening here is you're given the tabs and spaces before, or at the very beginning of the line, and then you're told whether the character at the end is an opening brace or a closing brace. So for those who are not familiar with indentation, there's this convention that some languages actually enforce it, like Python does. But what happens is at each indentation level, you want the number of spaces to increase by maybe 4 or 8, depending on your company's policies or your personal preferences. And so you have spaces, but you also have tabs. So in this problem, you want to replace all of the tabs with the same number of spaces.
So in this case, let's say you have some nesting brackets that look something like this.
Mm-hmm.
So here, every opening bracket needs a closing curly bracket. Is that guaranteed in the input section?
Yes, it is guaranteed it is balanced. Otherwise, this problem
Doesn't really make sense.
Ill-defined. Yeah.
And you're given some spaces and tabs for each line.
Mm-hmm.
And you want to see, can we replace every tab with some number of spaces so that we get a pretty indentation? Everything that's the same number of nests in has the same number of spaces.
Yes.
So in this case, if we replaced each thing with each tab with 2 spaces, then we would have 2 here, right? We have 1 plus 1. Here we'd have 1 plus 2 plus 1. Here we'd have 2 plus 2, and here we'd have 2. So these two are both indented by 2, and these two are both indented by 4, and that would
Yes.
look pretty.
Yes, that and in this test case, the answer would be 2 because you have replaced each tab with 2 spaces.
It's possible there are multiple answers, right? If that's the case, what should you do?
So the problem specifies, it says the smallest number. So for example, a very simple case might be you have like an opening brace, tab, opening brace, tab, closing brace, close. And here you can set t to be anything. You can set it to 1, you can set it to like 1,000 or 1,000,000 or whatever. But because 1 works, and 1 is the smallest positive integer, t would be 1, or the answer would be 1.
Exactly. So it seems like we have a bunch of requirements here for, I guess, equality. But how long can each line be? Is it pretty short?
1,000 characters.
So we have at most like 1,000 spaces and 1,000 tabs per
line.
or it's 999, something like that. Interesting. So what if we brute forced the length of a tab? Could we just check to see if it works? Is that possible? That would
Yes.
be about 10 to the 8th runtime total, worst case.
You wouldn't
Probably quite a bit
generate
less.
you wouldn't generate the like 1,000 spaces for each one, but like you would count it, and that's the intended solution. The intended solution is to brute force.
Oh,
the
yeah. So
number.
there are only 100 lines, and each one's only 1,000. So it's only 100,000, not a million length.
Yes, exactly.
Yeah. So this is a very doable problem.
Yeah,
I would say.
this problem was one of my predictions for first to solve. It wasn't the first to solve. It was solved 6 minutes later, but I think the reason why I expected this problem to be solved more is because this problem doesn't actually require you to have like algorithmic or like any like specific like algorithmic knowledge or anything like super special. It's a pretty regular like brute force sort of problem. So I expect that I would hope that all teams are able to solve this problem, though it'll take a while. Notably, so let's go back to the scoreboard for a bit. There have actually been some exciting updates since we started presenting K.
It looks like University of Toronto has gotten 2 more submissions. Is that right?
Yeah, they solved problem A at the 67-minute mark, and then they solved problem F immediately after, so they're at 5 now.
That puts them into first place, and they know pretty much what to work on next. It looks like C is definitely the next thing for them to work on.
They will be working on C. They probably have someone looking at L now because UCSD has shown that problem L is solvable, and Toronto will have to start solving the harder problems.
And yeah, that's quite good. This is, of course, the Waterloo neighbors, and they are certainly outperforming Waterloo, as we see here.
We'll see if they can keep it up. Waterloo are heavy favorites in the NAC. Having talked to a lot of coaches and contestants, a lot of them are saying Waterloo's going to win because they have a legendary grandmaster, and there were no other legendary grandmasters at the contest. So
We have some comments cheering on Never Give Up. He's on the Waterloo team, and apparently, yeah, there are some people who know him.
Yeah, Waterloo is currently Waterloo and MIT, interestingly, are the 2 highest ranked teams that have not yet solved problem K, which we were just discussing. And I mentioned like problem K is just a brute force problem, so we'll see how long it takes them to figure out that hey, it's just brute force. You don't have to do anything special.
If you don't read it, it does look a little scary. Like maybe there can be a bunch of lines of code that aren't parentheses or something like that. But the input section does make the problem much easier. They put significant restraints on it, and it makes it quite doable.
Yeah. Talking a little bit about sort of like the medal teams in contention. So we see that Purdue is also at 4 problems now. They solved problem F. So now there are 5 teams with 4 problems solved. I'm looking at the scoreboard coming down, so just to give the relative ranks for problems solved. So we have 1 team with 5 problems solved, that's Toronto. We have 4 teams that have solved 4 problems. If you go down to rank 12, if you've solved at least 3 problems, you're in the top 12. If you've solved 2 problems, you're in the top 29, so that's over. So the median rank right now requires 2 problems to be solved, and 46 teams have solved 1 problem. So 46 out of the 51 teams have solved at least 1 problem, so we only have 5 teams left before we've hit that mythical every team has solved a problem benchmark.
And with that, I think we'll take a look at the solution video to problem A. So here you go.
Hi, my name is Nick, and I'm here to present the solution to problem A, allergen testing. In this problem, you are allergic to exactly one of n compounds. You have case sites where you can apply compounds. You repeat the following process d times. For each compound, you will apply it to some of the sites, potentially 0. After you have applied all of the compounds, you will observe which sites have an allergic reaction. Given that each site can only be observed on one day, and a site cannot be used if an allergic reaction is observed there, compute the minimum number of sites you'll need to discover which of the compounds you are allergic to. In this problem, both the number of compounds and the number of times you repeat this process can be very large, up to 10 to the 18. So one of the first things that we can do here is we can observe that the number of sites you'll need, even in the worst case, will be very small. We can actually show that the number of sites will be at most 60. That happens when you have exactly one day and 10 to the 18 compounds to distinguish between. In this situation, we can use a binary construction to try to determine which compound we're allergic to by interpreting each compound's number as a binary number and then using that to determine the sites that we apply that compound to. Since we know that the answer is going to be relatively small, if we can quickly check for a fixed number of sites, if we can differentiate among n different compounds, we can either do a linear scan or a binary search to compute the minimum possible value. So now we just have to ask ourselves, given d times to repeat this process and k sites, how many compounds can we differentiate? With some investigation, we'll eventually show that if there are d rounds of the process and k sites, then the number of compounds we can differentiate among is d plus 1 to the kth power. We can prove this with induction. The primary thing to note in the induction hypothesis is the fourth bullet point on this slide. So under this assumption, if we have k sites and d rounds, if we have x sites that we specifically care about, then we know that we can apply at most d to the x compounds to those sites by the induction hypothesis. This gives us as a sum that by the binomial theorem completes the induction hypothesis. So this problem reduces to computing a minimum possible integer k such that d plus 1 to the kth power is greater than or equal to n. There is one potential trap in this problem, which is that when n equals 1, the answer is 0, because in that case, you don't need any sites, since you know that you are allergic to exactly that compound.
Okay, so I'm stepping out.
Here we go, we're live. All right, good morning and welcome back. We have the resolver here, or not the resolver, the scoreboard. What's it called? The overlay. That's the official name. And we'll take a look at which teams are doing what. Let's take a look at problem F. It looks like there are quite a few solves on that. It's a pretty implementation heavy problem, and we'll look at all the ways to do it. So problem F, we mentioned this earlier. This is the 4-square problem. You're given 4 rectangles, and you want to know how many ways are there of rotating them to get a perfect square. Let's draw all the ways. What do you say? So we can consider the case where you have like squares yourself. Obviously something like the Windows logo comes to mind, and here you have a perfect square. But maybe that's a bit redundant. So because these are all rectangles themselves, so this would be solvable quite a few other ways instead. So instead, if we have some big square, one option is we can do 1 square here, we can do 1 square here, and then we can have 2 squares in a row like this. I guess we can have 1 big square, and then we can have 2 squares that meet at a corner. And I guess this kind of shows us a general case, right? Anytime we can split this line perfectly, then we'll have 2 versions of this, where this height is equal to this height, and this width is equal to the height as well. What else? I guess you're always going to have a perfect line here, right? There's always going to be one thing, so either you'll have 1 square on the edge and the other 3 on one side, or you'll have 2 and 2. Of course, this is rotationally symmetric since it's a square, so you can always consider the line being vertical. And you'll always have one thing on the left or three things on the left, and it's also symmetric via a flip, so we should be good there. And that might be all. All right, we will take a look at the solution video and see if we're good there. And next on, we'll have the contest director, Tony, to come say hi to us.
Hi, my name is Nick, and I'll be presenting the solution to problem F, 4 square. In this problem, you are given 4 rectangles, and you are asked to determine if they can be combined to form a square without any empty gaps or overlaps. In this problem, the width and the height of each of the 4 rectangles is at most 1,000. To start out in tackling this problem, we can first determine if it's even possible to assemble a square with a valid side length, such that the sum of the areas of the rectangle matches the area of the square. So if the sum of the areas is not a perfect square, then the answer has to be no. Otherwise, we have a candidate square length, and so now we can just brute force all possible tilings of the square to see if any of them result in the desired decomposition. When implementing this, one observation that teams might find helpful is that you can always draw a line through the square such that for any given rectangle, the rectangle is on one side of the line.
Welcome back. We have contest director Tony here. Thank you for joining us. I appreciate it.
Thank you for inviting me.
So I wanted to talk about a couple things here. The first is that all of the massive amount of work that's gone into making a contest like this possible. We can take a look at everything that's going on here. All of these stations had to be set up. We have, probably 51 computers here just on the contest floor, plus quite a few more.
That's right.
Quite a few more out there. We have different workstations. There are lunches that need to be brought to these contestants. All of these desks, these are things that don't normally exist in this room. I've been in this room in other times. All of the black curtains, they're all gone.
That's right.
We have our own custom tech here. All of this is supported by volunteers, right?
That's correct. There are hundreds of people who work on this contest throughout the year. And we, as you say, it's a huge undertaking, and we have groups that take care of things like systems, the stuff in the back that you don't see where the judges are working, and they set up all of they make all the tech work. The operations group, they're the ones who make sure that the contest floor is all set up. The systems group is John Clevenger. I'm sure most of your listeners know that name. He works at the World Finals as well. He works technical at the World Finals.
He was the first one on the stream, as a matter of fact. Today.
Was he?
Yeah,
Was he? Well,
yeah.
he's the man. He makes all the magic happen in the back room. That's for sure. The operations folks, they set up the floor, as you pointed out, the pipe and drape, the tables and chairs, the signs, the lunches, all of that stuff that has to happen. Tom Capal takes leadership in that area. And then there's some other things. You're looking at the floor, but there's a whole lot of other pieces to this involving events, for example. Events it sounds like, oh, okay, so somebody's going to stand up and make a speech, but actually that's ceremonies. And the events people take care of things like hotels, food, transportation, branding, signage, and the big event, which is registration. So all of the students who just went through registration over at the Celeste know that that's quite an undertaking in its own right, getting all of that organized.
Making sure you have hotel rooms for all of these people, that everything works out as you'd expect. It's a huge undertaking. Even if you get to just some of the small details, like what logos are allowed to be near other people. There's all of these things that you got to know, and it's very tricky. It's things you wouldn't even consider when you're watching a stream like this or even attending the event. But someone has put hours and hours, maybe days, weeks of effort into learning all of the minutia of all of these big companies, and they're all very generous financial supporters of us, but making sure that they're happy, they're satisfied, and that they can get the best reach to our talented students that they can.
Exactly right, and they work so hard. What a dedicated group. To me personally, I think the greatest joy in life is solving problems with smart people. It doesn't get any better than that for me. And this is a group of incredibly talented, incredibly smart, incredibly dedicated people. And so you put a challenge in front of them, and they're going to not only do it, but they're going to do it beautifully, and they're going to worry about all the end cases. I think most of the people on my team were programming team member. I was on the programming team, for example, and we all worry about those edge cases, right? So detailed-oriented people are just such a joy to work with. People who worry whether or not the schedules will fit into the badge holders and all of the little details.
And you would be surprised at like how well the skills from ICPC translate into these other seemingly unrelated aspects. We saw earlier one of the teams who was in first place before. I'm not sure if they still are. They were a champion Go player. So that's just like unrelated. You got to spend time programming and doing Go. That's very separate things. But the problem-solving skill and the thinking ahead and the game theory, certainly there's some aspect there. Rutgers College also has the highest rated, I'm going to mispronounce this, Megumin, which is an MMORPG character. Their college is the highest rated one in existence. So that's kind of fun. Apparently this is a sorcerer. I don't play it, but it means a lot to them apparently. And there are quite a few other things that people are doing that aren't even related to competitive programming. Stony Brook University, they have one of their teammates is helping to implement Tetris with the blocks that fall down.
Oh.
But not just like the normal Tetris, they're implementing it in Conway's Game of Life. This is the thing with the dots, where the dots turn on and off. For people who aren't familiar with this is about as difficult. I mean, I'm sure they're using computer programs to do it, but this is about as difficult as simulating Minecraft with dominoes. That's like what we're talking about here. This is Conway's Game of Life is not a computer by any sort. It's nothing like that. And still, these competitive programmers are able to figure out how to do it.
I'm always blown away by the abilities that we see at this contest. Even at the regional level. I mean, clearly these are the folks who stood out at the regionals, but I'm always amazed at the things that I see at the regional levels as well. We have so many talented people participating in this contest at every level, and I just wish I could get all of them here.
And some very talented volunteers as well. Do you have anything you would like to say to some people who might be watching who maybe could volunteer, or if we have competitive programmers in the audience, could help judge in the future?
I would very much like to ask people in the audience, we get involved. That's my big message, get involved. There are so many places that you can contribute. If you're interested in being a coach, we can hook you up with a school that's looking for a coach. We can hook you up with an experienced coach to mentor you. We have materials that have been prepared that will help you get started as a coach. If coaching isn't your thing, but you love writing difficult, interesting problems, we could use problem setters. If you only have one idea for a really good problem, we want to hear about it. It could be just the greatest problem in the problem set the next year. And if you want to be a judge, if you're interested in being a judge, contact us. When I say we, who is we? Well, if you have if you know who the regional contest director is where you live, that's a good place to start. If you don't know who that is, you can always send an email to nacmanager@icpc.com, or .global rather.
NAC?
NAC. NAC Manager is a good place to start. We read that on a regular basis, and we'll happily connect you up, however it is that you would like to participate.
Absolutely. I know from experience in some of the contests I've done, setting hard problems is a very difficult thing to do.
It is.
And you need to come up with, to get a really good problem, you need to come up with a unique idea. You can't just reuse problems that contestants may have seen, because that's a huge advantage if you've already seen the problem.
Right.
So all of these problems, just like any other regional contest, and certainly like any World Finals contest, the problems are all unique, they're all very original, they're different from other ones in fundamentally how they work. They're not just the same problem with different names, or maybe like in a math textbook, you the same problem a bunch of times, but just different numbers, and you do it differently, but it's all the same. They're completely different. They use never before seen techniques, and coming up with them requires some insight, some genius that if you're able to provide, we'd be very thankful for.
Well, and I think once you start writing problems, and I'm sure this is true for you because I know you write problems, then you get into the mindset as you're going about your daily life, you see something and you think, that might make an interesting contest problem. We were somewhere recently where our hotel number had an interesting property to it, and we began exploring what would it take to find the next such number that would have that property. And just so once you get the mindset that you're looking for interesting problems, whatever it is you're doing in your daily life, you may just find, oh, hey, that could turn into a nice problem.
Matt Fontaine, who's one of the judges for Southeast Regional, he has the famous quote, there are two different types of problems. There are problems where people thought of the problem and then figured out the solution, and there are problems where people knew a solution they wanted and they figured out how to make it into a problem.
Exactly.
And a lot of times people will really prefer the first type, where there's just some natural thing that lots of people figure out. The interesting thing with that, though, is of course you have to be a good enough problem solver to be able to see that there is a solution.
That's true.
Because sometimes it just seems like, oh, this is so hard, we'll never be able to do it, and then you just give up on it. And a lot of things end up being NP complete, and that's always
Well, that
a
is true. A lot
disappointment.
of things do turn out to be NP complete.
All right, I want to thank you so much, Tony, for spending some time with us.
Well, thank you for inviting me.
And yeah, I wish you best of luck. Hopefully nothing starts on fire.
Oh, it's gone
and we'll all
very,
be all
very
right.
smoothly this year. Nothing has gone wrong this year, and I hate to even say that, but so far everything's just gone perfectly. And once again, I invite folks who are interested in getting involved. We are a big family. It's a labor of love. It is a lot of work, but it's also a lot of fun. And if you'd like to be part of that, we'd love to hear from you.
All right, with that, I think we'll take a look at the solution video to problem K. Here we go.
Hi, my name is Nick, and I'm here to present the solution to problem K, space alignment. In this problem, you're given a file of n lines of code, and you wish to replace every tab with exactly k spaces. The resulting file must have consistent indentation, so if a line of code is nested inside p pairs of braces, there must be exactly p times I spaces that precede the first non-white space character in the line. I must be the same over all lines. We wish to compute the smallest possible value of k, such that this is possible, otherwise report is impossible. There can be at most 100 lines of code, and each line has at most 1,000 tabs or spaces. If there exists some valid solution, then we can show that the minimal such solution must have k being less than or equal to 1,000. So what we can do is we can just check each value of k from 1 to 1,000 and validate that the file has consistent indentation. We'll print the first value of k that works, otherwise we'll print -1. There are some edge cases here. So one thing to be careful about is that it is not necessarily the case that the first opening brace is matched by the last closing brace, so you might have to scan the entire file to find a line that has spaces and tabs. Note that it is also possible to solve this problem algebraically without needing to brute force all possible values of k. This solution is faster, but it does have some casework, so you have to be careful not to miss one of the cases.
Welcome back. We have some breaking news. MIT has solved, or has submitted to 2 more problems. We'll try and get a scoreboard up here overlay in front of the contestants, and we can take a look. Let's see. MIT looks like they've got 5 problems now, and Purdue has 6. I can't believe I missed that, but that is that's incredible. So it looks like Purdue has solved all of the problems that have been solved, and they're the only team to have done that. Everybody else has their work cut out for them. I guess that's not true. Problem L. Nobody has problem L except for the dark green team. UT Dallas has a incorrect submission on it, but they're certainly trying. As far as MIT goes, their team members are from 3 different countries. MIT is obviously a fan favorite. They had Ben Q recently. They're the home of Andrew He here, and also of Kevin's son. They competed in MIT. You can see they're in USA 1, competing as we talk here. They AC'd on problem B and also on G. This current year's MIT, just recently. So congratulations to them. Their team members are from 3 different countries, and despite being from 3 different countries, they all ended up being in the same fraternity, which is called the Taxi. So there you go. You can take a look at each of them as well as their coach. We also have an AC from Iowa State University. That's always good to see. On problem I, they're catching up. Problem I is a fan favorite. Problem F seems to be very approachable, and so does problem K. Looks like we got another submission on problem K from NEU, and that's an AC. Waterloo has 5. They're looking to get 6, and they just got it. Problem F. I think that means they are tied with Purdue for problem solved. putting them into first place by penalty, only by 4 minutes. So it's incredibly close. Waterloo has the dark green on problem A, which is an advantage for them, and they don't have the wrong answer on problem C that Purdue does. So that gives them a bit of an advantage. Of course, there's also one additional wrong answer from each team, which makes it very close. We've got Waterloo here, the fan favorite, with Never Give Up on the right of the screen from Waterloo. And their coach in the middle right. We also have Purdue here with the exact same set of problems. Purdue home to Caroni, one of Monaghan's close friends, and also some others, as we've talked about before. Northwestern with a wrong answer on problem F, and De Anza with a wrong answer on problem A. Quite a few submits flowing in. I guess part of the fact that there is a relatively large problem set this year and a comparatively easy difficulty curve is the fact that you're welcome to join, Nick, whenever you'd like.
All right, I'll come back in.
All right. Is the fact that you'll get lots of submits early on in contest. I remember in previous years, sometimes we don't have them flowing in quite as fast. Certainly in World Finals in the beginning, there was a dearth of submissions and then quite a few wrong answers instantly. But we got quite a few ACs here. How about we take a look at what Andrew's doing? Do we have stats on his scoreboard? Looks like we can see. If we zoom in, he's got 6 ACs.
It's got 6.
C, G.
It's A, C, F, G, I, K. I just look at the top.
Oh, yeah, okay. With wrong answers on C, but that doesn't matter. Yeah, so Andrew figured out the data structures, solved it, well done. And it looks like case on, maybe Andrew's debugging something?
Maybe. We'll see.
Do we have the file name? It's B. He's looking
Yeah,
at B.
B is probably next that they would do. It's like a 100-line graph theory problem.
I see some tree code here. There's lowest common ancestor coming up.
Yeah, problem B.
And some sort of range minimum query. So that's a data structure as well.
Yeah, problem B is called a tree and 2 edges.
Do we want to take a look at it?
I actually was thinking maybe we talk about we're 90 minutes in. I wonder if we should talk about the N+1 strategy.
Let's do that. All right, let's also take a look at the scoreboard here.
Yeah, okay. We definitely need to pull out the scoreboard so that we can more easily discuss what we have coined the N+1 strategy.
Lydia, can we get the scoreboard when we get a chance?
All right, so this is the N+1 strategy. So at the 90-minute mark, let's just say we're at the 90-minute mark here. What we're gonna do is we're gonna screenshot the scoreboard and we're gonna list out all of the problems that have been solved so far. So let's just use right now. So there have been, I think it's 9.
So B just got solved and so did L.
Yeah, so I think there are 8 problems. There are 8 problems that have been solved. So the problems are A, B, C, F, G, I, K, and L. So in the N+1 strategy, if you want to medal, you must solve all 8 of these problems by the end of the contest. But that's not sufficient.
We consider the problems that have been solved by the 90-minute mark easy to medium. And then there's an additional set of hard problems, which probably no team is able to solve all of in a general contest unless you have some really outstanding team. So these are all of the easy and medium questions. And yeah, in order to medal, the prevailing knowledge is not only do you have to solve all of these easy and medium problems, you also need to get the +1, that one more problem that's one of the hard problems. So at 90 minutes, all of the teams now know which of the problems are easy or medium and which of the ones are hard. And they know if they're going to try and medal, they need to get all of those easy to medium problems and also one of the hard ones.
Right. So by this strategy, we would say that a team needs to solve 9 problems in order to get a bronze medal. It turns out that the +1, if you wanted to ask like how many problems do you need to get a silver medal or a gold medal, you just go up. So in order to get a bronze medal, you need N+1. In order to get a silver medal, you need N+2. And in order to get a gold medal, you will need N+3.
To be very clear, this is not actually how medals are determined. This is just a heuristic that estimates them. Determining medals is obviously decided at the end of the contest based on the ranks of the teams, not by what was solved 90 minutes in. So this is all just how contests over time tend to look.
Yeah. So we'll see how the heuristic pans out. 11 problems is necessary or sufficient to win, and if 9 problems is actually the threshold for getting a bronze medal. Of course, the other threshold that actually most teams here will likely care about is the threshold for qualifying for the World Finals. There was some chat earlier about how many teams are qualifying to the World Finals from NAC, and that information is not known yet. Like, we don't actually know. It's going to depend on the scoreboard. There is a real effort to have the threshold just be number of problems solved. So let's say 20 teams solve 7 problems. They might just say all teams that solve 7 problems make it to World Finals. But sometimes the scoreboard doesn't cooperate, and you have an awkward gap where, like, I think the year we talk about is 2021, where like 3 teams solved 7 problems, and then like 35 teams solved 6, and they had to put the tiebreak somewhere in the 6 problem range.
We've recently seen a wrong answer from Stanford here. Stanford has a 5-year age gap between 2 of their contestants, which is certainly possible. I guess you're allowed to compete if you're no longer in undergraduate school, and you're allowed to compete if you're a freshman, if you know what you're doing.
Yeah. I graduated from Stanford, so the Stanford coach and the Stanford team has been talking to me a little bit. They've been trying to pull information from me about the problems, but
unsuccessfully, I hope.
Yeah, I've been telling everyone, you need at least there were at least 0 problems on the problem set, that sort of thing. I've offered at least 0 problems, all that good stuff. But yeah, Stanford is. I always have a soft spot for Stanford. It's my alma mater, so we'll see if they are able to climb the ranks. They're currently in 8th place. They've solved 4 problems with 236 penalty minutes. So they have a wrong submission on problem F. So if they get that, they'll put themselves into bronze medal position. So we'll see if they can get it.
And speaking of your alma mater, my alma mater, UCF, just solved problem K. That gives them 2 problems, which is a little bit behind where they expect to be, I imagine. That's 29th place overall in a field of 51 teams. So hopefully they'll be able to get some more things. I bet they're working on those for sure now as well.
Mm-hmm. Yeah, I'm looking at the bottom of the scoreboard. There was some discussion in the judges' room. They were wondering when all teams were going to be able to solve a problem. Right now, it looks like it's just Lehigh University and the University of Kentucky. They both are still without problems solved. Lehigh has not yet made a submission since trying to solve problem C. The University of Kentucky, they have made submissions to problems A and K, which we know are 2 of the easier problems, so we'll see how close they are.
University of Kentucky is, of course, the Colorado School of Mines fan club. They have some favorite animes that they would like us to read. Do you know how to pronounce any of these? Obviously, there's One Piece.
That one. So the second one is Hunter x Hunter, and I do not know what the first one is. That
it's like Hayoka or something.
Yeah, Hayoka is my best guess, but I am not very knowledgeable about anime, so I cannot provide pronunciation.
They have told me, and like we mentioned earlier, there's a massive anime fan club here. They have been watching them and also other teams. I think Purdue as well was watching anime before their contests, and they watched it before they had their phones taken away, of course. And they also were watching it during dinner 3 days ago, inviting other people to come watch with them.
During the dress rehearsal, these teams sent in clarification requests, and I asked the judges if they could, if we would watch anime with them. I decided to throw in one of their clarification requests into ChatGPT, and I pasted the output back at them. And then afterwards, they asked me, they were like, "Did you send our clarification request to ChatGPT?" And I kind of winked at them and didn't say anything.
All of the answers to questions asked during the practice ceremony were listed. Unfortunately, I guess that one got missed because it was too long. Would have taken up too much time.
We did mention, actually, it was mentioned that there was a ChatGPT answer embedded, and that definitely got a lot of laughter out of the contestants.
Washington University from St. Louis just got a wrong answer on problem I. They would like you to know they are not from Seattle. That is the University of Washington, completely unrelated. They are from St. Louis in Missouri.
I would never have guessed that. What's that St. Louis doing there?
I
What's
don't
that
know.
Washington
Maybe that's
doing
the
there?
team name. Maybe University of Washington, they named their team St. Louis. That would be really funny, wouldn't it?
Indeed. Looking Lehigh with their first
Lehigh with their
AC.
first submit. Well done. Well done. These are rivals, of course. We also have University of Alberta with their second AC. Interestingly, most of the teams here probably use C++ in their submissions. University of Alberta, when they started programming and started competitive programming, none of their team members used C++. They used Java, like me, also Python, and also C. Those were their 3 languages they started with, and since then they have all converted to C++. I'm still a Java for life main, but yeah, there you go. And looks like it's paying off for them. They're getting problems right with it.
Yeah. I will say that I thought I would be using Java in programming contests for life, but in 2018, I finally joined the
bit the
dark
bullet?
side.
Yeah.
I joined the dark side. Now I write most of my judge solutions in C++, and this actually causes us a headache because Lewin is the only judge I think that writes in Java. And he's switched to Python, so we actually don't have any judges that have Java as their preferred language. And by policy, all problems must be solvable in C++ and Java, which means that there must be a Java solution that passes within the time limit. So someone has to bite the bullet and solve these problems in Java.
Carleton has just gotten their second AC on problem K, moving up to 37th place overall. They only have 2 teammates, and they don't even have a coach. They do, however, have flip-flops. Those will cheer them on, and they're a huge flip-flop fan.
Are the flip-flops their mascot?
I don't know. You know, UCF has a mascot. All of the UCF teams this year are named after Minecraft blocks. And the team that's competing, the NAC team, hopefully World Finals team, we'll see. Fingers crossed. They are UCF Beehive. So they're named after that. They do have a plush bee that they've brought onto the contest. It's on their desk. So that's theirs, but yeah, I don't know of any I think they're wearing them, to be honest. But honestly, I don't know. Maybe it's a little cold for that.
I wonder how many teams their team strategy is we're gonna wear Crocs and then we're just gonna be proud Croc wearing competitive programmers, and that's how they're gonna.
Do you think it's more than one team?
I'm sure there's more than one team that's wearing Crocs. We'll have to investigate after the contest.
Berkeley AC's on problem L. Congratulations to them. One of their teammates, Lynn Paz, he doesn't know how to use structs in C++, despite being a USACO camper. So I guess he just really likes writing things himself, just does everything in the main method and in their own functions, and it winds up being fine.
I will admit, I don't think I know how to use structs in C++.
They're pretty simple. They're very similar to classes in Java, so
Yeah.
they're not too difficult. But yeah, I guess if you like putting everything in arrays, it certainly works. All right, with that, we're going to take a look at the solution video to problem L. Oh, we got a black balloon being delivered. Look at that. I don't know which one that is. We'll take a solution video, or look at the solution video to problem L, after which we'll have Dean Georgiopoulos come visit.
Hi, my name is Nick, and I'm here to present the solution to problem L, splitting pairs. In this problem, Alice and Bob are playing a variant of NIM. Given n piles of stones, the current player will pick at most half of them and remove them. Then they'll pick k other piles each with at least 2 stones, and then split them into 2 non-empty piles. The player who cannot move loses. Determine who wins given optimal play. In this problem, there are at most 50 piles, and each pile contains at most 1 trillion stones. We can make some observations. So for example, the only losing configuration is when all piles have exactly 1 stone. When n is even, we can do some case analysis and see that a state seems to be winning if and only if at least 1 pile has an even number of stones. When n is odd, it gets more complicated. But if we divide all values by the largest power of 2 that divides all of them, then we seem to run into something similar, where the state is losing if and only if all piles have an odd number of stones after the reduction. It turns out that these are necessary and sufficient conditions. We'll quickly go over the proofs for why this is the case. In the even end case, if all piles have an odd number of stones, then it's impossible to only have odd stones after one move. But if there are an even number of stones in some pile, then there are some constructions based on how many piles have that. In the odd end case, we have something similar, where if there is some power of 2 such that all of the piles are divisible by that power of 2, but then some of them are divisible by the power of 2 larger, we can use the same logic to do some splitting to get into the losing state.
Welcome back. We have the Dean of Engineering, right?
And computer science.
Engineering and computer science, absolutely. The most important part here. Dean Georgiopoulos, welcome. Thank you so much for joining us today.
Thank you for having me. Appreciate it.
So this is the second consecutive year even, that the ICPC North American Championship has been held at UCF.
Correct.
Do you want to talk a little bit about how that happened and how UCF made that possible?
Yes. As far as I'm concerned, this is one of the areas that we are excelling in engineering and computer science. We have a very strong number of students who come to our engineering and computer science college because they want to do their academics in computing, either computer science or IT or computer engineering. And as you probably know, or maybe not know, we have the UCF programming team for a number of years. I think they have been around for more than 30 years. So to me, this is one of the obvious places that we can hold the North America competition, because we have had a long history with the UCF programming team, a great history with the UCF programming team. So I think it's a great opportunity for us to showcase not only the UCF talent around the US and Canada, but also around the globe, but also the talent of a lot of other universities in the US and Canada. So.
I'm a UCF student myself, and I have to admit, the reason that I came to UCF was because of the programming team, and it is really a fantastic experience. It gives the students of the programming lots of opportunities to interact with each other. Obviously, they end up being very successful, and many of them go work at big tech companies. Some of them join their own startups, create their own startups. StatSig is a recent one created mainly by UCF graduates. And it's great to see what they're able to do, and it really unlocks opportunities if you compete. And even if you don't make the team the first year, you can join it later. You can keep practicing and get better.
Absolutely. I think when I think of the UCF programming team, I don't always think of the 3 students who compete in the North America Championship or the World Finals, but I'm thinking of the 50 students that train on a regular basis. They train once a week on Saturdays for 12 hours to become better programmers, and not only programmers, but also understand how algorithmics work and solve real problems. And to me, that's a great opportunity for these students, but also students that they get connected with, because I do believe that the peer interaction also helps other students understand what they need to do to be successful during their academics at UCF, and of course in their future professional careers. So.
Yeah, not only is there this team of 3 UCF Beehive, but of course there are quite a few other UCF teams. They help compete with them. They help keep them on their toes, and obviously people naturally learn different things from each other, right?
Absolutely.
Some things are easier for some people, some are easier for others. And when you have other friends to help explain it to you, and professors who help coach and everything like that, it turns into a well-oiled machine where we are being very successful.
Absolutely. I think these students, as well as their coaches, are changing the culture at UCF in terms of what you need to do to be successful and how you can be a better professional upon graduation. So.
Do you want to talk a little bit about why NAC is so important that it exists in the first place?
Absolutely. In my mind, the vision is NAC gives an opportunity to obviously US and Canada, but also the entire globe to know the importance of the computing talent. You know, as you know, there are a lot of disciplines in engineering and computer science. You know, computer science is one, IT, computer engineering, but there are other disciplines: mechanical, aerospace, civil and environmental, construction, industrial. They all need computing talent. And a lot of companies that they hire, they come to us and they want to hire our students, whether they are mechanical engineers, aerospace engineers. They need people who understand programming and they know how to do well in computing. So to me, it's a much bigger goal that this particular NAC is is fulfilling by showcasing the importance of the computing talent, but at the same time give the opportunity for students around the US and Canada as well as the globe to understand the importance of computing in our everyday life and in our future lives as well. So in my mind, the vision for this NAC is to serve as the springboard of bringing in thousands of students, hundreds of companies in the same place, and say, okay, this is what we want to do. We are going to meet some great computing talent. We are going to hire this computing talent as interns and future professionals in our company. And at the same time, the students to see the opportunities that are there for them if they are good in computing.
Absolutely. Well, thank you so much for joining us. We're going to hear from one of those companies looking to snatch up some students here. And then after that, we'll be right back.
Wonderful. Thank you for the opportunity. That's it?
Yeah, 1 second.
I always felt that being kind of one-trick pony is not really how you want to go through life. In high school, I started taking computer classes, and I was like, wow, this is the thing to do. I don't know what else I'm possibly doing in my life. It's all about exact sciences, really. They're really tangible. You connect with things that you can see, you can experience, that actually make a really big difference by the time it's done. Technology is very enabling that way. Just building things and solving business problems is really gratifying. But most importantly, you really connect with the thing that you're solving. I love the markets. Every computation problem is represented in the field of finance. I think that challenge of generating profits from the markets is probably one of the hardest things in the world. And we're good at it. The things we solve are not necessarily exact in nature. How you build a world out of these things is very different from the exactness of a simple equation. Your imagination is projected. That's kind of artful, and it's really fulfilling too. As the saying goes, it's worth doing because it is hard. And the beauty of being here is that I look at things that are impossible, and they get me excited because I know it's an opportunity. My colleagues possess that wherewithal and self-awareness and the experience to be able to solve what needs to be solved. Knowing I have a team I can really rely upon, that is an honor. It's facing challenges. It's accomplishing things, driving things, succeeding at things. I don't know where else I'd be doing this. The future is here. I don't think it's anywhere else.
Jumping back to the contest, we have USA 1. Andrew just walked away from his computer. I guess Kevin is typing right now, and Andrew is thinking about problem H, it seems. They're doing quite well. I guess they have B correct. Is that true? I don't have the scoreboard link, but yeah, they're doing quite well. Let's take a look at problem H. It has, I don't think, any attempts even. So it's a hard problem for sure. Maybe he's going back to L. Well, we're gonna look at H nevertheless. Let's take a look. Might end up being an unsolved problem, huh? Problem H is game show elimination. It has a relatively large time limit, 8 seconds, and a 2 GB memory limit. So we're expecting something a bit tricky, but let's take a look. You're running an elimination style game show where players are eliminated one at a time until only one remains. Based on what you know about the contestants, you're trying to predict the results. Each week, the remaining contestants take part in a competition, where each contestant's score is based on their skill level. Because this is a silly game show, a contestant's score is a random number that falls within their unique skill range. The contestants are then ranked from highest to lowest based on their scores. Since scores are all real numbers, there is 0 probability that there is a tie, which makes sense. The winner of this week's competition chooses who will be eliminated that week. All players believe they should pick whoever did the best after them in this week's competition, so they always choose to eliminate the second place contestant. That contestant is eliminated and goes home. The show continues week after week until there's only one contestant left. The contestants' final ranks are based on when they left the competition. The last contestant to leave is the winner, who's rank 1. The second to last is rank 2, and so on, until the first person to leave gets the lowest rank. So you're given information about contestants' skill level, and you want to compute the expected ranks of each players. So the bounds here are you have n players, where n goes up to 1,000, and k determines the skill range of the contestant. I wonder what that means. So your skill... Yeah, so what is the skill range? Contestants are numbered from 1 to n. The skill range of the ith contestant, whoa, that's weird, is from I to I plus K inclusive? Does that make any sense? What?
It just means that
So like the lower bounds are all different for every skill range?
no so each problem or each person has a skill level, and then they just have a range on their skills. So the range is always I to I plus K. So they're just all like uniformly like in order.
Well, wait, but they're all so the first contestant has a skill range that starts at I. One, and the next one starts at 2, and the next
Yeah.
one starts at 3. So that's a pretty significant constraint to the start of the skill ranges. Or I mean, maybe it doesn't matter at the end of the day when you've got a bunch of math going on, but
Yeah, it's a uniform, or the skill ranges are uniformly increasing at the rate of like 1 per contestant, and this structure is important to the solution to the problem.
it is?
Well, it's important because so the first observation that you make is that person I plus K, or let's say person X plus K will never lose to
I
person
guess
X.
importantly, K only goes up to 10, right? So the best person's skill level is a number between 1 and 11, worst case, which means the 11th person will always have a bigger skill level.
Yeah, so actually K being small is also critical to how you end up solving this problem.
It seems like you're interested at some particular point in the mask of the next 10 people who haven't been eliminated. So if there are like 10 people after you, the subset of them that haven't been eliminated is important. So it seems like a 2 to the 10 is going to be somewhere in the runtime here. You also have n different people, and you probably need the probability of each of the possible states. I don't know exactly how you'd implement it from there, but
So
that's something.
As a general meta note, the judges unanimously agree that problem H is the hardest problem in the set.
It seems very tricky. We can move on from it from now. I thought Andrew may have been working on it, but I guess he's on to bigger and better things, or I guess smaller and easier things.
Let's take I'm going to take a quick look at recent submissions to see what has been going on. It looks like Rutgers just solved problem K, and the University of Minnesota Twin Cities has solved problem F. I'm pulling up the scoreboard. So I missed out on a little bit, but it looks like both the University of Waterloo and Purdue University are both at 6. And they're only 4 penalty minutes apart. Very close. That is fewer than 1 wrong submission difference.
In first and second place, wow. Yeah, they've been 4 minutes apart for a while now. I think with the same set of problems even.
Yeah. I guess we have just crossed the 2-hour mark. So the University of Waterloo, they haven't. I guess the University of Waterloo is trying problem D. Actually, the judges were looking at problem D, and I believe it is a timeout. I'm taking a quick look. No, it's wrong answer. But we think their code would also time out. So we'll have to see if they can figure it out. D we think is either the second or third hardest problem in the set.
Yeah, interestingly, MIT just got another wrong answer on problem K. It seems like something they should be able to do.
Yeah, I'm pulling up their problem K right now. It looks like problem K, they're passing some of the test cases, but they're definitely failing some of them. I'm gonna quickly peek at their code. Their code looks pretty reasonable. Actually, there's a lot of cases. There are a lot of cases in their code. There's a lot of casework. I think they're doing too much casework actually, because you just have to brute force the values from 1 to 1,000. But they have a bunch of checks before they enter the brute force section of their code.
Interesting. Okay, yeah. So if you have any one of those wrong, then you're going to end up with an incorrect solution somewhere.
Purdue solving problem B, first to 7.
Putting them into first place, yeah, with 7 problems. Wow, congratulations. I think maybe one other team had solved problem B?
MIT has solved problem B, so Purdue is the second team to have solved problem B.
But the first one with 7 problems.
Yes, so Purdue was first to 7, so now they are in the lead. If Waterloo solves a solves any of the other problems besides D on their first try, they'll take the lead back. But probably they're probably focusing on problem D, but maybe they have someone looking at B, someone looking at L.
MIT is also in a bit of a pickle at the moment because they don't have F. They've got a wrong answer on K, and they don't have L either. So there are a lot of problems. They only have 5 problems. They're not doing great for penalty on 5, and they're a little short on it. So yeah, they've got some catching up to do at the moment.
Yeah, but if they solve F and they solve K, they'll be at 7.
It's an exciting scoreboard for sure. We're going to take a look at a JetBrains sponsored video here, and we will be right back. Welcome back. We have an exciting contest underway with Purdue in first place, Waterloo in second, Georgia Tech in third, and Toronto in fourth for now, though they are likely to be pushed back as soon as another team solves the 6th problem. We have an announcement from the judges. Obviously, we are a pretty good distance away from the contest floor at the moment. We don't want anything we say here, any potential solution information, to be leaked to the contestants. But the judges tell us that a balloon has just popped on the contest floor. This is an idea that has come up in many problems, this idea of intentionally popping balloons in order to try and distract other contestants. Obviously, it breaks your focus, and if you're coding something that's important and difficult, it can be a real tricky thing to keep working through. Harvard, just doing exactly what I predicted earlier, pushing some team out of 4th place. They now have an AC on problem C. For how weak of a start they have really been coming back. One of their team members is Maxwell Zen, and obviously that has the same first 2 initials as Mark Zuckerberg, a temporary Harvard student. I think he's gotten like the post hoc credit for graduating there. But yeah, his initials are the same as Mark Zuckerberg's. He also is in the same building as Zuckerberg was, my boss, the Kirkland House. Now, that house doesn't have any AC, but Harvard is bringing the AC to North American Championships with their 6th correct problem, so well done there. Maryland also 6 problems, 6 AC on C. This is Galen Collin, who is doing a fantastic job advertising his YouTube channel. UCF finally making a comeback with problem G, back into 27th place. UCF has kind of fallen from the top 25 in this contest, and they have been working to get back, but they have their work cut out for them. There's another 4 problems for them to take a look at. They know exactly which ones they have to do, and now they just have to implement them. It's an interesting question. You might wonder, for the N+1 strategy, where UCF knows they have to get 9 problems, are they still going for that? They only have 3 hours left, and in the first 2 hours, they've only been able to get 3 problems. They just got their 3rd one. Are they going to try and go for 6 more in 3 hours? Obviously, they've put a lot of thinking time into those other 6 problems, so they might know the solutions. But if you try and take on too much and you start coding multiple problems and you don't finish all of them, there's a big sunk cost. And it's not exactly a sunk cost fallacy. If the contest ends in 5 hours, you don't want to be spending time on problems you don't end up solving. San Diego with an AC on problem F, and Carnegie Mellon with an AC on problem B. This puts both of them at 6 problems. So it looks like the scoreboard is getting very filled with teams getting 6 problems. The 6th problem cutoff is becoming quite wide here. Lehigh with an AC on problem G. We've already taken a look at problem F, and problem B looks rather difficult. Maybe let's take a look at it here. See what it's talking about. We saw Andrew was working on this earlier. I think he has gotten the AC as well. All right, problem B, a tree and 2 edges. Given a connected simple graph with at most 1 edge between any pair of nodes, with n nodes and n plus 1 edges, that's a tree with 2 extra edges, so not just a tree with 1 extra edge, 2 extra edges. Answer a list of queries. For 2 distinct nodes, how many simple paths are there between them? A simple path is a path that does not repeat nodes. Obviously, for a tree, there's only 1 path between any 2 nodes, right? So there's only, that's like the definition of a tree. There are no cycles, which means there are no paths between any 2 nodes. For a cactus, I think, well, not a cactus, a Cthulhu graph, which is some sort of graph that has n edges and n nodes, you can make some observations here. It's not super complicated. I'll show you a bit about what it looks like here. Often you have either 1 or 2 paths between the nodes. So a Cthulhu graph has, interestingly, it has, like, let's say you have a bunch of nodes in a ring. So this is some sort of graph. This has 5 nodes and 5 edges. So this would have 1 extra edge. And you can also have like mini trees coming off of here. So you can have something like this. So in this case, 2 different nodes will have 2 paths between them. Let's say we pick this node here and this node here. If either they're in different trees, or we can define the tree's root as being this node in the cycle here. So we can say these are all separate roots. And now it's always true that there is only 1 path between 2 nodes, only if they're in the same tree. So any other, if we pick 2 different tree roots and we're able to identify this cycle, and then we can find all the nodes in it, we can associate every node with the closest node in this cycle. So this will give us the answer for if there's n plus 1 edges. The tricky thing is this has an additional edge, right? So it's 1 more layer more difficult. And this edge can be, there can be like a bunch of different ways you might have this edge. So if we have something like this, now we have like a figure 8 style, right? So we have something like this, where this is actually a path here. So maybe I'll draw it like, so we have a figure 8. And any of the nodes here can have their own trees. So we can have things that look like this. And now we have our own paths to discover. But basically, we can probably identify the parts of the graph that are this part here, this middle branch, and then the other 2 branches. I guess there isn't really any distinguishing factor between the middle and the left and the right. You just have these 2 nodes, and then the nodes along the path. Does that make sense? Is that true? Or is it even simpler than this?
So the way that when I so I'm the author for problem B, a tree and 2 edges.
Really? All right.
Yeah. So I actually wrote this problem. So the solution that I had in mind was relatively simpler, and you can sort of incrementally build up this idea by. So the way that I thought about it is we focus on the tree and 1 edge case.
Yeah, so we just talked about that. Yep.
Yeah. So in the tree and 1 edge case, basically what happens is, so you can always use actually think about it as a tree and 1 edge. So you pick
Well,
your
what do you decide is the edge?
It doesn't matter. So
Okay.
as long as you pick a spanning tree, you can pick an arbitrary edge, and that is your plus 1 edge. Okay, so let's ignore the plus 1 edge for now. So if you only have a tree, how many simple paths are there between two vertices?
Well, obviously just one.
Right. So by definition, if you have a tree, there is only one path on the tree that gets you between two vertices. So when you add an edge, the opportunities that you have to add simple paths require using that edge.
Yes.
So you can either use that edge going in one direction, or you can use it going in the other direction.
Okay.
So
But whether you can use it depends on the location of the other nodes, of course, right?
right. So
So
now
should we root this tree? Would that be helpful?
yes, rooting the tree is helpful.
So I guess we'll pick this as the root.
Mm-hmm.
So now all of these edges have directions.
Yes. So the other thing that happens when you root the tree is now we can define the lowest common ancestor.
So if we have the two nodes that are connected by this, let's say we have this node here. Oh man, lots of stuff here. I'll color them in here. So this node here and this node here. These are connected by our special edge.
Mm-hmm.
The LCA of these two nodes is this node here. So
Yes.
this is the lowest common ancestor, which is the closest node to the root.
Mm-hmm.
That is, if we follow edges backwards from each of these,
Right.
that's a backwards edge from each of them.
Right. So I realized that like you could compute like the lowest common ancestor between those two, but in reality, what happens is, what so computing the lowest common ancestor will be helpful, but let's not actually consider the lowest common ancestor for the query vertices at the current point in time.
Okay.
So you have your two query vertices. So you can either use there's obviously the path through the tree.
Oh wait, so what is the query? So we're given a bunch of queries for this too.
Yeah, so a query is a pair of vertices, and you want to count the number of distinct simple paths.
Between the
those.
vertices. I see.
Yeah.
Gotcha. But the tree the tree plus two edges is static. the
Yeah,
whole
the
time.
tree is static. The tree is always going to be static. So you can always use the tree edges to have a path. So you can actually draw out like the tree path where you go around.
Okay, so let's say we query this node and this node here.
Yeah.
So the only path is this path here,
Yes.
not using our special edge.
Yeah. So now imagine that you're using the special path to the right. So if you're using the special path to the right, imagine that the vertices are ordered. So you have like a start and an end.
Okay,
Because
so
of
this is A,
symmetry,
this is
it's
B.
fine. So you can go from A to B, and then you can try using the edge in like the forward direction. So if you try using the edge in the
So
forward
should we
direction,
call that this?
yeah. So let's call that the
Okay.
forward direction. We can now directly see what the path is, right? That's the path that uses the forward edge direction. Now there's the backward edge direction. So we could draw a path from A that uses that edge in that direction, but that path is illegal, you see, because it is not simple.
Yeah, because it uses like all of these nodes multiple times.
Right. So what you can do is you can figure out if so you just brute force the direction. Like there are three cases in the tree plus one edge case. You use only the tree edges. This always works. You use the edge in like the forward direction, or you use the edge in the backward direction. And you
Okay.
just check. So for the forward and the backward directions, you have to check that the path is simple.
Yeah, so that on its own is a bit tricky.
Mm-hmm.
But I guess every path would first involve going from like, let's say we want to go from here to here.
Mm-hmm.
I guess this is a bad example, right? Because it's not complex enough. But
It's actually fine. This example is fine. It's just complicated because one of the interesting vertices happens to be adjacent.
should we move B to something else?
It's fine. I would say it's fine.
I want to move it.
Okay, you can move it to like the rightmost. You can move it like to the rightmost thing on the pentagon.
Okay, let's say this is the new special one. This is B. All right, so yeah, so if we're using this direction, then the first part is we need to take the path from A to this node.
Mm-hmm.
So that'll use this path on the tree.
Yes.
Then we need to take the edge, and then we need to take this path on the tree.
Yes. So now you want to check if those two paths are disjoint.
Exactly, yeah. So I guess in this case they are. Let's look at a case where they're not. It might be more like easier to see.
That would be the reverse.
So,
So
you
the
use
reverse
this
direction.
path here,
Yeah.
and then you'd use this path here.
Yeah.
So in this case, they share some node.
Yeah. They share a bunch of nodes actually.
Yeah. So are we interested in the LCA of this and this?
So we're interested in sort of a bunch of different LCAs, or depending on how you decompose it, you are interested in LCAs. So here's how I thought about it. So I want to check if the path. So let's take a generic tree. So we can just consider a generic tree, not necessarily this one.
Okay.
So you have like some arbitrary tree, and you just take a path from A to B, and you take another path from C to D. And you want to check if the path from A to B is somehow disjoint from the path from C to D for an arbitrary tree. Like this, if
So
we
like
have this
just
primitive,
general, if you have two paths, are they disjoint?
yeah. So this is a primitive that I want to implement. I want to be able to implement the primitive, do two paths on a tree intersect.
So let's hypothetically say we had the ability to check very quickly, do two paths intersect. That would let us solve this problem entirely, right? Because basically, even if we have, like, this is if we have two nodes, but even if we have more, we can just brute force the direction for every edge, and then we can check, all right, we know we're going from here to here, we know we're going from here to here, we know we're going from here to here. There are only 4 possibilities, since there are only 2 extra edges. We just need to check, do they intersect? So that would solve the problem entirely. So the problem is now as simple as, given 2 paths on a tree from A to B and from C to D, do they intersect? Do they share any nodes at all?
Yes. So we have now reduced the problem from count number of simple paths to given 2 paths, like quickly count for 2 arbitrary paths on a tree.
On a rooted tree.
On a rooted tree. Yeah, on a rooted tree. Are they disjoint? So we're going to, so now we can, so there are a lot of different ways to do this. The way that I thought about it is I wanted to sort of make it, I wanted to make it as hard as possible to get wrong.
Okay.
So if you think about a path on a tree has to go up and then down. It could just only go down or only go up, but a path, it'll go up until it doesn't, and then it can only go down, and it'll never go back up again, right? So in this case, if you use the lowest common ancestor between the 2 nodes, you now have 2 like subpaths, and those 2 subpaths combined form the actual tree.
Yes.
Okay.
And each path is entirely vertical.
Right. And each
of
path
note.
each path is only going, let's say, only going up.
Yes.
So now,
Okay. Yeah. So we'll make this one going up.
right. So now, when we want to check if 2 arbitrary paths are disjoint,
So
we can,
we've got these 2, and we also have, like, let's say this is the other example, right? And here's the LCA.
right.
So now, instead of having to check 2 complicated paths, all we have to do is check, do any of these paths going up intersect with any of the other paths? So we can check like A, or let's say this is like, A with B, A with C. Oh, I've worded these weird, but D with B, D with C. So if any of these pairs intersect, then we have a problem.
Right. So now we've reduced the problem to something even simpler, which is you have 2 of these vertical only paths, so they only go up. Do these paths intersect?
And that seems pretty easy, because we can do that with binary lifting. So if we know how to go from some node to some other node at a higher height, we can pretty easily do that with binary lifting, which is its own strategy. So if you don't know that, you can learn how to do that, but hopefully the contestants here who are trying to solve this problem are familiar with it. And for doing that, you can see, like, if two paths intersect, you might have 4 points of interest, right? There are, each path goes up. So you're interested if at this level they're the same, at this level they're the same, and if this level they're the same. And also, I guess, at this.
It's only the
But-
2 middle ones, actually, because they
'cause
can
these
only
are
be at the
extreme.
2 middle ones.
But it's
actually,
kind of hard to tell what the 2 middle ones are, right?
it's
'Cause
always actually always the
you might also
the
have this.
lower node. It's always the lower node among the 2 like top
Of the 2
parts.
top ones.
That's the only
yeah.
one you have to check.
Because since like the property of a rooted tree, as you're going up, once they join, they're never going to split.
Yes.
One's just going to stop
So you
before the other.
yeah. So you just check. You have the 2 nodes. You check which one is further from the root, and you go to the other path, and you use the binary lifting. You can use binary lifting or any technique to count what's the node here. Is it that one?
And if these two give you different nodes, you know the paths are entirely disjoint.
Yes.
But if they're the same node, then obviously you found a place where they intersect.
Yes. So this problem is one where I think at first glance it's very you can draw like all of the different configurations and you're like, oh god, there are lots of cases to consider. But if you just break it down into I just want to check, do two paths share a node, and then you break that down even more, you eventually get to something that is doable with sort of standard tree graph theory primitives. So being able to compute the lowest common ancestor quickly is one of the standard algorithms that you learn when it comes to solving graph theory problems. So we expect that we're hoping that most teams are able to compute lowest common ancestor in logarithmic time. So one thing to be clear about is you can't do any of this. So David mentioned binary lifting. So binary lifting is a way of being able to quickly check like some ancestor or so in logarithmic time. If you just slowly walked the nodes like one node at a time until you got to the right depth, that would time out because that's a linear amount of work and the time complexity would be like n times q.
Yeah, so you have to solve each query very, very quickly. But once we compose it into simpler and simpler problems, the solution seems to make quite a bit of sense.
Yeah. Let's go back to the scoreboard. It looks like we have some interesting updates at the very top. So CMU just solved problem A at the 139-minute mark. They had 4 incorrect submissions on it, but they are the second team to get to 7 problems. So Purdue is still in first. They have 7 problems solved. Carnegie Mellon has 215 more penalty minutes than Purdue at the moment.
Oh boy, yeah, that's very exciting.
Going down the scoreboard some more, we'll see if we can get the scoreboard on the screen. It looks like there are 6 teams that have solved 6 problems. The University of Waterloo, the University of Maryland, the University of California, San Diego, the University of California, Irvine, Harvard, and Georgia Tech. So
we'll take a closer look at it in a minute, but for now we're going to take a quick sponsor break and watch this very quick video from JetBrains. Here we go.
Hello everyone, and we have a slight change in the audience in our live broadcast. I'm very happy to have with me Andrei Ivanov. Andrei, I'm so happy that we are here together at NAC together with JetBrains. I think that's very exciting to have you here.
Oh yeah, it is.
And it's me, Lydia Piroska. Hi everyone. I'm the ICPC Live Video Director from the World Finals, and I'm very happy that the live broadcast from NAC is actually as successful as it is. It is just incredible, and let's all write something for David in chat. He's getting lunch right now, which is very important. So if you haven't eaten from the very beginning of the contest, it's definitely time to grab some food, get yourself comfortable, and let's watch the live broadcast together. In the meantime, Andrew,
Yeah.
how was your time with JetBrains on NAC? Can you tell us a little bit more about JetBrains' involvement with the contest?
Just perfect. The involvement with the contest is usually small. We are just bringing the balls and put them to first solvers. But before that, we have the whole day talking to kids in the hall with our booth, and that was very interesting. We managed to bring quite a team here, both from our research team, talking about what we are doing in this area, from our advocates, development advocates team, talking about our products. So, pretty exciting, pretty exciting.
I feel like NAC is one of the unique contests that actually do the career fair and invites so many diverse IT companies, partners, both global, which is obviously JetBrains being the ICPC core programming tool sponsor. It's always a pleasure to have you, but also some local companies, institutions, research career paths. It's all very exciting to be able to show to the contestants how actually interesting their future life is as soon as they're done with the contest.
Or probably even without it, but better with it.
Yeah, it's much better with having a contest. Let's take a quick look at the current leaderboard. We have our two wonderful leaders, Purdue University and Carnegie Mellon University, both solving 7 problems.
Last time I checked, it was Waterloo.
We had Waterloo for quite a while, but Carnegie Mellon and Purdue actually were able to overtake them recently. In general, we have so many wonderful teams, and what I'm very happy to see is that every single team was pre-selected. I mean, they know how to solve programming contests. These are not just open registration call problems. As you've already noticed, and I'm sure as Nick's problem analysis make it not seem like, but the problems are actually very difficult. And we already have 50 teams solving at least one problem. We're just basically halfway through the contest. And we are wishing like all of our luck to University of Kentucky. We're very much waiting for them to get their first solved problem. They're also it looks like on the right path. They have attempts on one of the more popular problems. So let's hope it happens rather sooner than later.
As far as I understand, the sign of quality of the problem set is that everyone solves at least one, nobody solves all of them, right?
Yep, exactly.
What do you think about the second criteria? Is anybody going to solve all of them?
I very much hope that we won't have any team solving all the problems today. I'm very fortunate to not know problems both in advance and actually like not really was looking closely at the problems that are available today. But the very beginning of the contest was pretty stressful from that criteria because we had 6, I believe, problems open real fast. And currently, my favorite, I believe, submission of the whole contest is actually MIT having the first to solve on problem B. Whether we're not yet at the level where they've solved every single like easy problem at some point, but they figured, no, we're not doing on F. We're not working on K. We're actually going on B. But this is also a pretty significant monetary prize for NAC, which is, once again, an exciting opportunity for students, something that differs NAC from any other contest from all over the world, with all the variety we have on ICPC contests. So that's pretty exciting. Is there a particular team you've been rooting for? I know you're usually an MIT fan.
Yeah, I'm an MIT fan, but also after our conversation, I'm rooting for Waterloo as well, so it is 2 of my favorites in this contest.
Dear viewers, definitely let us know who you are rooting for. We see that our Argentina team's up, and we...
I'm actually rooting for Kentucky as well.
Yeah, Kentucky definitely deserves our cheers. We are very much hoping they will join us
Kentucky.
as soon as possible. But also, they can totally do that.
Yeah.
Once again, every single team had previously participated in regional programming competitions, and they know how to solve problems. They were in the top of their regional contest, so these are definitely very, very, very good teams.
Kind of semifinal, right? It is
Yes, this is the last stage before the World Finals. So whatever happens today, we will have best teams selected for the World Finals. That will take place this November in wonderful Sharm el-Sheikh. Definitely stay tuned for the ICPC News Media for further announcements. This is going to be a very exciting World Finals as well.
Yeah.
We're,
of them.
Yeah, two of them at once. I'm very much sure that JetBrains is going to be very much present there. Do you have anything special already saved or in mind for the ICPC World Finals this year?
No, nothing special. We will prepare at last moment. We are programmers. We do everything at last moment.
Well, we are problem solvers, and we do everything exactly within the allocated time slot.
You are completely right. Can you tell me how is it decided how these two finals simultaneously will be done from the team selection point of view? For example, those guys who are competing right away, which of the finals they join?
By the way, MIT decided to actually make you happy, and they've just successfully submitted problem F. So they're currently with 6 problems solved on the 6th place, which is good. We're giving out 6 prize places. Single gold, I believe, 2 silver medals and 3 bronzes. But I'm sure MIT are actually like aiming somewhere higher. So this is just a great way forward.
The first place is the only possible goal for such a team.
Yep. As for the World Finals, so the current rule set specifically says a single person is only allowed to participate in one of the 2 World Finals that will take place this November. So currently in the contest, we do not have any, hopefully, world finalists who have already advanced within contestants. But we have them among coaches, by the way. So we will have several incredible success stories, in my opinions, where a student was previously a contestant from the last year, advanced to the world finals in Egypt, and then this year brought an incredibly strong team to NAC. And I'm very much rooting for them to advance to the World Finals as well. The registration is going to be tough. The coach will have to like juggle T-shirts and make sure that they're on the same, they're in the correct moment, on the same place, and the pictures are all taken. But this is going to be exciting. So, and then university-wise, there is no limitation on a university to either be on one World Finals or another. Universities can have teams in both World Finals at the same time.
That seems like a good chance for some teams that wouldn't be able to win in the regular way because they are not in the top league to actually win. Because some of those universities from top league wouldn't probably be able to bring 2 teams. You know, it is always difficult.
It is true, but at the same time, I feel like current information on who actually won regional contests, like we don't have a final list of contestants for this World Finals yet, but everything that we see, both World Finals are incredibly stacked. And with the current results that we actually have in this contest, I can barely imagine like how many incredibly strong teams from this specific contest are actually going to advance. So this is definitely a contest to follow for today, and we are very much looking forward to a live broadcast in November as well.
Yeah, you
also,
tell me already, I promise.
Awesome. I'll catch you on that. Another thing that I feel some of our spectators may not know, but I want them to definitely follow that. So last year's JetBrains Tech Track was a very exciting race between Eric Toe and incredible Andrew He that we can follow right now. He's actually solving the NAC problems right now at the same time as us watching him, but he actually started quite a few minutes later after the actual contest start. This is actually done just for convenience. We make sure that everything is okay with the contest, and then we move on to an online judge where external contestants can perform.
Do you know how far he is solving the problems?
We have not seen that recently, but as far as I can see, he has 5 problems, problem statements, yet to solve. So we actually expect their team to have 1, 2, 3, 4, 5, 8 problems solved currently. Let's hope we see that within the coming minute of us following him closely.
They are actually higher than any of the team participants.
That's the assumption. And actually, Andrew is going to submit something right now. Here is a submission on problem J. Oh, that's exciting. We'll be able to actually see. Yeah, exactly. 1, 2, 3, 4. They have 5 unsolved problems. And incorrect. Oh, I'm so sorry for Andrew now. I'm afraid that this is exactly why, because we are currently following him. But oh well.
Visit effect.
Yeah, and also, as it was already discussed by Nick at the beginning of the broadcast, but I hope that our new spectators will also appreciate that information. Andrew is currently participating in NAC as part of the UCOP. So if you're actually looking for a regular regional finals, NAC, world finals level training, definitely join UCOP. That would be an exciting opportunity for you to improve and train regularly against quite a number of some legendary grandmasters from our field.
Great. My favorite question, I
Sure.
already asked you before, but I will repeat. Did artificial intelligence try to solve the problem from today's problem set? And if it did, do you think it would solve it faster than?
Well, the
Yes.
papers that I've read so far were not very successful at solving problems from Div 1 code forces round. And let me tell you, NAC is like a very complicated problem set.
Okay.
That is definitely worth Div 1 code forces and higher. So yeah, artificial intelligence can definitely give me a call the next time it actually solves like problem B in Div 1 or something. But so far, I can see how we can use language models to make judges' lives easier and building problem statements, making them as elaborate and eloquent as they need, because there is a really nice tradition amongst all the judges, I believe, to every once in a while have a problem with incredibly long statement, but pretty easy solution. And you know, it's sometimes a little tedious to actually write those, to come up with a crazy, interesting, weird problem statement. Well, we will be happy to have some AI help in here. But with the problem solving, yeah, still quite a way to go. But we would be happy to have more information about how
What is
AI
your
can actually
estimation?
work with.
How soon artificial intelligence will be able to win the competition?
I mean,
How many
it
years?
can win a competition
I think a couple
with
of years
trivial
max.
problems.
No, with this kind of stuff.
With NAC, oh, I would be happy to bet 5 years or probably even more. Are you ready to go
think
over under?
2 years at max.
Okay, so let's bet. I'm putting it on over 4 years, and you're on under 4 years.
Under 3.
Under 3. Okay, excellent. Now everyone can follow our incredible bet in a real time. If you're actually working on an application of artificial intelligence to problem solving, let us know in the comments. We would be happy to learn that from you. Or if you have any ideas on what kind of other research topics you would like to know more, we know that JetBrains does quite a number of research initiatives. Can you
JetBrains
tell us a
research.
little bit about JetBrains research activities?
It got a significant hit last year because of the war. So we actually lost a few laboratories because they didn't move together with us out of Russia. But still we have quite a few which are doing pretty interesting stuff. And currently it's all one way or another related to the artificial intelligence progression. Probably the most interesting is our lab about machine learning for software engineering, where we are trying to use it to help programmers and programming teams to do their job more efficiently, so to say.
And there recently has been very clear breakthroughs.
Yeah.
And some of them I also feel like are very applicable to everyday life of software engineers. Didn't just even Google recently during the Google I/O announced that they within the Android Studio, that is obviously a joint product that is cannot be possible without JetBrains as well. You can just copy paste all the necessary examples, figure out all the I don't want to say trivial, but basic layout components that you can just copy paste right from your what's it called? It's your companion, like the IDE companion pane.
Copilot?
Copilot, exactly.
Copilot, yeah. It seems to me that the future of software development would be at least the joint efforts between a human and artificial intelligence. And all of IDEs are currently doing some kind of functionality, us included, to make it possible. So you're writing something yourself, then you ask artificial intelligence to help you and get a help, and then you do something with this help. So this we already support to some extent in Fleet. I don't know whether it's already available in the latest preview, but it will be soon enough. But it is not. It is only the first step, of course, because we are currently inside the revolution. So how much our job will be taken from us by artificial intelligence? It is questions to be answered next few years.
Also, there's always the talk about competitions based on artificial intelligence and language models as well. We recently came up with an idea of a prompt-based competition.
Yeah.
So, what do you think? How would it be interesting for JetBrains to probably make it something along the lines? We put two incredibly experienced competitive programmers, but they're not actually allowed to type any code. They're only allowed to type a prompt into your language model and then copy-paste whatever results come out of it.
Yep.
Will it be easy for them to solve competitive programming problems in such a way? What do you think?
I think it will. Probably not immediately, but soon enough. And actually, the prompt engineering and working with prompts, it's probably kind of a future of programming. I mean, there are three stages you have when you're working with artificial intelligence to program. First, prompt engineering, then working with actual code generator, and then checking the results. And I think that first and third is where the future of tools is. I mean, prompt engineering helping to clarify the good task for the AI, and then checking the results, because as we know, AI is hallucinating a lot. So you cannot trust it.
We have a submission from Waterloo on problem B, one of the problems that I personally love more. Let's just put just a little bit of pressure on them. Let's hope it actually goes through the test. And they are currently in the first place, which is an exciting moment to be in a live broadcast. Yay, go Waterloo. As we come back to the incredible ways the future of software engineering will look like, I feel like there is also not a missed opportunity, but a missed mention of how good we are actually currently at the automated testing process. We have all these incredible tools. They've been around for quite a few years already that allow you to figure out if your code actually works reasonably well within the given constraints. And obviously, ICPC competition is quite a synthetic, but a version of that. We are also preparing tests using automated generators. We just make sure that every single test is actually passed in a timely manner. And this is also an area where JetBrains is very successful with the whole CI/CD process and making sure that the software quality is actually high enough. Do you have any new research in that direction that we should wait?
We definitely do. It is actually, we have Vladimir Kovalenko here, who is the lead of the
For
lab.
real?
Yeah.
You know, we studied at the same school.
Yeah, I heard.
Oh, that's cool.
So he's here, and he actually leading the lab, which is doing the test generated and automatic test generated problem. So I can try to catch him and talk to him about it in more details. I'm just a manager, so I don't know details.
Well, you're an incredible manager.
Thank you
because
very
you're
much.
bringing us so many talented JetBrains employees to interact with. And I feel like we as an ICPC are trying to do our part with connecting basically as talented students with these talented colleagues of yours as possible.
It is really a synergetic combination between JetBrains and ICPC. I always say it, we're part of the family, we feel ourselves part of the family. So a lot of people from ICPC works for us. We try to help as much as we can. We try to have as much talk and discussions between ICPC teams and our engineers and research leaders as possible. And actually the NIC is, the NIC 2020 is the place where I personally changed my assumption about the possibility between to collaborate between ICPC and development companies, because it was a really nice and collaboration experience. There was a whole week in Atlanta where we were able to talk to teams and make friends among them. Because, you know, in some of the ICPC events, there is not much the company can do with teams, because teams are busy.
And the schedule
They're
is very
solving
packed
tasks.
usually.
Exactly. Yeah.
Whereas on NAC and NAPC, which is a very important part, people, myself included, tend to omit the NAPC part, whereas this is probably even more important part for the excellence of those contestants,
Yep.
for their integration into the general software engineering field, than the competition itself. The competition is just 5 hours. The friendships and connections that we're building here are very likely to last longer.
Yeah, but this model that NEC and APC have, it is really good and right, and I hope that all of the regionals will be done in the same model, with more time dedicated for this and more time that companies can spend talking to the teams without disturbing them from the real competition and preparing to it.
Sounds like an excellent way to end our incredible discussion. Thank you so much for being here. We're very much waiting for everything that JetBrains prepares for the future ICPC
I
competitions.
think we will be doing that together, because I really want to have the similar thing we had in Moscow and Dhaka, in Sharm el Sheikh as well. Is probably Gennady participating in it, so I need to help with this.
Okay, we will.
Thank you
very
for
much
having
for
us.
coming to the broadcast, and see you soon.
See you soon.
Welcome back. We have a scoreboard update here. Waterloo now has 8 problems in first place. Oh my goodness.
Yeah, so very recent update. So Waterloo was first to solve problem E. They have the dark green on problem E, and then 6 minutes later, they 1A-C'd problem B. So now they're the first to 8. Out of all of the problems, so there are now 9 unique problems that have been solved in contest, and Waterloo has solved 8 of them. The only one they haven't solved is problem L.
And it looks like we just got another AC from UCLA, moving them into 17th place, and from Emory into 28th place.
Yeah.
Problem C, no one else has even attempted it, right?
C?
Or sorry, E. Excuse me.
E, there were a couple other attempts. MIT has attempted it 5 times.
Oof.
UCLA has attempted it 4 times, and
Oof.
that's about it. I was looking at MIT's code. It looks roughly in the right direction, but they have a lot of variable names that look the same. So a lot of their wrong submissions are one-line fixes of one variable into a different variable. It's very hard to tease apart the logic. There's a lot of casework, so it's very likely that they're just missing. They might have one case wrong or something like that. But the code, like, roughly looks like it has the right idea, at least.
It looks like MIT is really hitting a wall when it comes to both that and problem K. At this point, it might even be worth just having a different teammate recode K.
Yeah, because if they can get both E and K, then they will have 8 problems solved, and that will be tied with the first place team, which is the position that they were in a while back.
All of a sudden, the skies become so much brighter when you're sitting at 8 problems instead of 6, especially if you're MIT. I mean, for most teams, 6 problems is fantastic. Right? Very
Yeah,
impressive.
like at this point, Waterloo, I would guess that they've like they've gotten their ticket to World Finals at this point. It seems unlikely that other teams are going. Well, it seems like they're on a roll. They're going to continue solving problems. So even if a lot of other teams get to 8, they were the first ones there. They're probably going to keep it up. So.
Of note, UCF has improved quite a bit. During the first 100 minutes of contest, they solved 1 problem, and in the following 50 minutes of contest, they got 4.
Yeah, so it looks
So
like.
that means in the next 25, they're going to solve 8 or solve 16.
Oh no.
Solve the entire set and a half.
Oh no. I've during the the precursor to all of the contests, people were asking me about problems. They were like, "Oh, like how many problems did you write?" and so on. And I think I've already mentioned this. I was like, "Yeah, I wrote at least 0 problems in the problem set." And they asked me how many problems there are total, and I'm like, at least 0. So we'll see if UCF can solve all 13 by the end if they're just continually accelerating.
Speaking of, we have UCF attempting another problem C. They got time limit exceeded on that, which is interesting. Wait, is that even possible?
Problem C, time limit exceeded is very,
spanning
very
tree.
reasonable. But Harvard in 4th place now. They just solved problem L. So they are the 4th team to 7 problems solved. So they joined Purdue and Carnegie Mellon at 7. So those teams are also looking really comfortable. If we look through the rest of the scoreboard, it looks like the top 11 teams have solved 6 problems, and then the top 22 teams have solved 5. So there's this open question of how many teams are going to make it to World Finals. Like, are there going to be 22 slots, or we'll have to see how these teams at 5 if they can get to 6.
We see MSOE, the bottom of the 5 problem solved pack. One of their team members is currently ranked 40th place on Caddis.
That's
Do you have something to say about that, Nick?
Oh no, not this.
What are you ranked on Caddis?
Oh, okay. We cannot be having this conversation right now.
We won't have this conversation right now.
Oh my
Nick
God.
is number 1, right? Number 2?
So this has been changing during the event. So the North American Programming Camp is being run on Caddis, and so there's Open Caddis. So someone went to Open Caddis and they were like, "You're no longer in rank 1," and I was like, "Huh?" And so I was like, "Oh, there's this professor named Doug who also solves problems on Caddis," and I was like, "Huh? I guess he had some free time before NAC and decided to solve a bunch of problems." But no, it was someone else from Moscow Institute of Physics and Technology. And I was like, well, this isn't acceptable. So then during NAC, I've just been on Caddis like the entire event solving problems, and people were like, why are you solving problems? And it's like, well, someone told me I needed to get rank 1 back. So yeah.
Maybe 40th then on Caddis is impressive. Maybe it's not, but it's certainly something to be proud of.
It's
something only 40 people are better at.
It's a lot of dedication. It's a lot of dedication to training, and that's how you get better, through a lot of hard work and a lot of practice.
UCF looks like they've had a series of wrong answers on C. They've gotten their 4th one wrong here, which must be a little annoying. Maybe they didn't do enough stretching and yoga beforehand. I know that is their routine before every contest, is to do some yoga.
I'm taking a quick look. It looks like their code on the secret test cases is not doing super well. There's
lots of wrong answers.
It's mostly time limit. Their code's just mostly a little bit too slow. It's in C++. I thought UCF was mostly a Java shop.
We certainly used to be. Since then, I think Andy has switched to C++. Lots of people have followed. And I think the newer folks are now using a C++ library. We call it a hack pack at UCF. But C++ library code is very common, although I'm certainly in the older generation where we were all Java all the time.
All right, I looked at their code. So problem C, the bounds are like 2,000, 3,000. So it's the broken minimum spanning tree problem, where you have a graph of 2,000 nodes, 3,000 edges. The intended solution complexity is O of n times m, roughly. Actually, it might be m log m, or no, it's O of n times m. Their solution has an extra log factor in the complexity, and I believe that is the reason that it is too slow. So they're going to have to remove that log factor in order to actually solve the problem. They have a bunch of sets in there, and you don't need a set in this problem. You're computing a minimum spanning tree, and yeah, like you don't need a set when you're doing that.
Log chopping like a lumberjack. MIT's got 2 more wrong submits, one on K and one on E, I think.
The University of Dallas, Texas is the next team to get the 7 problems. They just solved problem F. So they're now in 6th place, and now in order to have a medal, you must solve at least 7 problems.
I think it's very likely that that's going to increase to 8 or 9.
Yeah,
especially with how few submits we have on B.
If you remember our earlier discussion from the M+1 heuristic.
Sorry, Collins' team just got B. So
Collins'
speaking of,
got
Maryland just got B. They're at 7 problems now in 3rd place. So
I
it's
see.
likely that B is the waterfall is turning. We have 5 different teams who have gotten it, and it likely teams are seeing that it's easier than it looks.
Yeah, I'm actually, I don't know, I didn't know how to evaluate problem L, but if you look at the top, it's like the top 4 teams have L, and then the next 3 teams, or the top 4 teams have B, and then the next 3 teams have L. I didn't know how to estimate the difficulty. I thought it was going to be hard. It looks like the top teams are proving me wrong. I'm always glad to see that the problem is easier than I thought, because problem sets always skew a little hard. So we'll see. We'll see if the teams that solve B can solve L, and if the teams that are solving L can solve B.
All right, we are going to have to take a quick sponsor break, but right after this, we will be back with Gennady Garakovich, tourist, to talk about some of the hard problems in this set. See you guys in a minute here.
So I interned at 2 Sigma last summer, and I returned this fall primarily because of the people I met.
I feel like people here genuinely form a community around shared interests, usually a shared passion for science and tech.
Honestly speaking, finance wasn't on my list when I started job hunting. But when I came here, everyone was so smart and so friendly and so sincere. And I feel like my skill set can be truly valued here, and that's something really important to me.
There's so many cool, exciting projects to work on, and I know I'm going to be working with those people that are super knowledgeable, and that's like what drives me to move forward.
At other tech companies I've worked at, you can kind of feel like you're a very, very small part of a very, very large thing, and that you're kind of expendable that way. Whereas here, people are extremely invested in my success.
This is just the perfect place to be. So yeah, I'm pretty happy I made that decision.
I mean, yeah, so I solved up to G.
You solved up to G. All right, here we go. Up to G, okay. By difficulty or from
left to right?
Left to right. Oh boy, all right. So let's take a look. So we have solved A, we've talked about, and C we've talked about. D and E we have no clue, and then F and G look pretty easy. F is the rectangle one, right? And then G, what is G?
G is frequent flyer. It's kind of easy.
Yeah, G's easy. All right, apparently G's easy. I don't think we've talked about it, so maybe we'll watch a solution video on it and skip that, and we'll just talk about maybe some of the harder ones, huh?
Well, I feel like I know H, but I didn't have time, sorry.
Let's, yeah, no worries, no worries. Oh, all right, hang on. There we go. Welcome back. All right, we have tourists here, and let's talk about some of the good problems. He solved problems, first G of them, right?
First G of them, yeah.
First G of them.
I was going left to right because why not? And I solved A, B, C, D, E, F, G up to this point. We can say that the first ranked team, University of Waterloo, got all of those problems and D. Except D, sorry. But also I and K, right? So it's pretty comparable, but I don't know, D took me quite a while to get. So sure.
Do you want to talk about E first?
Sure.
I think it's more reasonable.
Of course. So problem E, which Waterloo solved, right? We just saw that.
Yes. Let's read it first. Does that sound alright?
Oh, of course. So problem E is about a game which is called like word chain or geography. Essentially, you are given a list of words, 2 players play. The first player picks any word from the list. The next player picks any word that starts with the letter that the previous word ended on. You cannot repeat words, and the one who cannot pick the next word loses, like because there are no more words that start with the last letter of the previous word.
So let's do a quick example here. Let's say your words are,
For example,
all right, so attic, climb, and alpha.
yeah.
So obviously we have C's match, these A's match. Oh, so it's first and last, right? So
Yeah, first and last.
A matches this last A.
Yeah, and also, yeah, sure.
I guess that's it.
That's it in this case, yeah. And
So-
the problem is asking like, the first player can choose any word at the starting word, but the problem is essentially how many words as the starting words would work for the first player to win the game if both players play optimally.
Hang on. So it's
Yeah.
This is
No,
not the
it's-
right graph.
It's okay. I mean, usually, whatever, yeah. You can,
Okay, yeah. So attic goes to climb,
yeah.
and then alpha goes, I guess, also to alpha, but also to attic.
Yeah, but also you cannot repeat words, so actually,
So it doesn't
like,
really matter.
Like this edge doesn't matter, right? You cannot go from alpha to alpha.
Okay.
But you can go from alpha to attic. You can go from attic to climb. And so, once again, the first player can choose any word as the first word. So, for example, here, if
And
there's
you win if
Allison,
you move
Allison
last?
involved, you lose if you cannot.
If you can.
make
So
it.
yes, you win if you move last.
That's
Yeah, yeah.
exactly.
Okay.
So, for example, if there are two players, Alice and Bob, and Alice goes first. If Alice picks climb as the first word, she just wins.
Wins
instantly.
outright.
Because
Yeah.
like Bob doesn't have any words that start with B. So
Makes
that's
sense.
one starting word. If Alice starts with attic, then what happens is Bob can name climb after that, and then Alice cannot make any more.
But Alice could also start with alpha and also.
But
win.
if Alice starts with alpha, then Bob has to name attic, Alice names climb, and Alice wins because Bob doesn't have any information. So there are two words, climb and alpha, which Alice wins if she picks first.
And the question
that's-
is, how many words
Yeah.
can Alice pick first and win? Okay.
Yeah, exactly.
Gotcha.
And this problem in general is kind of well known, like as the generalized geography, I think is like one of the neighborhood terms. Sure. And the twist in this problem, like I think this problem like is not solvable like in polynomial time. At least not known at least how to solve in polynomial time for now. But in this problem, there's a twist that there are only 3 letters that words start or end with.
Wait, what?
So yeah, like it says that there are at most 3 distinct
my
letters
goodness.
at the beginning and end of all words. So like for example, it could be that like the letters are A, B, C. So every word starts with A, B, or C and ends with A, B, or C.
So in this case, that's it, right?
Yeah,
so you have
like, for
A,
example.
C, and A, and then C, B, A.
Yeah.
I see. And obviously, if you have some word, none of the letters in the middle really matter at all, other than
Exactly.
the words are distinct,
Exactly.
but they don't matter. So really, you only have, 9 different types of words?
Yes, you have 9 types of words, 3 times 3, and for every type you can have multiple words of that type.
Gotcha.
They're all like distinct, so you can only use every word once, but
I
that's
see.
it.
So yeah, so you're like, if you were to do this as a DP, you have like a state, which is like, I guess 9-dimensional, and the sum of these things is 1,000, which is obviously probably way too big to actually do a DP for, I would imagine. Maybe you can do something clever, but yeah, okay. So you have this observation here, though. Okay. Interesting. Okay. I think I understand the problem, but I have initially no ideas whatsoever of like how to approach this.
yeah. So in this case, first of all, you drew a graph, right? That's what that's your first instinct, right? You have words, and you draw you create a graph where you make an edge between words. I mean, like you can go from this word to this word, right?
Yeah, so I guess we would have 9 different nodes, one for each type, and then each node has like a count of how many times we have left.
You could do that, yeah.
And,
But
and you've got like some directed edges.
yeah, you could do that.
Okay.
But this formulation I think is worse and less clear than the other one.
Oh,
and the
okay.
best, but the better formulation is to have vertices not for every word, but for every letter. A, B, and
Ah, okay.
C.
you
So
have, like-
essentially, you will just have 3 vertices in your graph: A, B, and C. And now every word is an edge from A to B,
With
from A
self
to A.
loops,
Could be
yeah.
loops, yeah. Could be multiple. Could go
and you
both
have 2
directions.
directions,
Yeah,
yeah.
for example, here.
And every edge has like a certain count, it's like a certain weight, maybe.
Yeah.
So like you have 3 words that go from A to B, 5 from A to A.
Yeah, exactly.
1 from this, 1 from this, and 2 from this.
Yeah, exactly. So you can model the problem like this, and now the game looks like you are at some vertex. You pick any outgoing edge from this vertex, you move to the end of this edge, and you remove the edge, right? Because you cannot use the edge more than once.
I see. So
or
if
you decrease the count.
Yeah. So if we're in a situation like this, if we ever take this edge to go away from A, since C is like on its own, I guess this isn't important, but since C is on its own, we will always take this edge back. So like essentially this C part is meaningless. We can like drop the
In
whole
this
thing
case,
off. But you could end up going to B, and then that wouldn't really be true.
That would be important. Yeah, you could have edge from C to B, and
I guess if they're an even number of self loops, then you can ignore them, right? Like there's no sense in having an even number, because if you take one, your opponent can always counter with the other one.
Exactly. Yeah. So I think like to formally prove this, it might take some some formal writings, but intuitively it's very clear, right? Like if there's if there are 2 words, like 2 loops for vertex C, like using a loop can never be a winning move for you, because your opponent just repeats your move, and like you have to do something else anyway. So
yeah, like if they're an even number, you're never gonna choose, and you're winning. If there were 0, you would never choose to do it. And if they're an even number and you're losing, if you do choose to do it, your opponent will just do the same thing until there is 0 of them.
Yeah, and you'll get to 0. So essentially, for every vertex, you can only leave like 0 or 1 self loops.
Yes. Okay. All right. So maybe this DP does end up being possible. We're cutting things down quite a bit. So we now have, so this is 0, and this would be 1, and now we have an equivalent problem. We might also have edges here, but now we have like 3 very limited types of edges, and then 6 very general types of edges.
Yeah, so it would make it 6, so now like n to 6 when n is 1000. So essentially like we could have like, I don't know, 160 edges of 6 types, and 160 to 6 is still too large.
Yeah.
So just the general DP still does not work. But there's also another observation which seems to be correct. At least I guess my solution used it in the past. But again, to prove it, you might not want to be formal. So it's similar to the one you made. Essentially, it's about edges.
Is it like these? So if these are both like 10,
then you just remove them.
So can you remove them to 0 or mod 2?
Well, it's not about parity here. It's about like if you have 15 edges in one direction and 10 to the opposite direction.
That's the same as 5 to one direction?
Yeah, and just 0 to that one.
Interesting. Okay.
Yeah.
That's
yeah.
Seems harder to prove, but I could see that would be easy to like come up with. Like just like think that might be true, but yeah, so why is that true? Like why?
Well, so essentially kind of like you can take the 10 extra like pairs of edges going back and forth and claim that like again using one of those edges can never be the only winning move for you, because the opponent can just take the other edge and put you back to the same vertex.
Yeah. Okay, so it is like the same logic. So like, yeah, if you're winning, then if you take one of these, your opponent could make you losing, so you would just pretend this doesn't exist. And then if you're losing, then taking this doesn't matter. You can just pretend it doesn't exist anyway, because your opponent will just bring you right back.
Yeah, sometimes.
So, okay. All right, yeah, very cool. All right, so now everything is, well, now we have 3 edges. This can be something, this can be something, and then we have a one-way direction here. So this is something. And these sum to 1,000, so we have like 300 cubed, roughly, is the runtime?
Yeah, also
times like 2 to the
2 to 3, right? Because like for every vertex you can have a loop or not, and then like also you have to like, I don't know, like try like what the next move is and stuff like that. So it could be fast enough. Like like it's also the time limit is 1 second. Like I don't know, like maybe you can probably get it accepted, but you can go further after like the analysis and like.
Okay, so let's say you have.
I guess it's harder actually.
If you have like a cycle, can you do anything there?
So there are actually
first
two cases, right? Like essentially, like So first of all, we have left only just like one, like direction between every two verses, right?
Yes.
So we can have a cyclic graph like
maybe
this.
like 1 or 2 self loops, but there aren't many.
maybe 3 too. Like, I mean, it could happen.
Yeah. Okay.
Like, we don't know. And also, some of these edges might not exist and stuff like that, right?
Yeah. Yeah.
Yeah.
Oh, do we want a cycle or no?
Let's say not cycle. I think it's the
Okay.
an easier case, right? So here, yeah, you can order the verses like A, B, C, and like say you only can have verses edges from A to B, A to C, or B to C, right? Like in this example. First of all, like I guess the number of edges between A and B doesn't matter as long as it's positive, because you cannot use it twice. You can go back to A, right?
Yeah. So whether this is 10 or 1 doesn't matter, because you'll never really get back. That's clever. Yeah. Okay.
Yep, that's one thing.
And so now we're at 500 squared times 2 to the
No,
4.
sorry, that applies to all of the edges, BC and AC as well. Like you
Oh,
cannot
because
use
there's
any
no
of them.
cycles. Yeah,
you can't
exactly.
use any of them
So this is
twice.
just 2 to the 6.
Yeah, you can do the B, or you can just like manually solve it like
Sure.
small cases.
Okay. Yeah, very cool. All right, so now last one is we have a cycle.
Yeah, last one is we have a cycle, and first of all, let's say we have a cycle. Now the counts matter now, right? Because we can go by the cycle and like stop somewhere, right?
Yeah.
Let's say we have no loops, first of all.
We have no loops. Oh, no self loops. Okay, yeah.
No self loops, yeah.
Yeah.
What do we see in this case?
So it seems like this is a very much a guess, so I don't have a proof here. But if you go around twice, then that's 6 moves, and that's an even number. So it's the same person's turn, and you're at the same thing, and you've just subtracted 2 from everything.
Okay.
Also, I mean, the other observation is your moves are forced, so we can initially just count the parity, see who wins.
Yeah, essentially, like here, there's no game. Like
it's just
you just go until
simulation.
you're stuck.
Yeah.
Like you just simulate and you know what happens. And I think one way, like if there are, well, here it's not like 12, right? Because like it's not like this. It's different,
you're right.
Because you'll
it's
stop
7.
somewhere in the middle, right? Essentially, we'll stop after. You'll stop at where it's B,
So
right?
it's like 8 plus 7 plus 7.
Yes.
Okay.
Like you will make 7 full loops and then one more step from A to B, and stop, because you're out of edges from B to C.
Yes. Okay, that makes sense. All right, so we had a very complicated problem, and the last part we have is what happens when there are self loops. Like a player could choose to not go to the next one, instead take a self loop. So let's say we've got like, well, if we just say we have 1 here for now.
Yeah.
If you're losing and you're at A, you would take it. But otherwise, yeah. So you can, like, if these numbers are big, you'll never be able to force A to never get taken, because it's your turn now. So like this will be Alice, but like next time around the cycle, it'll be Bob's turn.
Yeah, I think that's about my reasoning as well. So like, if the numbers are big enough, you will always like, someone like will be able to take this. So you'll just add that to the, like, you took some parity to find the winner, right? And you just add self loops there as well, like, because someone will be able to use them anyway.
Okay, and then if one of these is like very small, then you just
yeah, you can just do some DP or something. Yeah.
Okay.
Yeah.
All right, very cool.
Okay.
That is that's an advanced problem, but each of those steps made sense. All right, let's check the scoreboard first to see if there's any emergencies.
Hey.
We have 3 teams with 8 all of a sudden. Wow. Purdue, Waterloo, and Maryland.
But I guess the biggest emergency is the first to solve problem J.
Yes. Oh my goodness, you're right. Toronto just got J.
It's their 7th problem though, so they have not solved either of B and L, but they solved J.
I believe they'll definitely be able to get B. B is quite doable, I think. I mean, maybe it takes a few steps, but once you know it's doable, I think it becomes more doable.
Yeah.
Awesome. Yeah, very cool. We can take a look at J live if you'd like in a minute. Otherwise, we can maybe look at D. Do you think D is something we'd be able to explain?
Do I think D is something we could be able to explain?
Or is it just way too hard?
We can explain the statement in any case. I think it's definitely good enough, and then we can just describe the gist of the solution.
Okay.
That's fine.
Yeah, that sounds good. Should I read it?
I can explain it on the screen.
Sounds great. Let's go.
It's reasonable. So in this problem, you're testing some like software project, and you have n tests. Each test, I know, you can imagine as like, I don't know, a circle, whatever. For each test, you have 2 numbers. The first number is how much time it takes to run this test.
Okay.
Like CI, whatever. C1, C2, yeah, whatever. Some numbers. And the second number for each test is the probability that this test passes.
Okay.
And it's claimed that all the probabilities are independent.
So if one passes, it has no effect on whether
Yes,
the next one
yes,
passes.
exactly.
So can they be 0?
It's not 0, not 1. Just
Okay.
that's kind of a degenerate case which we don't want to consider this problem. And yeah. And now, the idea of this problem is basically we want to test our project, but running tests takes time. So
Okay.
we can run them in any order.
I see. Okay.
And we want to run them in such an order that the expected time until the first failed test is as low as possible. So essentially,
Oh, this is like a very real world problem. Like this.
Yeah,
This makes a
okay.
lot of sense. Okay. Yeah.
The problem is named fail fast.
Yeah.
And essentially, that's what you want to do. You want to fail as fast as possible.
And you can only run one test at a time?
You run them one by one. Yeah, left,
Okay.
right.
So
But
this will
in any
take
order.
2 seconds, whether it passes or fails.
Yeah.
And
But then if it fails, you stop.
Gotcha. And it has a 0.1% chance of passing.
Yeah.
Okay. So most of the time you'll want to do this first because this
Yeah,
will fail
it
very
seems-
quickly and it's very fast.
Yeah, in this case, it seems you want to start with this one. Yeah.
Okay. Gotcha.
Yeah. So that's one thing.
So my initial reaction is like we do something like just multiply the two and then sort by that. That doesn't work, I assume.
Well, so like in problems like this, there's an idea called exchange argument usually.
Okay.
Which says like you look at you have some order of problems. Let's say you want them left to right. Okay.
Okay.
And for any two neighboring problems, you want to figure out like, is it good that we run them this problem and then this problem, or do we want to swap them?
Yeah. I've seen like lots of instances like this.
And then you write down two formulas, essentially how much time we need if we run the first and then the other one, and in the other case.
Okay. Yeah. So like cost now and cost swap.
Yes. And then like if cost swap is smaller, we want to swap them.
To swap them. And I guess these formulas will tell us whether like this is like scalable. But
yeah. Well,
like, is it necessarily sortable? Maybe there are
Not
like
necessarily,
3
yes,
things that
yes.
we want to like cycle, and
Not
it's
necessarily.
not better unless we do all 3 at once.
It depends very much on the on how the formula looks like.
Okay.
And in this problem, I can just like tell the answer, so we don't do actual math on stream. And the idea is like you take the value of CI, which is the time that it takes, divided by 1 minus PI, which is like essentially the probability that the test fails.
Yeah. Okay.
And you sort them in increasing order, and you run the tests in this order.
Wait, is that it? Is it?
That's
I
not
feel
the-
like this
that's
would have
not the
way
whole
more
problem.
solved.
That's
Oh,
not the
okay.
whole
All right.
problem,
Okay.
but that's like an essential part. So
Okay.
like
and that's the optimal order they should be in.
Yes, you can figure out that that's just the optimal order. Essentially, like if the test runs fast, you want to run it as soon as possible.
Okay.
And
Yeah.
if it has a high probability of failing, you want also to run it as fast as possible. So it's also very intuitive.
And you
right?
balance them by multiplying in this case.
Yeah.
Okay.
essentially.
All right. Sure.
It's a
Sure.
division, but sure. Yeah. And that would be the problem, except that there is an extra twist. So you're also given, for each test, you're also given another number, which is DI, which is dependency.
Okay.
And essentially, it means it's either 0, in which case it means the test has no dependency, or it could be some other test.
So
And
the other one has to run before this one
Yes,
does?
yes.
Ah, okay. So this is like nothing. Maybe this one depends on this test.
Yes.
Can you have cycles?
You cannot have cycles, but you can have like sequences. Yeah, like this.
Okay, and then this one could depend on this one.
Maybe.
I see. So, gotcha. But you can like, okay. so instead, let's like maybe think about this as a graph problem, for instance.
Yeah, you can definitely you can only have one dependency for each task. So you can think of it as a like forest essentially. Like a tree, right?
Everything
Because,
is like a tree.
You have only one outgoing like edge from every vertex. But yeah, so in this case, well, yeah, sure, could be like this.
Something like this.
Yeah.
So we need to like find a way of merging these trees together, so that we have like all of the nodes sorted in some way, but like there are requirements additionally.
Yes. Yes.
Okay. So certainly we know the order two nodes at the same layer should be in, but I guess it gets more like in this case because they have no dependencies. But I guess it gets a little more tricky if we have something like this, where maybe this this is like bad, but this one is really good.
Yeah.
So like we really would like this one to happen now, but having it happen now requires putting a bad thing sooner, and maybe this is just like average.
Yes. So this is a good case, right? For example, here we want to run good, then average, then bad, and it's okay. Like we don't have to run bad immediately after good. We just have to run good at some point before bad, right? So we would.
But in this case, we wouldn't be able to, right? Like we would have to run bad before we run good.
Oh, sorry. I mean, I think it's the other way around. Like every test depends on something. So like.
The arrow is what it depends on.
Yeah. So you have to run.
So the arrow should be the other
direction. You have to run it down, bottom to top. I mean.
Yeah. You're right. Okay, so in this case, we would run good, and then we would run average, and then we would run bad.
Yes. So in this case, we want this. And let's say we swap good and bad.
Yes, that's
what you wanted.
Yeah, that's what I was interested in.
Yeah.
Okay, so now we have like this conundrum where we would ideally. So this is bad, and this is good.
Yeah.
So let's say somehow we end up doing these nodes, right?
Course,
and then now we have to choose, right? Do we want, like, we would like good to be immediately next, but we can't because it depends on this. So do we want to bite the bullet, do bad, and then do good, and then do average, or just do average now?
Yeah.
And then bad good.
Essentially the question, right? So
sorry, I don't mean to interrupt, but one thing that I see here is like, if we were to do this now, any decreasing sequence, we would want to do them all at once. So we could like maybe kind of find a way of considering those all being one node. And then once we've done that, we can like keep collapsing nodes until we have an increasing sequence. And now we can like make decisions greedily.
That's very much like what we have to do. Yeah.
Okay.
Like here, like if you have bad and good that depends on bad, you will want to do them at once. You will want to do bad and then immediately good.
Yeah.
So you can essentially kind of merge them into one task.
Okay.
And you can just claim like it's just one test, which is like run bad and then good immediately. Like it will have some
Is
parameters.
the math to that difficult? Or?
Well, I mean, it will have some CI and some PI, but essentially like...
You just have to find out what they are?
You can figure out, yeah.
Okay.
Like it's not too difficult. You can merge them. And then, after you merge them, you once again apply the criteria we talked about at every node. So
and then you can like use a priority queue to get the order of
everything. You will have like sets and then like you merge them for like different children of a node. And essentially like this. And then like let's say you have several tests that depend on your current test. You'll have some sequence like in which you want to run it. And then you have the like let's say you wanted like this node, like I don't know, to which
should we draw a better example?
No, it's okay. Okay. I was talking about the node like. Okay, sorry. Like my point is that just for each vertex we do the following. So we have some children, right?
Yeah.
Which we order according to the criteria, right? And we know that we want to do them like this and then this and then this.
And first, we've already combined things potentially.
Potentially, yes.
Okay. So we have like these three. Maybe we want to do this first, and then this second, and then this third.
Yes. And then you have the root node, like not the root, but like this node, right?
Yeah. Okay.
Subtree root. And you will want to also merge it with some of the like tasks. Like here, if it's bad.
So like if one is better than this, we would want to merge these two together.
Yeah, for example. Or maybe if that one is better too, we will want to merge them. Like
merge all three.
All three. Or maybe all four.
Yeah, gotcha.
Or maybe nothing. And we can
so anything that's like, we go from best to worst, and then anything that is still better than us, we'd want to merge with.
Yes, essentially that's it.
Interesting, okay.
So it's a quite complicated problem. I think like not many teams definitely will solve it, as we can already tell from the scoreboard, but I don't expect too many. Like, and also like, it's easy to find some greedy strategies, like you want to run this and this, but like, can be not that easy, so you have to use some insights.
Looks like UCF just got problem B, putting them at 6 problems, so they're climbing up the ladder for sure. Excellent comeback from their weak start. Yeah, no, that sounds like a very, very cool solution. All right, so that was D. We also had E.
Let's
check out Scoreboard.
Yeah.
All right, check out. Oh, Waterloo has 9. Wow, well done, Waterloo.
Waterloo has. Oh, and we also have the first submission to M, right? Is it
happening right now? Yeah, I think so.
from Harvard. Unfortunately, wrong answer, but
Darn.
Anyway, that could also mean that like it's solvable. Might have a solution soon, but I don't know problem M statement because I was going left turn.
Do you potentially want to think about problem J live?
I think I read it, so like we can
Talk
go
about
into
it?
But sure.
Do you have any ideas to it immediately or not quite?
Yeah, I think I do.
Where's J in the alphabet? Right, 4K. All right, repetitive string invention.
Yes, I think I can tell the problem statement as I read it.
All right.
So we are given a string of letters.
Okay.
Maybe you can look at some example.
Abacaba, the classic.
Sure, let's go Abacaba. Why not? Now we call a string repetitive if it is of even length and its first half is equal to the second.
All right, so abacaba.
Well, okay,
All right.
yeah, abacaba would be repetitive.
Repetitive, okay.
Yes.
Because so it's even length, and then this part is equal to this. Okay.
Yes.
All right.
And now the problem is we are given some string which might not be repetitive.
Okay, so back to abacaba.
Yeah, and we want to pick two substrings from the string, and then we will concatenate them in order, like first and second. We want them to be non-intersecting, like for example ABA and ABA, and we want like the concatenation to be repetitive.
And this one would be.
This one would be, yeah. And then we want to find the number of ways we can do that.
But they can be, for instance, different length.
They
so
can,
it could be like length 1 and length 3.
Yeah,
That would be
like
length 4 and 2, 2.
Could be, yeah. Like for example here, I guess it's, yeah. Let's say like swap the A and C. Like I don't know. Like let's make the test like this, yeah. For example, A C. You could choose like A B A A as the first part, A B A A.
Oh yeah, sorry.
And then B A is the second part. And when you concatenate these parts, you get a repetitive string too, right?
Do you mean just wait? Oh, and BA?
Yeah.
Oh yeah, I see. Okay. Yeah. So then you have A B A, and then B A, but this half is equal to this half. Gotcha. I see. Okay. Yeah, that makes sense. And then is 10 to the 5th?
No, it's just 800.
800.
Which is surprising.
Wait, 800. Yeah, that's odd. That's a very weird number.
Yeah. Normally, like when you have some string problems, you are usually given very long strings, right? But here you just like have 800, which is interesting. But anyway, even though the constraint is pretty low, we cannot just do it naively. For example, if we just brute force over two substrings, that would take n square options.
Right?
N square options for one substring, n square for the other one. It will be n to the 4th. To check, we also like would need like some linear time.
Yeah, 800 to the 4th is probably too slow, right?
Yeah, to the 4th is
even
definitely
on its
too
own?
slow. Yeah.
Okay.
And that again doesn't even count check-in, but we can probably optimize check-in, but it will still be n to the 4th, which is too slow. Yep. So we can probably do better here.
One observation is that one of the strings will be half the length or more.
Yeah.
And that one will either start or end with the ending string.
Yes.
So let's say this is the bigger one, hypothetically. We can like decide it is. So that means the string that's repeated is either ABA or it's BAA. Oh, but we also need to know the length.
Well, it's always no, sorry. Like I mean, it's always ABA, right? I mean, it starts. I mean.
Oh, in this case, because there's
like there are two cases essentially, like left half greater, like longer, or like right half longer, right?
Gotcha.
So let's say left half is longer because that's one case. We can just solve the other one and add the answers.
Yeah. So we could like brute force the substring. We could brute force whether this is left or right, and assume it's the longer of the two. And then we also have to brute force the length. And then so this is n cubed. So we're doing n cubed so far. So now we know what the substring is, and we know how we end. So we can probably use hashing or a bunch of other things, I imagine, to check whether this suffix matches this prefix. So in this case, it does. And now we need to say how many BAs are there in the string after this position.
Essentially, yes.
Because we know we're looking for BA.
Yes.
Is that doable? Is there an easy way of saying how many of this hash appear after this position in the substring?
Could be. I mean, we could use some hash table for sure. Like we can, if we just like have a hash table of all substrings of the fixed tanks.
Is there like a better structure that you have in
Well,
mind? Or are we gonna run into like time issues with 800
I think
cubes
with
being so
a hash
tight?
table we might run into it. Like I think n-cube in general could be fine because like it's like 500 million, and then like also there are a lot of like divisions by 2 or something, like because like the first index has to be smaller than the second index.
Yeah.
And stuff like that. So I think it could be fast enough. But with a hash table it's probably not that fast. Like it has really by constant. So what I was thinking is maybe let's try to fix the first part, like ABA in this case.
Okay.
But let's not like iterate over like the lengths
of the first string.
Of the first string. Yeah.
I see. Okay.
And
So
then
we know we're looking for like ABA, and we've fixed. Let me get rid of all of this. So we're looking for this times 2, but we haven't decided
But we know
how
that
big the first one is. Other than we know it's this big at least.
Yes. Let's say we know that like the half is ABA.
Okay.
And now we know that like the string like prolongs somewhere, so like it could be A here, right? And then BA somewhere like to the right. Like
Yeah.
this.
Okay. Or it could potentially end here.
Yeah,
I mean,
yeah.
it wouldn't, but
it wouldn't,
could.
but it could,
Yeah.
yeah. So I think what we should do is we should
say this word B.
Yeah, B is good. So let's say we fix the position of the end of the second substring, like we iterate over that one.
The end of the second substring.
Yeah.
Okay.
Like for example, the end of the string in this.
Yeah. So let's say it ends in this hypothetically.
Yes. And now I think like that's n cubed now, right? We have iterate over the first substring, like the first half of the like concatenation, right? And the.
So yeah, these 3
end.
pointers basically.
Yes,
yeah.
yes, 3 pointers. And now I think what we can do is like we go left to right from the second pointer and find how many characters match.
So we want to see how many of these match this prefix here.
Yes. So like 2 characters match here.
Yeah, and we
A
do
match,
this
B
with
match.
z values, probably.
For example, yeah.
Z values and times. Okay.
Mhm.
And then we also want to see how many of these match. Oh boy.
Yeah,
Match
essentially
what?
the suffix. Yeah, that's exactly it. The suffix
Oh,
of
match
the
the
first.
suffix of the original. Oh yeah, yeah, I see. Okay.
Right.
Let's do a different color.
Mhm.
So how many of these match this suffix? I see.
Yes.
Yeah, and we can do that with z values reversed.
Yes.
So advanced data structures, yeah, z values, for those of you who aren't familiar, is like a very tricky advanced string algorithm. It's not that tricky, but it's a string algorithm that most of the good competitors here probably know.
Yeah.
But yeah.
And essentially you have like 2 characters on the prefix and 2 on the suffix.
Yes.
But you need like 3 in total.
Yes. So you need to pick one of these and 2 of these, or one of these and 2 of these.
Yes. So you can just
So you like do min math and then like find the
Yes.
overlap.
Yeah, I think the length of the overlap is essentially like how many you can get.
Okay.
Right.
So there are 2 options here because there are 4 and you need 3.
Yes.
Plus 1.
Yes. Yes. No, plus 1.
Yeah. Okay. Very cool.
That's probably good
Yeah.
enough, yeah.
And that should be like all of those are fast, no hash tables, no big data structures,
That's
z
my
values is
understanding, yeah.
instant. Yeah. Awesome. Very cool. All right. Yeah, that was honestly easier than I expected for a problem with what, 1 solve, 0 solves?
There's 1 right
How
now,
many?
yeah, but we are getting there. And I think maybe teams will like when one team solves a problem, definitely other will look closer into it and probably get it at some point.
Yeah, my hypothesis is that any team that doesn't have B is looking at B right now because the waterfall has kind of tilted toward B. But J and E are certainly on the chopping block. And we got one more submission on F by Lehigh.
Yeah, so like it looks like there are kind of 6 easier problems, which most of the teams get. Like half of the teams already got like 6, those 6, right? And then there are B and L, which are important. So I think like if you want like to get a medal, you have to solve both of them.
Okay.
And then probably 1 more.
So that would be 8 problems for L. Oh, and we got Waterloo with a submission on J. That would make it 10 problems if they got it, and they did. Oh my goodness. Well done, Waterloo. Let's check out the scoreboard. Can we look at the scoreboard? Well done.
It's 10-8 now. Wow. Dominating.
Congratulations. Yeah, this is Never Give Up, right? They got A, B, C, E, F, G, I, J, K, and L.
Yeah, it's gonna be hard. Well, I guess their penalty is not that great, but probably they are pretty safe. And now they have 3 problems remaining, which are D, H, and M, right?
Yes.
And yeah, I guess they don't know which one to do, but they had some wrong submissions on D, right? So maybe they will fix that one next.
It would be really interesting to see where Andrew is here. We unfortunately don't have access to how many problems he has, just because of like how this is set up. But we can maybe see what he's looking at.
Looking at D. That's D.
At D? Okay.
It's the problem statement of D at least.
Problem statement of D.
Okay, let's see.
I think it's M? It
Yeah,
says M here.
They call this for M, I think, yeah. But I don't
So-
know the problems. So.
Yeah, I guess M is probably quite tricky.
It's another problem which no one submitted it. One team submitted, right? Harvard submitted it. So.
Yeah, I can explain the problem to you if you'd like to hear it. I did look at it on my lunch break a little bit. Would you like to? I guess we do have we've got upcoming guests. All right.
I think it's
all right.
good enough. I think we've done a good job.
Sounds good. Yeah, thank you so much. We will take a look at a quick solution video and be back in a minute. Here we go. Here's problem M even.
Hi, my name is Nick, and I'm here to present the solution to problem M, who watches the Watchmen? In this problem, there are n sentries in 3D space, each facing some direction. We want every sentry to be pointing at some other sentry, and for each sentry to be pointed at by exactly 1 sentry. With cost 1, we can change the direction some sentry points in. With cost 1000, we can change the location of some sentry, as long as it doesn't overlap with any other sentry. Note that in this operation, the direction does not change, so if we want to change the direction as well, we need to incur an additional cost of 1 to change its direction. We want to compute the minimum cost to attain the desired state, or report that it is impossible. There can be at most 500 sentries. When n equals 1, this is obviously impossible. However, this may be potentially surprising, but it turns out it's always possible. Furthermore, there is only one case where we need to move a sentry. Notably, n must be odd, and all of the sentries must be collinear. If n is even, or some sentries are not collinear, then we've reduced this problem to a minimum cost matching problem. So we can connect sentries I to j if I can directly see j, or we can connect I to j with an edge of cost 1 if there is no other sentry on that line segment. This corresponds to changing the direction. The collinear case is the only case that is left. In this case, we have to move 1 sentry. Since moving 1 sentry is more expensive than rotating all sentries, it is never optimal to move more than 1 sentry. Because n is small, we can afford to brute force which sentry to move out of the line, so when we move a sentry, we can form a cycle with some subsegment of sentries and the move sentry. All of the other sentries must be paired off pairwise. We'll need to use 3D rate intersection to determine the cost of that cycle, and then with some prefix sums, we can compute for a fixed prefix of sentries the minimum cost needed to pair off all of the sentries. Here we present a case when they're all collinear, so you'll notice that before moving, the second sentry from the left is pointing straight down, and after moving, we move it up to form a cycle of length 3.
Welcome back. We have a UCF coach here, Travis Mead. Travis, thank you for joining.
No problem, David. Good to be here.
We were talking a little bit about what we were going to talk about here, and we ran a little short. But, yeah, you're a UCF coach. We have UCF doing pretty well. They've had a great comeback so far.
Oh, yeah.
They had a weak start, for sure.
Yep.
To be honest. And now, have they dropped out of the top 23? Do I not see them?
They're 14.
14, yeah, there we go. Okay, very good. Very good. Yeah, U Central Florida. Yeah, they've gotten quite a few problems. I think they had some mitts on, was it B recently?
Yeah, I think they got both B and C recently.
We have got, UCF Beehive here with another UCF coach. That's Coach Arup.
Yeah. So Arup is actually the coach for that team in particular. We have like 7 or so teams that are like kind of at the regional level. And I coached 2 of them. I coached, because we were doing the Minecraft theme teams this year, I was coaching Ice and Command Block. Arup was coaching Beehive and Beacon. Beacon was also a pretty good contender for potentially making it to NAC. Unfortunately, they kind of lost out because Beehive has some pretty good coders on their team that were able to kind of like do phenomenal in the regional contest. Now, unfortunately, they didn't quite do as well as they probably could have in the regional, but they did well enough to qualify for NAC, so it was good.
It looks like they've had a really strong past couple of minutes. They got B, and then 5 minutes later C.
Yeah.
Obviously, they had been trying C for much longer before then with 6 wrong submits. But
Yep.
it's good to see they finally got it out of their way.
So the good news is that this team has like a lot of really strong coders, and so what helps out about that is that they're able to work in parallel. And so even if someone's like kind of having some issues on one problem, another team member is able to go ahead and like work on getting some of the other problems in that like kind of assist. I know that some people kind of like bet all on black sort of deal where they kind of put all their hopes on like one particular person, but I think that Beehive is like one of the better teams because like all of them are like relatively equal in strength, which is nice.
It's always a really risky strategy too, because not only is it like super high risk if the person fails at their one job, but also you are very limited in terms of flexibility.
Yeah, definitely.
Like if that person needs to be on some really long geometry problem and then they have a bug and no one else can debug it other than them, and they're also the only person that can type some FFT problem, then you are just like in big trouble.
Bottleneck, definitely.
There's just no way to get out of it other than just like massively eating up terminal time.
I think that team strategy actually isn't bad for doing a training team. Like if you're not expected to go to World Finals or NAC, like having one person that's really strong and 2 people that are kind of weak can actually kind of help bring those weaker people up because they'll see some new techniques that they wouldn't have seen otherwise. But it does kind of hurt them as well because then they might, kind of get burnt out and feel down on themselves that they're not like coding as much inside those team settings. But yeah, definitely having people as balanced as possible is like very important, I think, to team strategy in general.
We can see UCF here on the screen right now, actually. It looks like all 3 of the members, that's Andy on the far left, Natalie in the middle, and Jacob closest to us.
Yeah.
They're all talking about the solution to some idea, maybe planning out the last hour and a half of contest. At this point, I remember Arup specifically telling us many times, at this point, you figure out exactly what you're going to do, and you don't go for too many problems.
Correct.
Because if they go after 2 more, right, they try and go after 9, and they don't get either of them, that's when you run into real trouble.
Yes, definitely. There's actually 2 times we like to go ahead and kind of have a team discussion in the contest. We like to have it once after the first 90 minutes or depending on like what your team strategy is, like sometimes the first hour, the first 2 hours. You were mentioning that rule earlier where it's like you want to get like, N+1 to go ahead and like medal. So we like to have a meeting at the beginning to go ahead and say this is kind of the plans that we have for the middle of the contest, and then we like to have this meeting near the end to make sure that we know what problems that we're going to be doing in the last hour to ensure that we have a successful contest. And it's really important. Like this is like probably the most critical part of the contest now, because this is going to decide like whether they end up like getting into the World Finals qualifying region or not. So hopefully they make good decisions here.
Yeah, I would say this is definitely a critical moment in the contest, because in this case I would say N is 8. I think that's a fair estimate. That's what we had at 90 minutes, and I think it's turning out to be true.
Yeah, and they have 7 right now, so they just need to really get 1 more if they want to, kind of qualify, and they could go for 2 more if they want to be like kind of top 10, but I don't know if that's necessarily a good thing to go after. Hopefully they at least go ahead and plan out 1 that they're definitely going to get, and then like if they have time, like they could maybe have 1 other person like kind of think about 1 problem in the background. But
yeah, absolutely. Yeah, I think that's spot on. Yeah, one more is like that's your good chance to qualify. If you want a solid qualification, I would go for 1 more if I were you. Obviously, you got to get kind of lucky on penalty. We got quite a few wrong answers with C, A, and F, I think it was.
Mm-hmm.
But that'll definitely come back to bite you, especially C. But if depends on how the 8 problem shakes out, and then 9 is if you want to medal, and that's obviously tricky.
Yep.
All right, let's give Beehive a break. Let them think.
Yep.
Obviously, they can't hear us, but can you talk a little bit about training the UCF teams, Travis? I know UCF is one of the schools that very consistently has World Finals participation, relatively strong World Finals participation, and it's usually not something that you think of as one of the schools that many super smart people would naturally go to, right?
Yeah, so definitely. We kind of, I feel, are sometimes fighting an uphill battle because we don't get a lot of people from like IOI or USACO that come like to, work with us. So what we have to do instead is like a slightly different approach where we kind of like, bootstrap people that aren't normally competitive programmers. We really have to like focus on this sort of pipeline where we have people that are at this developmental level that we train for like 1 to 2 years to get to the point where they're kind of more at the regional level now. And then like, from there we hopefully can see who pans out to be world finals qualifying material. It's a very tough choice because we get a lot of students. UCF has like 70,000 enrollments or a deal. We have like 20,000, not 20,000, about 2,000 I think computer science students, but not everyone on the team is necessarily a computer science student. There was 1 year where we had like an electrical engineer who was like double majored like in some music thing, and then we had like a mathematician on that same team, and they ended up going to world finals. So that was kind of weird.
We've seen lots of those from other teams too. We've seen a petroleum engineer, we've seen biology, we've seen chemistry, we've seen one team where all 3 of the people were something else, I forget, to be honest. But yeah, lots of teams with like non-computer science engineers.
Yeah.
How does UCF go about picking which teams end up being on this World Finals team? I mean, obviously a lot of it comes down to regionals, right? Only the best team at regionals gets to compete here.
I was gonna say we don't really say who's gonna be on the NAC team. It's kind of the regional problem set that says who's gonna do that.
What about who competes at the regionals?
Yeah, so what we do is we do a tryout in the fall semester. We do like a practice in the first Saturday of the semester where we say this is kind of the setup that the contest is going to be in, so that way people can kind of get acclimated, know what the submissions are going to be like. They kind of have a feel for what the contest is going to be. And then we have an actual real tryouts the following weekend. Now, COVID actually kind of made things a little bit shaky for us, and what ended up happening is we've been doing like a 3-round thing where we do 1 practice round, then we do 1 virtual, which is kind of like a qualifying, and then we do 1 actual real tryout. And then what the coaches have to do is this really tough decision is looking at just like kind of 2 data points and trying to extrapolate that to like how people are going to be doing at these regional contests, which, I mean, sometimes it's clear cut. It's like, okay, so, these 3 people solve the set, they're going to probably be a really good team. Or it could be a case where like maybe 2 people solved the set, 1 person didn't solve the set, but they worked as a team together. So that's like a good thing to go ahead and do. We try to kind of keep some synergy and some cohesion going by trying to keep some people that have been on the same team together. I know that doesn't always happen. Sometimes it's a really tough choice when we see like someone that was on the same team as someone else, but they're like performing like 10 places below like where their team members were at. And then we have to make this kind of difficult choices like what is best for the programming team at this point? Is it going to be something where, socially it'll be better for them and they won't have to like adjust to new team dynamics? Or is it going to be, better for us to go ahead and put someone that's like a higher rated person or someone that has better knowledge coverage that could like assist them on those really hard, like, last hour problems that we would get these regional or these North American championship contests. So it's difficult, but what we do is we do try to separate, also the people that are younger that have a lot of eligibility and don't have a lot of programming experience, because those people have the potential to develop into flourishing competitive programmers. The people that are like math majors or something stupid like that. Not stupid. Math majors aren't stupid. I was a math major, but we can get them to into the system early, so that way we can go ahead and see what they end up turning out to in like maybe their junior or senior year.
One question that I have for lots of people who help like teach lots of people to grow up and teach lots of people competitive programming is this. You've seen so many people's path to being very new to competitive programming and really like, I mean, not even just like coming out of IOI, but just coming into computer science, maybe not being very good at programming, into being at a world finals level at the fight for the school to try and, get a medal, get a world finals team. Are there even any elements that you see that tend to be good predictors of success, where if people are doing these things, even if they're not at that level yet, where it's a more safe bet than average that they're going to be successful?
Outside of practice solving, like upsolving, I think is actually a really good indicator to see how people do in their contests, because when they're upsolving, it's not a matter of just that they're
and really quickly. So what does upsolving mean?
So upsolving is when you do a contest and you do what most people do, which is you don't solve every problem, and what you end up trying to help your improve your skill by working on those problems that you were close to getting in contest, but you ended up not finishing. And it could be a matter of like you you had the idea in contest, but then you weren't able to solve it within the 5-hour range. So you're working on it, or it could be like there was a problem that was heavily solved in contest and you didn't know how to approach it. So you like go out and learn a new technique. Maybe you talk to a friend that's like working on it. So there's a number of things that can be classified as upsolving. Another thing that happens in terms of upsolving is like if you're on a team and one of your team members gets the problem, but you personally didn't get it, like you might be able to learn something from it. So you work on it. It's really just solving a problem that you personally did not get in contest. And that can be incredibly helpful for people to like improve their knowledge, but also it shows you kind of who is actually interested in competitive programming and like who like has a desire to work on it. Some people do competitive programming just because it's something to go ahead and like put on their resume, and like they don't necessarily have, I feel like, the heart for the competitive programming. I'm not saying that if you hate upsolving, you're not going to be a good competitive programmer. I don't think like 100% of people that are good competitive programmers like upsolving, but you know, if you're into upsolving, then like it kind of shows that you have a drive, you have a desire to go ahead and improve yourself, and those people I think normally tend to grow a little bit faster. Or they don't like plateau as quickly as other people. And I don't think necessarily people plateau, it's just like people kind of limit themselves in terms of like what they can do.
One more thing I want to talk about, Travis, is what UCF does over summer break maybe, in order to practice and keep things growing. And if there are any stories you want to tell about that thing.
None good.
Maybe teams not Beehive.
Okay, so we have a lot of opportunities for people at UCF to practice in the summer to improve themselves, because like, you know, they have to get ready for the fall contest, and you know, it's really cutthroat at UCF because we have so many people trying out for the team. So people are always like trying to like improve themselves before the locals contest, so that way they can make the cut. So we have two main ways of doing it. We have weekly practices where everyone can go ahead and kind of like join in on the contests and compete against each other and kind of like, you know, see where they're at with respect to other people. And then we also have like this really large problem set that we developed, and we call it the 300 set because I think in the first year there was like 300 problems on it.
We also name a lot of things on the UCF programming team after Greek things. So we've got a Sparta website, 300.
Leonidas, Delios, So it's great. Glenn like does all that type of stuff. It's really good for the theming and stuff like that. It keeps things consistent, and also the Spartan training regimen is something that people are kind of like used to.
Yes,
like,
I love it.
Being tough.
Work hard, be tough, beat everybody else. Yeah. No, so we got this 300 set, which has lots of problems on it.
Yeah. Normally it's actually 150 problems, and what happens is there's been promises that if like someone gets to like 120 or something like that, then we'll release the next 150 problems. But that is something that kind of like keeps team members motivated. I think last year, like one of the team members got to like 100 or so, which is like kind of crazy. And that team member was like not even one of the like experienced members. That was like one that was like in the early stages in the pipeline as well. That was like a what we call like a developmental member. And like they were just like gun-ho, I need to get as many problems as possible. And I think they were like in the top 5 or something like that at the locals programming contest when it happened. So like that shows like, you know, if you're like putting this effort in like extra to go ahead and work on these problems, then like you'll end up doing well. And I should mention the 300 set is formed from problems that we do Saturday practices at UCF to like get people ready. And
5-hour contests.
Exactly. Trying to keep it as close to the ICPC style as possible, because that's what we really target. And what we do is we take all the problems that weren't solved in those contests, or they were solved by very, very few teams, and we, you know, kind of combine them into the set. And we sometimes roll over problems from previous 300 sets that weren't solved as well. So we get like a lot of problems that are very challenging for students to get. So even getting like a few of these problems is like kind of meaningful for team members in general. But yeah, so it's a pretty amazing feat that someone that was like at this lower stage of the pipeline was able to get these problems that like the upper classmen were unable to get during these 5-hour contests. It showed a tremendous dedication to the art of competitive programming.
Yeah, I've always said, you know, at some point in competitive programming, eventually you will eventually be somewhat limited by intelligence. It does matter.
Yeah.
That said, the percent of people who are effectively limited by intelligence in competitive programming is very, very, very tiny.
Yeah.
Almost everybody, it's an insufficient practice. There are tools that exist that they have full capacity to learn, and they just haven't done it.
Mm-hmm.
And like being able to learn all those tools and see all the things everybody else has seen before, it helps so much.
Mm-hmm.
And you're easily able to get massively through the ranks if you do put in the effort. And if you don't put in the effort, no matter how intelligent you are, it's going to be very, very, very difficult to get to where contestants like UCF Beehive are today.
Yep.
All right, thank you so much, Travis. We're going to take a quick ad break, and we'll be right back.
All right, it was nice being here. Thank you so much for the invitation.
Yeah. Thank you for coming.
No problem.
All right. What are we saying here? Is this two Sigma? Yes. There we go.
So I interned at 2 Sigma last summer, and I returned this fall primarily because of the people I met.
I feel like people here genuinely form a community around shared interests, usually a shared passion for science and tech.
Honestly speaking, finance wasn't on my list when I started job hunting. But when I came here, everyone was so smart and so friendly and so sincere. And I feel like my skill set can be truly valued here, and that's something really important to me.
There's so many cool, exciting projects to work on, and I know I'm going to be working with those people that are super knowledgeable, and that's like what drives me to move forward.
At other tech companies I've worked at, you can kind of feel like you're a very, very small part of a very, very large thing, and that you're kind of expendable that way. Whereas here, people are extremely invested in my success.
This is just the perfect place to be. So yeah, I'm pretty happy I made that decision.
Good morning and welcome back. We have a quick scoreboard update here with Jinbang. How's it going?
Hi.
Welcome. What's new on the scoreboard?
I think CMU just passed and that to 9, same as MIT. So we have 2 9 teams right now, I guess. Yeah, and Georgia Tech is still wrong answer in J.
And yeah, it's a tough fight. We've got room still left on B, some wrong answers on J. And it looks like you're currently coding J right now, huh?
Yeah, I'm coding J now. I mean, J is not a hard problem. It's like, because the length of the string is short, so you only have to figure out the right way to enumerate the right things. Like brute force on everything and taste analysis.
Tourist was here just a couple minutes ago. We talked about the solution to it. We kind of figured it out live on stream. We have an n cubed with z values, but I won't spoil anything else.
Yeah, mine is something like just n to the 3, something like that. So I think it's basically the same thing. It's all about the right way to enumerate, I would say.
Sounds great. All right, how is Georgia Tech doing today? What are your thoughts on their performance? And it looks like they just got a submission to J.
Is it for frozen board, or we didn't see?
Yes. So we're 4 hours in. All right, tell us about the scoreboard freeze. What does that mean?
Oh, that means that in the last hour you cannot know about the result, like, because it will be all hidden and will be revealed in the closing ceremony. So it's very important. This is like the fun part, the funniest part about the ICPC. It's like everyone will be more nervous. You can only count on yourself. No matter it's the students, you are the contestants, or you are the coaches, you don't know anything.
We'll talk about some of the possible scoreboard freeze options in just a minute. But yeah, it's very exciting. After the contest, we'll have probably a 3-hour break or so, and then we'll have the closing ceremonies. In that, we will show the resolver, and we will resolve all of these hidden submissions. You'll see whether they're right or wrong, and teams will move up the scoreboard if they're right, or stay where they are if they're wrong, and that'll reveal the final order of all of these submissions. But that depends on, over the next 58 minutes, whether teams get the problems right or wrong.
Right.
All right. Tell us a little bit about Georgia Tech.
I mean, Georgia Tech, I would say that they are not having a good performance today. And they are like basically like behind the scoreboard for a long time, and even like getting 1 out of 4 problems in the very beginning, 1 or 2 hours. And they finally get bad by doing 1 and 1, and they finally come back to the medalist, like top 6. So I would say that they would do maybe better in the normal, like less penalties or something. But I guess, I mean, at this point, it's like because it's under great pressure. And this is on site, so we cannot ask for more, because like they will be definitely be more nervous than the normal practice. So I think the current strategy things is like is correct. So basically, it's like they are doing whatever problem that I predict they will be doing. It's like, so we know that the first few problems is like quite ad hoc. You need case analysis, like you need careful implementation, so without penalties. But they are still doing the problems from the middle. And then they have time, they come back for AC in it, and just like, so they have 2 people who can mainly code long things. So I guess they are like coding B and J at some point at the same time, and then when they pass B, so the third person who's working on maths, he come back for the game theory problems. I'm not sure whether
So you've seen J, you know quite a bit about it. Do you think it's a good strategy for them to go for both B and J at this point with less than an hour left?
I mean, B, they already passed B, so I mean, right now they can only do is like.
Oh wait, yeah. Did they just have a submission to J? Was that what we saw?
Yeah.
They've already submitted. Okay.
I mean that's like the third submission. I mean, I'm not sure whether pass or not, but I hope so.
So it seems like at this point they're at least in 7th place, which is pretty good. There's a good chance that'll be eligible to qualify for World Finals anyway.
Yes, I mean I'm aiming for medals, I would say.
Yeah. So that means they need like at least one more.
Right.
Probably 2. Well, I mean they probably one more might medal.
I mean in general for every team, it will be really dangerous if you don't pass anything in the last hour.
Oh, for sure, yeah.
Because everyone is like working very hard, and I mean it's at the edge of the point that you have to pass anything, or maybe there will be like 10 more teams that passing you. So basically, that's what happened to last year's Michigan.
Especially this year, you have these 2 medium hard problems which are very doable. You have both B and J.
Yeah, and then you have like L is a very. I also told L is very short problems that is like 1 or 2 lines you can finish it. So basically, it's like generally for all the teams today, it's like basically how good they are. This depends on how they deal with B, J, L together.
Absolutely.
So 3 of them will have to 2 of them is coding B and J at the same time or similar time, and 1 of them we have to think about J and pick the right time to finish it. So I would say this is a very, very good part of this analysis. Is like it actually required the teams to construct a strategy. It's not about like one person soloing everything. It's not like that. That's the fun part about this.
Last thing I want to mention here before I let you go again. I know in this contest, contestants get sequestered before they lose their phones. They got to just kind of sit with all the other contestants for a good amount of time before the contest starts.
Right.
Is there anything that you've done to help prepare your students for that feeling, for the extra adrenaline if they get there?
I mean, I guess this is similar to something some other teams like. Last night we run a team meeting, the coach and we basically just discuss about like what's the thing, what's the strategy, what do we expect from each other, and more importantly, I'm telling them that okay, you guys already did a great season, you already did many trainings, so don't be nervous, just enjoy the contest, and moreover, it's like if you have anything to say or yell at your teammates, you better do it right now, not during the contest. So basically, it's like we have like 45-50 minute meeting last night, and I sent them back to sleep. So this morning I checked them. I think they are like pretty relaxed. I think it can be also been told from the performance. I mean, it must be really frustrating if like the first few problems you all got wrong answer. There are a lot of penalties, but I think they work it out. So I think they are in the good shape now. It's only I would expect coaches always expect better, but I mean they are already doing a great job.
Yeah, we've seen a lot of teams have a rough start. Certainly UCF, MIT, I guess Georgia Tech a little bit as well.
Yeah.
And despite the difficulty curve actually being very reasonable from the judges, I guess lots of teams this is their first time in this kind of experience. There are a lot of nerves, and it's very natural to go too fast, get stuff wrong.
Yeah, I mean, it's not the first time for 2 of the members in Georgia Tech. I mean, even like that, they are still very nervous. You see, they just submitted again, which means that they didn't pass in the previous submission. So I guess there are some connotations that I haven't known about in J.
And it looks like we got lots of other teams submitting to J as well. Purdue, UC Irvine, lots of them. So
yeah, I mean J is definitely the nice problem they want to get. The 8 or 9.
One of the members of UC Irvine, Kodakan, I believe, he can do, get this, 12 one-handed push-ups. Or pull-ups. 12 one-arm pull-ups.
I can't do that.
I don't know if this is assisted or unassisted. If it's assisted, it's like much more reasonable. Yeah. But if it's unassisted, that's insane.
Yes.
You have to be so strong. I can't even do 1.
Yeah.
I don't know how many I can do assisted, but
I'm gonna try my best to do 2, I guess.
Yeah, it's incredible.
Yeah, but
even with 2 arms, it's tough.
But you know that I mean, the physical practice is also very important in the contest. It's actually related because it's like if you are very tired in the end of game, you cannot do anything. So you have to like you not just practice helps. It's also like physical exercise is also helping for the 5-hour contest because it's actually long. It's 5 hours.
It is, yeah, and there's a lot of like mental energy that you burn doing this that you don't burn when you're like, watching TV or even at school. School's a lot easier than when you're like 100% thinking 100% of the time going as fast as you can.
Right.
5 hours you burn out if you're not careful.
Right.
So you got to practice and you got to have the physical strength too. All right, thank you so much.
Thank you
we
for
will
invitation.
we will see you in just a minute after this quick advertisement. Good morning and welcome back. We have a coach here from Kentucky, right?
University of Kentucky, yes. in
Welcome.
Lexington.
What is your team's name?
The team name, and this is basically probably why I'm here, just to explain the name, is University of Kentucky, so UKY dash, I will spell it because it's important for the story that I want to say. So UKY dash BBUN and CSM fan club, and I will explain the name. Okay, so UKY stands obviously for the University of Kentucky. BBN are initials of the last and first name of the student, but the meaning of that in Lexington is, and in Kentucky in general, is very well known. It stands for Big Blue Nation. And then there is an ampersand. It has also some meaning, I will explain later. CSM stands for the Colorado School of Mines fan club. And you know, I was asked, okay, why such a name? Because traditionally, University of Kentucky teams have very straightforward naming schema. It is UKY, just to identify this school, dash, and then typically 3 letters, okay, an acronym of something related to computer science like PNG or initials, as in this case. So the question is why such, where this name came about. And the story is that actually there is a team here actually in the NAC, the team from Colorado School of Mines that has a very symmetric name. Their name is simply Kentucky Fan Club. So the question is how the name, these names came about. And it started really about 1 year ago, also at the North America Championship in this very place. And it happened that the very first breakfast, or maybe even dinner after registration, my team sat together at a table with students from the Colorado School of Mines. And you know, just they chatted and had a nice conversation about problems and in general as students. And we actually sat at breakfast and dinners quite often. That was definitely some sort of, you know, just we liked joint conversations. And after the contest, when in late summer, practice is renewed. It also renewed activities of students, and my team joined a Discord server run by one of the students in Colorado School of Mines, and it renewed the acquaintance developed during the NCA, North America NAC. So you know, just after practices, and they just enjoyed practices, both teams came up with that idea of, expressing this mutual, recognition of the schools. So that's really the story. But if you allow me, I would like to give 3 points that I see really testify, just tell about the broader impact of
Yeah, absolutely.
And AC. So firstly, it is the organization and the structure of an AC, and this is really I would like to recognize. It's very important to recognize people in the process because nothing happens by itself. So I would like to recognize Dr. Tony Logar, the manager director of the AC, that she has been able to create the environment that is not only for competition, which is very important, and that's the purpose of the meeting, but also for students to socialize and really build camaraderie. So this is what is happening, and that's really something that lasts, for the entire life, networks, and just really process. There is the second impact, I believe, not impact, comment that I would like to say. Sometimes we are thinking about students participating in programming contests as really focusing on programming, not doing anything else. But, just creating names like that, discussions, why this name, we had some discussions about it, shows multidimensional talents of the students and the need to really do things and ability to do things beyond just programming. And I'm saying just, but just it's a very creative process, but it's not the only creativity that the students demonstrate. And if you allow me, with the third comment, it's a little bit of a joke, but it is what happened. I would title this item, and there is an ampersand to this story. So as I stressed, there is an ampersand joining 2 parts of the name, and Michael Roitko, who is the photographer of NAC, told me that finally he figured out, after some time and many efforts, why his efforts to upload our UKY team photographs to Flickr failed.
And it was because of the unusual character?
And that ampersand was the culprit. So we contributed to software engineering testing. So that's the story.
There you go. Yeah, very cool.
Yeah.
Make sure you test your code before submitting, and make sure you test it before pushing to prod too.
No, Michael just took it, really jokingly, and thanked me for, just providing good test. Okay, so it's a all positive story here. Mm-hmm.
Awesome, Jersey. Well, thank you so much. We will look at a solution video to, what do we think? Perhaps problem J here. It's a very advanced one. We can take a look. And we want to thank you for joining us.
Thank you very much for inviting me. Thank you.
Hi, my name is Nick, and I am here to present a solution to problem J, repetitive string invention. Given a string S, we wish to compute a number of ways to concatenate 2 non-overlapping substrings to make a repetitive string. A repetitive string is a string with even length, where the first half is equal to the second half. The string can have length at most 800. There are 2 cases to consider. The first case is where the 2 substrings are equal. The second case is where the 2 substrings have different lengths. Therefore, the longer substring must take the form ABA, where A and B are not characters but substrings, and then the shorter one must therefore have a length, or it must just be B. So what we'll do is we'll pre-compute the longest common prefix array, in this case LCP_I of j, to be the longest common substring starting at indices I and j. So we can use this array to handle the first case, where 2 substrings are equal in quadratic time. We need to be careful that the strings don't overlap. In the other case, what we can do is we fix what B, the shorter substring, must be in the longer substring. For some fixed B, we can brute force what values of A are valid by fixing the position D that the longer substring starts with. With some prefix sums, we can compute this in n cubed. Contestants might notice that the bound was 800, which is actually fairly large for a problem where the intended solution was cubic time. This is because the solution that runs in n to the fourth, without some of these optimizations, actually runs very quickly with a good constant factor. So in order to make this problem viable, we had to make the bounds relatively high.
Welcome back, everybody. We are in the final hour. We have about 40 minutes left. And at this point, we were hoping Andrew would have finished the set. So we're going to take a look at the scoreboard first and then how he's doing. Here we go. All right. So we have University of Waterloo has 10 problems. They're sitting very pretty with submission or with penalty points. One thing to keep in mind, if another team gets a problem correct at the last minute of contest, that'll be at the very least 300 penalty points. Here we go. We have Carnegie Mellon. They have 1 submission in the last hour. So that's at least 240 penalty points. But they also have 5 wrong answers. So even if they got that correct, they have about the same amount of penalty as Waterloo. Already, I guess they have 400 points more. So, oh, interesting. Okay, yeah, this is optimistic. So this is not necessarily what's true, but you can see they're massively behind in penalty. This is even if every submit every team has made is correct, which certainly isn't the case. But Waterloo's still doing amazing on penalty. So the only way Waterloo loses is if some team comes out of the woodwork with at least 2 problems. That's either MIT or Carnegie Mellon, or Purdue, Maryland, or Stanford, or Georgia Tech gets, 3 problems in the last hour. So that would be an incredible performance by any of them. It seems unlikely since all of the reasonable teams who are in contention all have B. So that means J is very, very gettable. But then you have to get 2 of D, E, M, or H. Very tricky. Yeah, welcome here. You don't have like top secret information here that I can't see, right?
Nope.
All right, good. All right. So yeah, we're talking about the final standings here. Anything worth saying?
So I understand that this year we now have functionality to show the optimistic and the pessimistic scoreboard. And so I remember actually at the 2020 broadcast, we showed the optimistic scoreboard. And then I remember saying, these teams are guaranteed to make it to... We knew how many slots there were, so I was like, these teams are guaranteed to make it to the World Finals because under the optimistic rules, whatever. And there was a whole bunch of stuff. But
it ended up being right?
I mean, yeah, I was right. But
Okay.
I mean, yeah.
So this year, under the optimistic rules, which team are guaranteed to make to World Finals? Certainly Waterloo. Probably everyone who currently has a medal.
I think every team, I think that every team that has 8 problems solved under the current settings is definitely guaranteed. I do not foresee, as a caveat, just so people don't go bombarding me later. I'm not saying I don't have the authority to give out World Final slots and whatever, but if you had to ask me looking at this scoreboard, I would say for sure, everyone with 8, I would expect them to go to World Finals. And I don't know how many slots there are. That's above my pay grade. But if you told me that the cutoff was 7 problems, it might be a bit much. But, the cutoff, I think that you must... I feel like at this point, it's you must solve 7. And it might have to be a fast 7 depending on how the board goes. That's my speculation. I haven't actually looked at the judge scoreboard very carefully, so I'm saying this without leaking any information. So don't assume that I'm trying to
tell us secret stuff.
Yeah, I'm just...
You'll have to stay tuned for the resolver.
Yeah, I've been focused on the public scoreboard because I was told I would be showing up in the 5th hour, and so just before the contest, I didn't want to leak anything about the contest. I have intentionally not looked at the judge scoreboard since the freeze, so I'm actually in the dark. So I'm just speculating, sort of based on what I know about the problems, what I've seen, looking at these submissions and so on. So if someone wanted to pull a cutoff from me, it would probably be a somewhat fast 7 problems. I don't think every team that solves 7 problems will make it to World Finals, but I would say at least half of them it just depends on how many teams solve 7.
Really quickly, we got 2 submits from Iowa State U on G, it appears. So the first one probably wasn't right, but maybe they found their bug. Notably, they have the #1 globally ranked Brawlhalla player. This is like a fighting game. And one of them was sleeping on the bathroom floor their first day.
Oh my.
So yeah, pretty fun story from Iowa State. Hopefully they had a good night's sleep last night. And hopefully they figure out whatever's going on with problem G.
Yeah.
That's all I've got to say.
Yeah, I do wonder, like, how many people get a good night's sleep the night before the contest. I will say that I was up until, like, I don't know, 1:30 a.m. And then I woke up at 6 a.m. and I was like, all right, it's contest day, let's go.
I feel like you have a history of getting not so great sleep before big contests, Nick.
Yeah, I definitely am running. I run on a lot of adrenaline, I think, during contests. It's just, like, I remember I, like, showed up here at 7:30 and the operations folks were like, are you a judge or are you in ops? And I was like, oh, I'm a judge. And they're like, cool, you can help us in operations right now. And so I spent an hour assembling lunches for all the students and doing a bunch of moving things and stuff. And then people were like, I thought you were a judge. I didn't think you were helping us move stuff. But, you know, I showed up. I do apparently everything at ICPC nowadays. I'm not just a judge. I'm on the live stream half the time anyway, so, you know.
Exactly, yeah. Lydia, would you mind taking a quick look at U Chicago? It looks like they have jumped up in the standings. They're now 22nd place, or I guess pessimistically. And they haven't made any submits in the last hour, but they're doing better than I remember. They're a very fun team, I'll say that much. If we have their picture here, you might not be able to tell given that the only people here are their team, but the average height of this team is 6 foot 1 inch, and they're almost all the same height. So these are all four wonderful men, 6 feet or taller. They are very popular with the ladies. That's what everybody says. They tell me that. That's what they say. That's what everybody tells me. And their team name, as you can see here, is Ned Tegtmeyer. What does that mean? Do you have any guesses?
Nope.
This is one of their teammates' roommates. And the reason they named their team after one of their teammates' roommates is they felt it would be absolutely hilarious if this roommate was looked up on Google, who has nothing to do with ICPC, doesn't really even program. If he shows up in the ICPC World Finals, that's where his name gets hit. So kind of a fun story. Derek is a huge fan of horse sports. Henry's first time in Florida is this competition, this North American Championship. And overall, they're some very, very fun folks.
Yeah, I have to say that on the topic of naming teams after random people who are not competitive programmers, I am actually guilty of this. I'm not going to say this person's name on the live stream because I don't want this person getting lots of undue attention. But people who know me and know some of my team names, I compete on a team with some of my friends, and so my first job out of undergrad was working at Dropbox.
Are some of these friends your brothers?
I haven't talked to my brothers in a very long time. Anyway,
this is a running joke. There are 2 other very well-known competitive programmers, Scott Wu and Neil Wu, who are in fact brothers.
And for the record, I am not actually their brother.
They are not related to Nick Wu.
I am not.
Nick Wu.
I am not related to them, but it has been a running joke for many years that I'm related to them. So every time people ask me how my brothers are doing, I say, I haven't talked to them for years, because I actually haven't talked to them for years. Anyway, back to my naming story. So I formed a team with a couple friends at Dropbox one time, and we were thinking about what to name our team, and at that point, one of our coworkers walked by, and they were like, "What are you doing?" And we were like, "Oh, we're planning a programming contest." And then she was like, "Oh, that's cool," and then she just walked away because she knows that we like programming and stuff, but like explaining a programming contest is it's a bit of an ordeal. And then we're like, what are we gonna name our team? And then I was like, oh, we should just say we're like her fan club. So we named ourselves like this person fan club. So if you look up all my like fan club like team names, you'll like find this like former coworker of mine, but did want to I have done this before where I have named a team after some person who has no programming contest affiliation.
Lots of stories here about Person Fan Club. We've got Colorado School of Mines Fan Club, University of Kentucky Fan Club here today, and it's a common thing on Code Forces, right? I love this person.
Yeah, lots and lots of fan clubs, and you know, I don't know if you mentioned this when Gennady was on the stream, but I've been hanging out with him like every day since like day one, and we'll be like eating lunch or like at some event or whatever, and then in the like the far background you'll see like a couple people, and they'll be looking at us, or they'll be looking like in his direction, and then like I'll like look over and see them looking at him, and I'm like, oh, okay, they're gonna ask him for a picture, and so you'll see them like tiptoeing like to Genna, and then they'll like he'll like turn and he'll see them and they'll wave and they'll be like, are you tourist? And it's like, yeah, everyone knows he's tourist. And actually, so many people were really shocked to see him. They weren't expecting him to be at NAC because, I don't know, he doesn't really have any affiliation.
We've got Neil in the comments.
Oh, God.
Oh, my goodness. Hilarious.
No. Oh, my God. I'm getting called out here. Yeah,
oh, man.
That even wasn't planned. Like, I did go to New York 6 months ago, and they were all in New York, and it was I think it was Scott's birthday party, and someone was like, do you want to go to Scott's birthday party? And I'm like, I just flew in, but sure. And next thing I know, I'm wishing Scott happy birthday, and of course Neil's there, and a bunch of competitive programmers are in the room, and once again I'm in a room where I'm like in the bottom half of Code Force's ratings.
We've got University of Minnesota with a submit on K. They already have 3 problems. This might be their 4th. For 2/3 of their team this year, this year's regional was the first contest they had ever competed in. For 2/3 of their team.
That's crazy.
That is crazy. To make it to NAC and to be doing comparatively pretty well. I mean, yeah, my coach used to say 1 is good, 2 is great. They've already got 3, maybe 4.
That's really crazy. Like when I started doing ICPC, like I didn't make it. So back when I was doing regionals, back when we were doing regionals, there wasn't NAC. It was just regionals to world finals. And I remember like my first regionals, I was a freshman, and everyone else was like a senior or like a grad student. And yeah, there were people with tons of experience, and like we didn't stand a chance. And like I had been doing contests for like 4 years at that point. Like I did USA Computing Olympiad in high school, so I had a ton of experience going in, and I was still like outclassed. So to see these teams comprised of individuals where their first contest is their first regional, like that's like it's really inspiring just to see, like, you know, your first contest, you can make it to NAC. Now the question is, will they make it to World Finals?
Speaking of improving and getting better, Lydia, can we take a look at UC Davis? One of the members from UC Davis is he's named Theo, and I actually coached him when I was in later part of college. Here on the left here, we have Theo.
That's David. That's UCLA.
Oh, hang on. Well, it is Davis. Maybe just the thing on the bottom is different.
Oh, I see.
Yeah, this is Davis. That's definitely Theo. Mm-hmm. So yeah. But Theo, I coached him when he was in USACO. He was in high school training for USACO. I was in college. And I helped coach him to do better, and now I got to see him at NAC. Very small world. Mm-hmm. It's good to see that he's doing pretty well. He's got F, I, K, and G. Always good to see. Looks like they've got quite a few submits on A, and they were trying C. Maybe they're not quite there on A, but they're doing pretty well. They are also, as you might be able to tell from their stature, climbing and gym bros. So far this weekend, as of last night for dinner, they had hit the gym twice already. Which is probably more than most teams this weekend, although there are quite a few runners here.
I remember the night I checked in to the hotel, one of the first things I did was I went down to the fitness center, and I saw one of the sponsors.
Hang on, sorry, real quick. Waterloo, who has 10 problems left, they're in first place. They just submitted to M.
Oh my.
So that would give them 11 problems. And wait, how many problems are in the set? 12?
13.
13. Oh, okay. All right, so they're not there yet.
There was
done.
There was some speculation among some of the coaches over which of D, H, and M Waterloo would target. They already excuse me, they already had a incorrect submission on problem D, and that was the optimistic standings. I got a little unnerved that there was some leaking going on. But yeah, if they solved M, that would put them at 11. They would maintain their first place, and then another team would have to solve yet another problem in order to overtake them. So it'll be interesting to see if they got it. I think no team had solved M prior to the freeze. No team had solved M prior to the freeze, and I think there have been.
I think it was Harvard. If I remember, I think
Harvard did attempt M. I don't know I don't know if that was before or after freeze.
They attempted it like several times before the freeze, and then once after the freeze so far at least.
Okay. Yeah. So So I think that we'll see if they get it. M is pretty involved. Did you talk about it with Genna or not?
I didn't get a chance to, but I don't know. I guess I just don't see why it's so hard.
M is
like okay. So first of all, let's be clear. The geometry part of M does not matter, right? The geometry is trivial. All that matters is whether things are collinear. Right? That's it?
I would not say that the geometry part is completely trivial. I think 3D ray intersection is...
Do you have to do ray intersection?
You have to do... There is 3D ray intersection involved.
Oh, but it's ray intersects a point.
No, it's ray intersection. You need two ray...
Oh, because they could point to a person who's here?
You need to... So... Okay, so in problem M, just to remind folks about what the problem was.
We haven't actually talked about the problem.
Oh, we haven't talked about it?
Yeah,
okay.
let's talk about it.
You should
now.
read the problem. Well, the problem's a little long, but basically the way that the problem works, I'm going to give a bit of like a reframed version just to avoid the flavor. So imagine that you have a bunch of laser pointers in 3D space. So a laser pointer is just like a point, and it's shooting a laser in some direction. And what you want to do is you want the laser pointers to be arranged in a way such that there are two conditions to meet. One is that each laser is actually the only concern is that each laser must be pointed at by exactly one other laser.
Yes. So in this case, we have that satisfied. So every point points towards another point.
Yeah.
And every point is... That doesn't matter. What matters is every point is pointed at by one point.
Mm-hmm.
Yeah.
And so in the original configuration of all the laser pointers, you can either change the direction that a laser pointer is pointing in, or you can translate the pointer. So the direction stays the same, but you can move the point in space. Changing the direction of a pointer is cost 1. Moving a pointer is cost 1,000, and so you want to minimize the cost of doing this. So
to be clear, there are fewer than 1,000 laser pointers,
Mm-hmm.
which means it's always better to rotate everything than it would be to move one thing.
Right. So so the first part that you do in this problem is you determine, do you need to do any moving whatsoever? Because if you don't need to move at all, then you have essentially a matching problem.
So to be clear, yes, that's true. But to be clear, you also need to minimize how many times you move, right?
Right. So that's why like in the matching you will compute the minimum cost matching. So you will match each laser pointer to another laser pointer, and then you will minimize the cost of that matching. And so as long as you don't need to move any lasers, if you have minimum cost matching, which most teams usually embed minimum cost matching into their TRD, their team reference document. Have we talked about TRDs yet?
Wait a minute, this isn't bipartite, is it? Just like the book code, right?
Right.
Yeah, we'll assume people know what book code is. You got to bring some code on site, blah blah blah.
So,
but wait, is it the graph bipartite or no?
Well, you manufacture. Well, what you do is you draw in a matching. You do like one of the standard constructions you do is you take each point and you copy it. So you have laser pointers 1 through n on the left, and then laser pointers 1 through n on the right, and then you draw a connected edge from like left I to right j. So you can match like left I to right J.
Ah, I see. So it is bipartite. So it's just flow.
You manufacture a bipartite graph. Like the graph itself is not, there's not inherently a bipartiteness, because like your cycles can be odd in length, which wouldn't be bipartite.
So yeah, so for instance, like if 1 is naturally pointing at 2,
Mhm.
and 3 is also naturally pointing at 2, and
That-
2
yeah.
is pointing at 1,
so
then
so
this is the original graph, and then you have like this,
Yeah.
right?
Yeah, and so in the minimum cost matching, there were 2 types of edges. There's a cost 0 edge. So if 2 is already pointing at 1, for example, then you connect it with a cost 0 edge. If you can take a laser pointer 2 and point it at 1 somehow, and it can actually shine on 1, then you add a cost 1 edge. One thing that I didn't actually say here is that, as in real life, sort of, when you shine a laser on something, the first thing it hits, it like blocks the rest of the laser. So if you have like, if you had 3 laser pointers in a line, and there was like 1, 2, 3, and you point laser 1 in the direction of laser 2, then you can never hit laser 3 because laser 2 is blocking it. So that's one other nuance that I kind of omitted to.
Wait, you run
mention.
flow on this graph?
You run min cost matching, min cost max flow or min cost bipartite matching on this graph. So
wait, is that just so? Wait, hang on. So sorry, don't we just want the maximum number of zeros that we can keep?
No, but because the point here is that, so this is what I was saying while you were drawing this, which is, if I have 3 lasers in a row, like 1, 2, and 3, and you shine laser 1 in the direction of laser 2, it can never hit laser 3. You can never add an edge from 1 to 3. So it's not actually about maximizing the number of zeros. You actually...
Wait, why is it not?
Because...
Oh, because some edges aren't possible.
Yeah, if some edges aren't possible, then you might be forced to... You're like forced to do something. So like one example might be you have like a plus sign, and then you have like 1 point in the middle of nowhere.
Okay, yeah, this is definitely harder than I expected. All right, let's draw this. So you have a plus sign.
So you have like a plus sign. So you have like 5 lasers in a row, and then 5 lasers in a column. Or like so like make a plus sign with like 5, like a column of 5 lasers, and then like a row of 5 lasers.
Okay.
So in this case, if you consider like the leftmost laser, that one can hit 5 different lasers, right? It can hit, yeah. So you're drawing them all out. So like this is like one. So like note that the graph that you're going to draw, it's not going to be complete. In fact, it's very easy to construct them where it's not close to being complete. So
yeah, anytime you have 3 collinear points, then you have issues. Okay.
Yeah. So this is why it is min cost matching and not just a greedy like maximum bipartite matching, because even if you try to if you maximize the number of zeros, you might put yourself in a position where you don't actually match with you don't actually end up matching with anyone else. And like an easy way to see this is like, imagine each prong of the plus sign, imagine that they're pointing at each other.
What do you mean?
In the row of 5, you could have like the leftmost one pointing to the right, and then the second one pointing to the left. So these 2 are looking at each other.
Oh yeah.
Right?
So this guy would look this way.
Yeah.
Oops.
And then all 4 of the prongs are doing the same thing, but the center one might just be pointing in a random direction.
Like that?
Yeah.
Okay.
And so what happens is you like this one needs to point at something, but then something needs to point at the center. So in order for something to point at the center, you need to take one of the inner lasers on the one of the inner 4 lasers, and you need to move that one, even though those are already paired up.
Oh yeah. Okay. So all right. So if you pair these and you pair these and like you pair these.
Or no, you pair the 2 above it. The 2 above it.
You pair these.
And then the 2 below.
And these, yeah. Now
so
you're
the
in
center
trouble.
one isn't paired.
Yeah.
But this is not a legal state. In order to make this a legal state, you have to break one of the pairs to include the center somehow.
I see. Yeah. So you can't just maximize zeros. That doesn't work.
Yeah. So maximizing zeros is incorrect, and this is like one way of seeing it. So
this is possible, for instance, by they're.
Yeah, you can just make a right triangle.
Oh yeah, like this.
Yeah.
Yeah. Okay.
So this problem is like min cost matching is actually necessary here.
And how do you do min cost matching again? Maybe I should know this.
It's
I don't.
It's book code.
Honestly,
Yeah,
it's
yeah,
like
but
everyone's book code.
Is it like
The
is
way
this the Blossom filter thing, or is it something else?
Blossom is. Oh, you're thinking of
That's perfect matchings.
general matching.
Yeah, general
Blossom is general matching. The general idea for min cost matching is
It's like min cost max flow.
So min cost max flow is like the generalization of it.
Okay.
So if you think of it as min cost max flow, you can kind of just like run shortest path.
Oh, this is
and
like
then
Hungarian.
Yeah, it's Hungarian.
It's Hungarian. Okay. Yeah. Okay. I'm sorry.
Like this is why
I should have known that.
Most
but
people like most people are just like, oh, book code. Like,
Yeah.
Like I just copied my like some book code for min cost matching. Now, going back, like, this is if you don't have to move any of the.
Oh, it's even harder than this.
Lasers.
Yeah. So
some people might say, oh, you never have to move it, but there's actually a very simple case where you have to move it.
Just 3 in a row.
Yeah, just 3 in a row.
Yeah. Or 5 in a row.
3 in a row or 5 in a row. Basically, if they're all in a line, if they're all on a line and there is an odd number of them, you have to move one of them. Yeah. So this one's sad. So you have to move it off of that line. You have to and because the cost of moving one is bigger than the cost of rotating all of them, you can show that you will only move one of the pointers.
So, but like once they're not in a line, then you can do something like this.
Once it's not in a line, then you can always just make a triangle, for example. So then it's always possible. So you can show that this is the only case where you need to move it. You only need to move it when there's an odd number and they're all collinear.
So if they're an even number that are collinear, you can pair them up.
Yeah.
And if they're odd number that are collinear, yeah. So I guess let's explain a little bit why you only need this one, because I think that might not be intuitive to some people.
Mhm.
I see why, but like, so let's say you move this.
So
yeah.
if there are
Let's say there were 4 before we moved it.
Right.
So here we can pair these up, and now we can pair these up. Oh, I guess that would be true if we didn't move it. But
Yeah.
so now there were 5 before we moved it. So now we
Yeah.
moved it. So now we can make this triangle.
Yeah.
And we can always make a triangle because
Yeah.
there are one before and after, or like we could just do the top 2 anyway.
Yep.
It's just top 2 anyway. And now we have an even number of things here.
Exactly.
Yeah.
So yeah, it's not hard to see that you only need to move exactly one.
Okay. Yeah, and then it's bipartite matching. So why do you need 3D ray intersection code? Like you just need to see, like, is someone looking at someone else right now, right?
So you can have,
because you might have one person looking this. Sorry, go ahead.
So you can have so let's take the 3 case, and I'm gonna tell you the directions that each of them are pointing in.
Okay.
So let's have the top one, have it moving straight and to the right, like just to the right.
Okay.
Okay. Have the second one pointing up.
Straight up?
Yeah, just straight up. And then have the third one pointing like down and to the left at a 45-degree angle.
So there's nowhere we can move this guy to that will make a triangle? Is that what
No,
you're getting at?
my point is that you.
Oh, we need to know if there's a
No,
triangle.
my point is that you can move it to make a triangle, but notably, you can move it in such a way
that we won't have to rotate it.
That you won't have to rotate it.
I see.
So this is why you need 3D ray intersection, because you need to know.
Can you move it to a non-integer point?
Yes.
Sorry. Okay.
You can move it anywhere as long as they are at different points. You can move them anywhere.
Gotcha. Yeah, I see. So we're interested in like this we want to invert this ray, move it to here, and see if these.
Yeah,
two
you want to
intersect.
see if the ray at that direction is the same as like the existing point. If they intersect, because if they intersect, then you don't have to rotate it. If they do intersect, then you do have to rotate.
That is definitely a bit involved, especially for coming after 4 hours of coding.
Yeah, I think my solution to this problem came in at, I want to say, around 300 lines of code.
That's not terrible. Could be worse.
It's not terrible, but 300 lines of code is a lot to write. Even though like a lot of it is book code, like 300 is quite a bit. There are some metrics for like how many lines of code is reasonable to write in like an hour or so. So some coaches swear by this metric called LPH, lines per hour. And we talk about, what is the lines per hour of like
the winning team or like a world finals team. And a metric, I think a benchmark that has been used in the past is like if you can type like 100 lines per hour, like 500 lines in a 5-hour contest, that is usually enough to get you to world finals. And if you want to win world finals, you need to go from like 100 LPH to maybe 200 or 250. The top individuals for like relatively easy, like we only count this metric for like hard problem sets. For easy problem sets, it's very easy to have an inflated count, especially if you type quickly. So we only care about this metric for like world finals level difficulty or, you know, like NAC. So like for hard sets, like you average it over the full 5 hours. So if you're not like, this takes into account the fact that you'll be spending time solving problems. So even if, you know, you can type like 150 words a minute or something, like you're not spending all of your contest time typing code, you're spending time thinking about it and stuff. So if we look at Andrew, for example.
Yeah, looking at Andrew, well, I mean, pausing right there real quick. So it looks like he has a solution to D, it looks like. He's doing stuff with priority queues, and it seems like what we talked about with Tourist. So it seems like he has the right idea, but maybe he's got some bug. He's also looking through the statement, trying to figure out maybe something he's doing wrong.
Problem D, I think, is very easy to get wrong in the sense that the merging logic is a little bit tricky, and then when you...
Yeah, like the idea is very easy, but merging it correctly sounds tough.
Yeah, the merging...
Like the math.
Yeah, merging it is, and making sure that you like reconstruct it is the hard part. Because I think computing the answer, like computing the expected cost is not that hard because you don't need to maintain any state. I think I think you don't have to maintain any like the full state because you can just maintain the expected cost like for each job when you do the merging. But because you have to do the reconstruction, you also have to maintain that. And so the reconstruction is the hard part. We also saw this like reconstruction being the hard part for problem C, like the broken minimum spanning tree problem. Like in that problem, I don't know if we talked about it that much, but you basically want to like build the minimum spanning tree by doing these edge swaps. And so conceptually, I don't think people have a hard time understanding like how you build a minimum spanning tree, but like actually reconstructing the sequence of swaps that you need to do is like the hard part of this problem.
I'm going to be honest, I've gone this entire 5-hour contest. I've never even looked at the problem C.
Whoops.
So, oops. I would have liked to, but oh well. Yeah, so it looks like Andrew is probably not going to solve the set, unfortunately. Maybe he'll get D, but...
I think it would be... I think a lot of... Or... I would not be surprised if Andrew's team solved the set, but it will take him close to the 5 hours too, because like problem D is, I'll call it an Andrew problem. Like between Andrew and Kevin, like I would expect Andrew to do it because the merging is more of like a data structure sort of thing, and Andrew's definitely more of a data structures person, whereas problem H is more of a math problem, and Kevin is, that's like, I think Andrew's no slouch at it, but Kevin, I think, specializes on it quite a bit.
Yeah, it should be cool. Let's take a look back at the scoreboard once more. So it looks like Waterloo's first submit to M was unsuccessful, and they've tried a second time. Carnegie Mellon might be able to secure their second place against potential invaders with a correct E solution, although they have quite a few submits to it, so who really knows at this point. They're definitely not going to beat Waterloo on penalty, though. They just don't have a chance. Purdue has 2 submits, maybe looking to jump into second place. Maryland has 1, which would probably put them into 4th if they get it, I would guess. Yeah, and it looks like we got a bunch of submits on E, which I'm very proud of myself for that prediction. Yeah, I predicted earlier E is going to be the waterfall, and it looks like E and J have been.
Yeah.
So
what does the optimistic board say? Like, can we get the optimistic board? Because I get the feeling that they're optimistically, assuming every team does solve every problem that they've submitted. We see that, you know, there are at least 23 teams at 7 and actually 13 teams at 8. That would be crazy if like every team got every submission. Maryland is in second. Purdue is in third. They pushed down Carnegie Mellon was originally in second, but they would go down to fourth.
Yeah, the real concerning thing here for me anyway is UCF. What is going to happen here if they don't get an eighth problem? It's I don't know. We'll see.
Yeah, one cool thing about this optimistic standings is assuming every team did get every solution, then 10 problems exactly is medaling, and then you need a fast 10 to get silver, and then Waterloo just 11 gets gold. And it'd be great to see, like, I think people have a lot of differing opinions on like how the scoreboard should look at like it for like all teams. Like do you want the first place team? You want the first place team to like win on problems and not really on penalty. And you kind of want the medal thresholds to maybe also be on a problem count threshold and not a penalty threshold.
It's like MIT just had one more submit on J. Yeah, I guess this is their first submit on J. So
yeah,
seems plausible.
These optimistic standings definitely.
Yeah, can we go back to the normal one? Optimistic is a bit much. And can we also scroll through them? Is that possible? Turn the scroll on. Yeah, so one of the teams I want to take a look at is McGill. They're kind of a fun team. It turns out they're very, very new to the whole competitive programming scene. They have 2 years of CP experience combined among the 3 team members. So they're very, very new to it. And we also have, now that we're in the last 5 minutes, as we heard called out, UT Dallas, it's their chance to shine. In the last 1 minute of their regionals, they were able to solve a problem correctly. And they could pull a rabbit out of the hat again today with a last 5 minute solve, maybe a last 1 minute solve. That might be a little too close for comfort, to be honest.
That's really clutch. It is very, very rare to see teams solving problems in like the last minute or two. I have a story from like my second so before NAC was a thing, it was called the North American Invitational Programming Contest, or NAIPC.
NAIPC, yep.
And then even before that, it was called UCIPC, the University of Chicago Invitational. So I had a sort of a Hail Mary-ish submission to a problem, and it got wrong answer, and there was like 2 minutes left, and I was like, oh shoot, I had this like fudge factor of like how many iterations I did something. So I was like, you know what, I'm gonna change 5 to 20. I'm gonna turn it in. So I changed 5 to 20. I turned it in, and I just kept refreshing, and the contest ended, and then I saw like the little pop-up box that said like accepted, and I was like, oh my god, I solved the problem in the last 2 minutes. And then that was the reason that we jumped from like 5th or something to 2nd. So
we just got a third submit from Waterloo on M. Seems like that means the first 2 may have been unsuccessful, though they could be trolling us at this point. Who really knows?
Yeah. So one thing to keep in mind here is that all the teams know that we are broadcasting, and so because everyone knows that everyone's broadcasting, there's going to be a lot of speculation, especially in the last 5 minutes. There's going to be a lot of submitting. There is this heuristic that teams do where it's like if you solve a problem, there's never a need to resubmit to the problem because you solved it. But because the submissions are frozen, like they don't see that. So you could have solved it and you could just resubmit your solution a few more times just to make it look like you're not. I don't think that's happening because the teams were very severely warned about non-frivolous submissions.
Yeah, we had some issues in the practice round, but we won't talk about those here. We've got Calgary with 2 different problems submitted, both A and G. They were attempting to bring a fidget spinner and yo-yo onto the contest floor. We do not know whether they were successful in that endeavor. I don't think so. They also have one teammate who only wears ICPC shirts. That's his entirety of his wardrobe. He has 8 of them so far, and I think with NAC he'll get 1 or 2 more, I believe.
That's crazy. I don't know how you can survive on a wardrobe of only ICPC shirts. I could
believe it. There are enough out there.
I've been doing this for years, and like my collection is pretty big, but I would want to wear, well, I guess I'm wearing an ICPC shirt right now, so I don't have much to say.
Calgary also has 2 first years. one of which Rosa is a math minor obsessed with category theory. And I mentioned earlier something about marriages. Their coach got married just after last NAC. So what a small world.
NAC, what a time to get married. Yeah, it's really inspiring to seeing a lot of these first-year students being able to make it to NAC. So, you know, even if, like, I don't know if we have any folks in high school who do programming contests who are watching the live stream, but you, like, if you're doing contests in high school and then you're going to your first year of college, like, you can definitely make it onto your local ICPC team, make it to NAC, and, you know, then next year at NAC, like, we'll be talking about how you're, like, the latest generation of first-year students who are competing at NAC.
We've got 1 minute left. We're going to speed run some fun facts here. We've got University of Virginia. They were on different ICPC teams until halfway through this year. Now they're on the same one, trying to qualify for World Finals today. We also have University of Washington. Their team name theme is polygons. They have one gon, not really related to monogon, but it's one letter. Digon, which is a two-sided polygon, and dragon, which is just dragon because they like dragons. That's it. UT Austin, they also had almost 2x the penalty of their second place team in regionals. They had 22 wrong answers, but were able to win on problems. Their coaches weren't super happy with how they were doing earlier today, but we will see. We got one more submit from Waterloo, ends in 10 seconds.
7, 6, 5, 4, 3, 2, 1.
All right.
Contest is over.
Congratulations to all of the teams.
And we just want to wish the members of Yale a happy birthday. All three of them have a birthday on the same week this year.
I saw beads of sweat running down everybody's forehead. So congratulations to all the teams. I know you're tired, so just a few announcements. Spectators, after the announcements, you're welcome to come out into the team area, take pictures, talk to your team. Contestants, you may take your signs and you may take your balloons. Please tie your balloons to your wrists so they don't go floating off. Immediately after this, you guys can visit a little bit. Hey guys, up here just for a minute. Immediately after this, you guys can visit, relax for a little bit, and then we're going to move out pretty quickly to go to a Citadel snack break. There's tons of great snacks and swag and fun. Right upstairs, I know a lot of you are probably starving. So up in Key West on the second floor will be the Citadel snack break. Hey, congratulations to all of you. It was an amazing contest to watch, and I will see you at the closing ceremony.
All right, thank you all for joining our stream today. We hope you enjoyed. The closing ceremony will be in a couple hours. We'll also be live streaming that, and then you can see the resolver and how all of your favorite teams did and who won the 2023 North American Championship. Thank you all very much. Thank you, Lydia, for all of the back-end work as well. And hope you guys have a great day.